ಬನ್ನಿ ಮೇಡಮ್
ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತೀನಿ ಸ್ಟ್ರೀಮ್ ಅದಕ್ಕೆ.
ಬನ್ನಿ ಮೇಡಮ್
ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತೀನಿ ಸ್ಟ್ರೀಮ್ ಅದಕ್ಕೆ.
ಬನ್ನಿ ಮೇಡಮ್
ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತೀನಿ ಸ್ಟ್ರೀಮ್ ಅದಕ್ಕೆ. ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತೀನಿ ಸ್ಟ್ರೀಮ್ ಅದಕ್ಕೆ. ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತೀನಿ ಸ್ಟ್ರೀಮ್ ಅದಕ್ಕೆ. ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತೀನಿ ಸ್ಟ್ರೀಮ್ ಅದಕ್ಕೆ. Yeah, and I guess Pradeep Ilani is
Okay.
not available now.
Okay, mine is second one, so I just
Second one. So I just want to do that. Ganesh?
yes.
Okay. Okay. Yeah, tell me.
PPTs.
No, PPT will be there. And I guess Pradeep Ilani is
Okay.
not available now.
Okay, mine is second one, so I just
Second one. So I just want to do that. Ganesh?
yes.
Okay. Okay. Yeah, tell me.
PPTs.
No, PPT will be there. And I guess Pradeep Ilani is
Okay.
not available now.
Okay, mine is second one, so I just
Second one. So I just want to do that. Ganesh?
yes.
Okay. Okay. Yeah, tell me.
PPTs.
No, PPT will be there. And I guess Pradeep Ilani is not available now.
Okay, mine is second one, so I just
Second one. So I just want to do that. Ganesh?
yes.
Okay. Okay. Yeah, tell me.
PPTs.
No, PPT will be there. And I guess Pradeep Ilani
Rolling. 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 Rolling.
ఏవి మోడ్లో ఉంది, ఏవి మోడ్లో ఉండకూడదు యాక్చువల్గా.
ఏవి మోడ్లో లేదు అది.
అదే సార్ నాకు తెలుసు.
చూడు.
ఒక్క నిమిషం ఉండు. దీంట్లో
యూ కెన్ చెక్ యాంగిల్ బిఫోర్ షూట్.
యాంగిల్ దీంట్లో వ్యూ పాయింట్లో ఒక్క నిమిషం.
లేదు, వీడియోలోనే ఉంది.
వీడియో పక్కన
ఇదే ఇదిగో ఇక్కడ ఉంది కదా.
ఓకేజీ
ఏవి మోడ్లో లేదు అది. 2.8 ఓపెన్ అయింది చూడు. అది ఎట్లయిపోతుంది. యూ కెన్ చెక్ యాంగిల్.
ఇప్పుడు తగ్గించలేమా మనము? తగ్గించలేమా?
తగ్గించేకైతే వీడియో మాన్యువల్
వీడియో పక్కన
ఇదే ఇదిగో ఇక్కడ ఉంది కదా. ఏవి మోడ్లో లేదు అది. 2.8 ఓపెన్ అయింది. ఇట్లా వస్తాం. ఐఏఎస్ఓ ఈఐ ఏవి ఆఫ్ అయింది అట్టో. ఏవి ఎక్కడ ఉంది? ఏవి మాన్యువల్ 50 MB.
దీంట్లో ప్రాక్సీ ఆన్లో ఉంది. ఇది ప్రాక్సీ ఆఫ్ చేద్దాం.
చెయ్యి. ఐఏఎస్ఓ ఈఐ ఏవి ఆఫ్ అయింది అట్టో. ఏవి ఎక్కడ ఉంది? ఏవి 50 MB. ఆఫ్లో పెట్టి ఆఫ్లో పెట్టి
Mic check. Okay, good. Okay. Yes. Everything working? Mic check. Live stream is on. Mic check करना है. Mic check. All. Okay. You have to turn it on. Ask them to turn on. Audio room. Mic check. Hello. Live stream is on. Mic check करना है.
Hello.
All.
Hello.
Turn it on. Ask them to turn on. Audio room. Mic check.
Hello.
Live stream is on. Mic check करना है.
Hello.
All. Ask them to turn on. Audio room. Mic check.
Hello. Speaker को बुला भाई.
Mic check करना है.
Hello. ले, come here. I just.
Ask them to turn on. Audio room.
Whenever you're putting the mic, make sure इसके नीचे हो, ठीक है, उनके हाइट के लिए. डन. इसके ऊपर होगा तो वही अच्छे से नहीं. मैग्नेट भी है और क्लिप भी है.
समझ गया? इसको ऐसे लगाना है स्पीकर के कॉलर पे मैग्नेट पे.
हेलो.
आई थिंक कि अगर चलेगा
हाइट.
हाइट
स्पीकर का हाइट है ना, नीचे चलते हैं.
ठीक है नीचे. हाँ ठीक है.
Whenever you're putting the mic, make sure इसके नीचे हो, ठीक है, उनके हाइट के लिए. डन. इसके ऊपर होगा.
This is down, right?
Because
मैग्नेट भी है और
stand
क्लिप
here.
भी है.
समझ
Yeah.
गया?
Okay. And plus, I have to keep standing here, right? I cannot move around. Yeah, sure.
आई थिंक कि अगर चलेगा
हाइट.
हाइट
स्पीकर का हाइट है ना,
All
नीचे
good?
चलते हैं.
सेम लेवल स्टिल.
This is it? Make sure इसके
Sure.
नीचे हो, ठीक है, उनके हाइट के लिए. डन. इसके ऊपर होगा.
This is down, right?
Because stand here.
Yeah. Okay. And plus, I have to keep standing here, right? I cannot move around. Yeah, sure. All good?
Same level still.
Let's get started. Good morning, everyone. My name is Govind Rajan. Welcome to this first session this morning. complete to introduce Professor Saurabh Banta from IIT Delhi. He got his BTech degree from IIT Delhi and PhD from Stanford. Currently, he's on a leave at Graviton Research Lab. Today, he's going to talk about super optimizer, and sure, we're all super excited to hear it.
Thank you very much, Professor Govind. It's a pleasure to be here. Thank you for having me. My talk is on imagining a next generation super optimizer. I hope the title sets the expectations correctly. Let me elaborate. Please focus on the word imagining. I am largely going to be painting a vision. I am going to draw on a work that has been done by other research groups.
My talk is on
And I'm going to
imagining a
talk
next
about
generation
work that
super
we have done in
optimizer.
this direction.
I hope
It's a
the
large
title
problem,
sets the
and there
expectations
are pieces
correctly. Let me
that
elaborate.
are,
Please focus on the
that
word
are kind of
imagining.
that I expect to come together in the future, and that's what this
Be
talk is all about.
painting a vision. I am going to
My
draw
affiliations are
on a
Graviton
work
Research Lab and
that has
IIT
been
Delhi as
done
listed
by other
here.
research groups.
I also
And I'm going to
run
talk
a
about
startup
work
called
that we have
Compiler
done
AI
in this
Labs,
direction.
which is like
I hope
too
it's a
many
large
abbreviations on a
problem,
single slide and things like
and
that.
there are
But I
pieces
just want to say that
elaborate.
all of these
But
things
please
basically
focus on the word
kind of do this
that I expect to come.
are working on some aspect of
Painting a
optimization,
vision.
super optimization, things
I
like
am
that.
going to
My
draw
affiliations
on
are
a
Graviton
work
Research
that
Lab
has
and
been
IIT
done
Delhi as and I'm going to talk about that
by
goal
research
today.
groups.
And
I
hope
also
run
run
able
a
to get the
startup
message
called
across.
Compiler AI Labs, which is like too many
So you may have
abbreviations on a single
noticed
slide
that
and things like
compilers
that.
have been
But I just want to
growing
say
in
that
complexity over the
all of
past
these
3
things
decades.
basically
Kind of do this. The
that I
chart
expect to
demonstrates the
are
number
working
of
on
lines
some
of code in the
aspect
GCC
of
compiler
painting a
over
vision.
time.
Things
Starting
like
from
my affiliations
1992,
are
the number
Graviton
of lines
Research
of
Lab
code
and
has
IIT
increased
Delhi, and I'm going to
linearly,
talk about that goal today.
basically as
Also
fast as humans could develop it. Today, GCC stands at over 22 million lines of code, which is an astounding amount of complexity, much of which is due to its code generation and optimization logic. All this good engineering or better engineering, the development model hasn't changed. And we see a similar growth in complexity for LLVM too. Here I show the lines of code in LLVM's core components, mostly the include and lib directories, in LLVM over time. Once again, we see a linear increase in complexity that is showing no signs of slowing down. The total lines of code in LLVM's core components stands at around 4 million lines of code today. It is thus no surprise that we witness some kind of a fatigue in compiler development. Students are afraid to enter this space, as even the best contributions may seem incremental in the setting. And it is not just about the new entrants. This example of a conversation shows how an existing compiler developer can feel disinterested in implementing yet another improvement that optimizes a particular coding pattern. The compiler requires millions of such incremental improvements to become and remain a top quality production compiler. However, each improvement involves laborious design and implementation, which is the root cause of the growth in compiler complexity over the past 3 decades and keeps the pace of compiler development slower than desired. I want to clarify that I'm not at all saying that compiler development has saturated. In fact, my next couple of slides motivate through examples that there remains lots of headroom for a compiler to improve. We just need a better development model. Simple implementation of the strlen function in C is shown on the left, and an optimized implementation as available in the glibc library is shown on the right. The glibc implementation first aligns the input pointer to a 4-byte boundary in the first loop over here. And then in its second loop, reads 4 bytes in one instruction and checks whether any of those 4 bytes are null by using this clever use of masks, arithmetic, and logical operations. This kind of things you will find in literature like A Hacker's Delight and things like that, where you can say, oh, how to do this thing using fewer number of instructions. If the expected size of the input strings is long, then this implementation can offer a 3 to 4x speed up over the simple implementation shown on the left. However, today's compilers are unable to perform such optimizations automatically. Here is another example. On the left is a functional specification of the strlen function. The functional language is our own, so don't read too much into it. It is similar to OCaml, but perhaps not identical. The functional specification just says that a string is formed by a nil-terminated list of characters, but does not specify how that list is implemented, whether as an array or a list or something in the middle. On the right is an implementation of strlen in C that uses a chunked list representation, chunked list to represent a string. It uses the same trick of reading 4 bytes in a single read, but it also stores a string non-contiguously to save space through sharing. It can be shown that these two implementations are mathematically equivalent. However, this seems well out of reach of today's compilers. There are many other examples of hand-coded optimizations that are in everyday use, but are either out of scope, poorly supported by a compiler today, even after decades of development. Complex rewrites involving SIMD vector instructions are one example. While ideas like superword level parallelism, SLP, tackle this problem in a significant way, there's still a lot of performance that is left on the floor with vectorization. The array-based strlen implementation that I showed on the previous slide is one such example of vectorization that a compiler cannot do today, even after all the years of development in vectorization. Data structure selection is another one that perhaps requires a higher level spec than C-like syntax, but a compiler is unable to do today. And there are many more, not necessarily present on the slide. I will not go through all the examples on this slide, as I don't think there's any controversy on the fact that there's much more that is possible than what compilers do today. One potential solution to this problem is to try and get machines to help us in this compiler development task. An overwhelmingly large fraction of the compiler complexity is its optimization logic. So if we could get the machines to automatically identify optimization opportunities, that would relieve the human programmers of this complex task and could potentially make the compiler development process faster. Here, we have two sets of algorithms. One set are the inductive synthesis algorithms that use certain heuristics and search strategies to automatically propose candidate solutions. You can imagine that these inductive synthesis algorithms are approximate. For example, they may be based on machine learning techniques. And so, the candidate solutions may be incorrect. However, a compiler cannot tolerate an incorrect optimization, and so we use a validator, also called an equivalence checker, that checks every candidate solution. This is the second set of required algorithms in this design. The equivalence checker checks the candidate solution for equivalence against the program specification. If it is able to prove that the two are equivalent, we obtain an optimized solution. On the other hand, if the equivalence checker is unable to prove that the program specification and the optimized assembly implementation are equivalent, it should hopefully generate a counterexample that demonstrates this inequivalence. A counterexample here is just a program input that would cause the specification and implementation to behave differently. This counterexample can then be used by the inductive synthesis algorithms to appropriately fine-tune their search. So better candidates are generated in the future. This vision has been painted by several researchers in a common theme of work called program superoptimization. The name superoptimization was coined by Henry Massillon in 1987, where he was interested in finding optimal implementation for a given problem using machine power. Now, the term superoptimization is used for a technique that uses machine power to discover optimizations, even though it may not necessarily be searching for the optimal solution. For inductive synthesis, there are several algorithms that have been proposed, starting from brute force enumeration, stochastic search, learning from examples, mutation-based learning, constraint solving, and many more. Recently, the breakthroughs in neural networks and large language models have made them a very promising approach to try and attack this problem. And I will talk about one such recent effort in more detail. Meta's LLM compiler is an LLM that has been trained and fine-tuned for 3 distinct tasks. Emulating a compiler involving specifying as input the unoptimized LLVM IR, the optimization flag, and obtaining the output IR and or assembly. The second task is for tuning compiler flags for optimizing code size. They give as input the program as an optimized LLVM IR and request the model to predict the required optimization flags for code size reduction and the output LLVM IR. Finally, the third task involves a task where the model is trained for disassembling assembly to LLVM IR, which basically means it's the inverse function of a compiler or a decompiler. I'll share more details about all these 3 efforts in my next few slides. Here is the prompt used for LLVM to LLVM compiler emulation. The prompt says, give the LLVM IR for the following code when optimized using this set of optimization passes as given to the opt tool in the LLVM instruction. Prompt also says that what is the input instruction count. So the input code has instruction count XYZ and binary size ABC bytes. And then it expects the LLM to answer that the LLVM IR that you output will have instruction count DEF and binary size GHI bytes. And then it will output the optimized LLVM IR. Now, this is the prompt and the answer. If you are aware of how LLMs are or how neural networks are trained, you just fill up the right answers for these dashes and train it over lots and lots of examples. And then you magically start expecting that it starts giving near approximately correct answers for unseen inputs. Here is another example. Here is a prompt for LLVM to x86 compiler emulation. Similar, give the assembly for the following code when optimized using opt passes. The input code has instruction count blah and binary size blah. And the answer that is expected is the assembly will have instruction count blah and binary size blah, and here is the assembly. What are the results? The results show that pre-training and fine-tuning helps significantly. After pre-training and fine-tuning using the prompts and answers that I showed you in the previous slide and lots of different correct answers, we see that 95.6% of the code that is generated by the LLM compiles. That means it's syntactically good LLVM. 20% of the generated code is an exact match for what LLVM produces, which I think is a phenomenal result. You can also see that before fine-tuning, so I'm looking at the last row here. You can also see that before fine-tuning, the exact number is near 0. So if you look at these numbers here before fine-tuning, so the LLM compiler starts with the code llama LLM, which has not been trained with all these prompts and things, and so the results are much poorer when it's not trained. But if you start training it, then it starts giving better results. But you can see, I mean, one thing that I noticed here is that the compiles value, which is 5.4%, is still pretty respectable, it's pretty high. So which basically means that Code Llama has already learned the LLVM syntax. It just doesn't know how to do compilation and decompilation, which fine-tuning allows it to learn. Here is another task that they did in their paper, which is an auto tuner. And here they try around 5,000 random sequences of passes per program. So recall that the second task was not about actually generating the LLVM IR from the blind or magically. The idea was just give me the right set of passes such that I can minimize the code size. And you know the OZ flag, I believe, yeah, the OZ flag is used for minimizing the code size that is given by default by LLVM on WinGCC. But it is well known that the code size that's produced by OZ is not necessarily the smallest that you can get. And if you use a different set of command line options, you can get a much better answer. And so the task here is what is the right set of command line options such that I get the minimum code size. I don't trust OZ. I want to do better than OZ. In this task, notice that I'm just training the LLM to predict what passes I need. I'm still using the compiler to kind of do the optimization and the code generation. And in this result, I think the primary result here is that it produces a 7.1% reduction in binary size over dash OZ after training and pre-tuning on the correct set of optimization flags. So what is the prompt here? The prompt is, tell me how to optimize this LLVM IR for object file size, and you give the LLVM IR. And the answer that you expect is the code has object file size of, so you expect the LLVM to predict what the object file size will be in x86. So sorry, you ask it, you expect the model to predict what the code size will be for the without any optimization. And then if you apply this optimization, then what will be the code size? And what will be the eventual code that will be generated? So all these tasks we expect the LLM to help us with. What are the results? Evaluated on an embedded benchmark suite called MyBench, MIBench, and with a 13 billion parameter LLM, this LLM generates object files that are shorter than -OZ in 61% cases. But it also sometimes generates object files that are larger than -OZ, and that happens in 12% cases. But there's an easy solution to that. You just run with -OZ and with the LLM and just pick the smaller one if you're interested in the smaller size. For some benchmarks, the improvements are as high as 13% extra reduction in code size. That's, I think, huge. The improvements with the 7 billion parameter model are often higher than the improvements obtained with the 13 billion parameter model. So it seems like the bigger the model, the better the results, at least at this scale. The third task that they did was disassembly or decompilation. Learn the inverse relationship for the command clang-xir, some C file, -o, some assembly file with the -s option. The prompt here is disassemble this code to LLVM IR, and you give the assembly code, and you expect the LLVM IR to be the answer. The LLVM is optimized. So to train this particular disassembly task, and to avoid redundancy, what the authors did was they optimized LLVM using the -OZ flag before lowering it to x86 assembly. So the idea is that you take some LLVM, you generate x86 assembly, you take the x86 assembly and put it in the prompt, take the LLVM, put it in the answer. But as we all know, there's redundancy. There are many different LLVM programs that give the same x86 assembly. So we want the one that is canonical, and for the canonical version, they just use the one that has the smallest size, let's say. And how do you know what's the smallest size? They just use a -OZ flag. Okay, so now the question is, how do we know that these outputs are correct? So they use a data set of 4.7 million samples. They have a context length of 8,000 tokens for the assembly and 8,000 tokens for the output IR. And the question is, how do they do the equivalence check? Well, they do round tripping. So what they do is they convert the disassembled LLVM IR back to assembly using Clang and check if we get an identical syntactic assembly. And if we do, we declare success. If we don't, then we declare failure. These are the results for the disassembly task. For 936 out of the 2015 input assembly programs, the output LLVM IR is well formed. So it's generating correct syntax LLVM IR for a large fraction, around 50% of the cases. Further, 14% of these programs produce exactly the same assembly when the LLVM IR was compiled back to the to assembly using Clang. In other words, they pass the round tripping test. These numbers are near 0 or 0 for Code Llama or GPT-4. So it tells us that training is helping. So to summarize, overall 96% compiles, 96% of the output compiles, and 20% exact match for compiler emulation, and 14% round trip match for disassembly or decompilation. These are both very promising results. But there are also significant macro opportunities for improvement in this space. First, these requirements of exact and round trip matches are too strict. Instead, we need a way to check the semantic equivalence match. Second, the LLM is used in a one-shot input-output setting, and there is no feedback to the LLM from the equivalence check. These seem like obvious areas of improvement. Because all these synthesis strategies are noisy, there is a need to validate the proposed optimizations. This validator is also called an equivalence checker. The equivalence checker must be sound. That is, it must return true only if the problem and solution programs are equivalent. However, it is hard to have an equivalence checker that is both sound and complete at the same time. In other words, the equivalence checker may return false even if the programs were equivalent. That is, it may have false negatives. The more robust an equivalence checker, that is, the fewer times it has false negatives, the more optimizations the super optimizer can potentially learn. Thus, the power of a super optimizer is in a big way dependent on the capabilities of the equivalence checker. For example, if an equivalence checker incorrectly discards a valid solution, our system will never be able to identify and learn the corresponding optimization, no matter how good our inductive synthesis algorithm or LLM is. As a recap, the full picture of a super optimizer includes an equivalence checker that iteratively interacts with the inductive synthesis algorithm to eventually produce a solution. Recall that we said that the capabilities of the equivalence checker determine the power of a super optimizer based development approach. The equivalence checker needs to support checks for end-to-end equivalence between an unoptimized program specification and a fully optimized implementation without assuming any knowledge of the intermediate steps used in the transformation pipeline. That is, it should be black box. It needs to support loops, aliasing information, floating point, and all the general constructs of an imperative programming language, such as function calls. The transformations it supports should include loop transformations like splitting, peeling, unrolling, unswitching, vectorization, etc. It should model memory precisely, including the presence of the ampersand operator, the address of operator, in the source code. Importantly, the equivalence checker must have no false positives. In other words, it must return true for truly equivalent programs. In other words, the equivalence checker must be sound. A false negative is a situation where an equivalence checker returns false when the programs are actually equivalent. It is perhaps not possible to build an equivalence checker that is both sound and has zero false negatives, because the problem is undecidable in general. The equivalence checker should aim to minimize such false negatives. This problem of equivalence checking has a well-known and important application in translation validation. Because compilers are so complex and may have bugs, a translation validator checks the source code against the machine code for equivalence. Because this is a well-understood experimental setting, we have been developing and testing our equivalence checker in this context too. Translation validation remains an open problem, and the development of an equivalence checker that performs automatic translation validation is a significant step forward in the development of provably correct compilers. Our research over the past many years has targeted this space, even though our broader motivations relate to a super optimizer based compiler design. We have tested our equivalence checker against mature optimizing compilers on large programs. We have also tested it across aggressive vectorizing transformations, either implemented manually, like the strlen example that I showed you in the beginning, or through a compiler. Now I'm going to walk you through a demo of our translation validator. Consider this strlen function that I showed you on the previous slide, just that it is in the VS Code environment this time. And here is the optimized implementation as available in glibc. Our equivalence checker can be used to start an equivalence check. So for example, I can start an equivalence check and an equivalence check has started here. I just want you to quickly walk through the optimized implementation once again. The first loop here basically aligns PTR to a 4-byte boundary, or the boundary of the size of an unsigned long. The second loop reads a long word, which is 4 bytes on a 32-bit architecture. If it was a 64-bit architecture, it would have been 8 bytes. And then checks whether, and does some clever tricks to basically check whether those 4 bytes contain a null byte anywhere. If not, then we have saved a lot of work. We can just continue and load the next 4 bytes. So that's where the 3 to 4x speed up comes from. If it does, then it checks which one is the one that is kind of which of those bytes is the null byte, and then based on that returns the correct answer. Our equivalence checker completed while I was speaking, and it was able to find the proof, and I can view the proof here. The proof itself is represented as a lockstep correlation between the two programs. It encodes the fact that what happens if one program takes one path. So for example, this edge says that if the optimized program goes from the beginning of the program to the head of the first loop, then the unoptimized program also goes from the beginning to its only loop. It also kind of encodes the invariance at this point. For example, it will encode the fact that PTR is equal to P when the two programs are at these respective stages. Then this edge basically says that one iteration of the first loop is equivalent to one iteration of the loop on the unoptimized program. This edge here says that if the first loop itself returns, then the unoptimized program also returns. This edge says that if the optimized program exits from the first loop, which means it has aligned to the 4-byte boundary and goes to the second loop, then the first program does nothing. It just stays at S6, the source line number 6. This edge says that one iteration of the optimized loop is equivalent to 4 iterations of the unoptimized loop, and you are able to identify relations invariance between the two. For example, PTR is equal to P. And finally, if the second loop exits, then the first loop exits with less than equal to 4 iterations. Now, I've shown you an example of source-to-source equivalence checking, but we are able to do source-to-assembly equivalence checking as well. And I'm not going to run it, but I'd run it before I started the talk. And here is an example of a program that that is basically heavily vectorized. So on the left is a program that's taken from the test suite of vectorizing benchmarks. It has a loop, it has multiple if then else's and memory accesses and things like that. And on the right is the optimized assembly, highly vectorized, generated by GCC. As you can see, it has lots of vector opcodes that it's using. It's actually pretty hard for a human to ascertain that these two programs are equivalent, but it's only a matter of minutes for the tool to kind of see that these two are equivalent. And once again, we have a correlation graph that encodes the lockstep correlation and the invariance between these two programs. So for example, this one loop in the assembly program is equivalent to 4 iterations of the C program. Thank you. Over the years, we have found several bugs in compilers and other software such as the QEMU binary translator, a C libraries, and an SMT solver. All these bugs were found using our equivalence checker. In all these cases, when an expected equivalence proof failed we tried to identify the reason for the failure. We would typically expect a shortcoming of a tool when there is a failure of equivalence, because as I said, the tool is not complete. It is possible that the programs are actually equivalent, but our tool just couldn't find the equivalence proof. But sometimes we found that the bug was not in our tool, or the incompleteness was not in our tool, but there was actually a bug in the programs that we were testing. Except the GCC bug that is shown on the slide, all other bugs were previously unknown and were fixed immediately upon reporting by us. Some of these bugs were found by comparing implementations of the same function, for example, strchr, across different library implementations. For example, we would compare glibc with klibc and so on. Different people optimize differently, they write their code differently, and so on. And it turns out that some of these different implementations, as a result, are different. And when two implementations are different, as reported by our equivalence checker, then we basically check what is what is the reason that they are different, and sometimes we find a bug. I want to point out that these kind of bugs that we found were always very, very subtle. And the reason for that is because we are actually not searching for a bug. We are not searching for a known pattern of a bug. We don't even know what kind of bugs can exist. We are searching for a correctness proof. And when a proof fails, then we start debugging and we find, oh, and it takes us some time to figure out, oh, okay, this is the reason why they are inequivalent. And so the bugs are usually very, very surprising, even for the people who are running the tool or are developing the tool. Here is an example of a bug report where we mention the library and the example input which triggers the bug. For example, this report says, I'm writing to report a bug. Here is an example. And this bug was found in the strchr function in the klibc library, which ships with the Linux kernel. Now, sometimes, and these are the kind of responses that we will get. People will either fix the bug themselves, or they will thank us for a submitted patch. This is an example bug that shows the kind of mistakes that were caught by the equivalence checker. These mistakes were identified by comparing the equivalence of two library implementations of the same function across different libraries. Here is the function strrchr, and it deviates from its specification if the character being searched is null. So if you call strrchr with the null character, then the implementation is incorrect. Now, many testing methods will not even try a null character, and that's probably why this implementation kind of slipped through for many years. And this is the patch. Instead of using a while, you start using a for, and you add a break statement in the middle, and that's what they did. And here's an example reaction. For example, we reported a bug in the swab function of the netbsd library, and the bug author says that the previous optimization was incorrectly tested for over 2 decades and broken for years. Among other things, I hope these results convince you about the value of formal verification and the inadequacy of testing. To conclude, I hope we all agree that there is significant scope of improvement in compilers. And given the recent advances, a super optimization or AI-based compilation is perhaps around the corner. In future work, I think there is lots of work to be done in training the neural network to learn optimization patterns within a compiler, and there are multiple directions that can be taken. And there's lots of work to be done on the equivalence checker front as well. These are the references I'm using for this material presented in the talk. Some of these papers are in the public domain, not necessarily from our group. The equivalence checking work has been through multiple PhD theses in our group, and they're available as shown on the website. Thank you.
Thank you. We are ahead of time, so we have
Correct.
Okay, and go from that part, right? Please introduce yourself and then ask the question.
Hello, I'm Prajwal. I'm still an undergrad student, so please, I do apologize if I say something wrong. But I mean, obviously, we saw the bug reports, and it's clear that it's catching errors that people will think of or didn't test formally for it. But like we're talking about compilers here, and no matter what code you write, it's brought down to a very definitive system, right? Where it's predictable system, it's a predictable system. So why haven't formal methods of verification not caught these errors? Do you think it's because of the testing methods that were used to verify these programs, or what is it that the LLM that you're using is catching all these bug reports that the formal methods could not? And is there a way that we don't let this happen again?
I just want to clarify. Maybe I don't understand the question. So our tool is a formal verification tool, right? The translation validator is a formal verification tool, and all the methods that have been used to test these libraries, pretty much all the code that's written today, is usually not formal verification. They use testing.
Okay, and then what I meant to ask was like, what, you can emulate these outputs or whatever it is into a very
May I request you to
yeah, I'll get it now.
make it offline and then give it back? Okay. Over here. I'll come to you after that. Please make sure that you're brief when you're asking your question.
Sure. So thank you for the excellent talk. I'm Sujit from Bangalore. My question is about the super optimizer loop, and I'm concerned about the gap that is left in the where we are not able to prove the equivalence. How much effort or how much compute is required to bridge that gap? Because that will decide the final success of this methodology. Even if it is 98% correct.
That's great. Yeah.
No.
That's a great question. Thank you for that question. So let me just repeat the question just so that everybody understands. So the question is that I already said that an equivalence checker cannot be both sound and complete. It needs to be sound for the compiler to be correct, but it may not be complete, which means sometimes the optimization was correct, but the equivalence checker just couldn't find the proof. And because of that, we miss on the optimizations. And is that a fundamental weakness that is kind of going to cause the super optimizer architecture to fail maybe in the future? Well, I think what is our competition? The competition are current compilers. And as long as the equivalence checker can do whatever, can check and prove the transformations that are generated by the current compilers, we have already made progress. Of course, the problem can never be solved completely. Compilation itself is an undecidable problem. And so there is no hope of solving the problem in its completest form. But if you are making progress, that's good enough. And I definitely think that writing a translation validator is is orders of magnitude easier than writing a compiler. For example, the equivalence checker that I presented today is an effort of around, let's say, 20, 30 man years, person years. Whereas a compiler like GCC, which we are testing against our equivalence checker, is thousands or hundreds of thousands of man years. So definitely this is this is an easier way of doing things.
Hi, so I'm Ravi. I had one question. So the equivalence checker, is this ESBMC?
Is this?
ESBMC? Or like ESBMC, so CBMC, ESBMC, these are the tools?
No, this is our own equivalence
Your
checker.
own equivalence.
This is completely our own equivalence checker.
The second question is like, so you're already in the undecidable territory. So you're talking about syntactic equivalence. Can we go to semantic equivalence of two programs?
No, this is not syntactic equivalence. We are doing semantic equivalence.
So you're doing semantic.
We are doing semantic equivalence.
Okay, then I know. Thank you.
Sure.
So I think partially my question is asked by Sujit and Ravindra. But I want my question is, how do you give that specification to super optimization? I mean, what is the specification again? Secondly, since the equivalent checker, I think this question is asked by Sujit. It has to be sound and complete. What is it if it is not complete? In your case, it is not complete. Are we going to not optimize fully, or what is it? effect?
Yeah. So the first question is, what is the specification to the super optimizer? The specification is just like the source code, right? So you just given the source code.
Okay.
So yeah, but I think I understand your question a little better now. So basically, the idea is I haven't gone into the full details of how the super optimizer is architected and things like that. It's available in the literature. Just for the paucity of time, I couldn't. But basically, we think of it as a pattern replacement matching thing. So think of it like people optimizations. So if you're aware of people optimizations, you have a pattern and you have a replacement. But this time, these are not like small peoples. These are large peoples that can contain loops and things like that. So we think of this. So we basically organize this as a people optimizer, and we'll have a super optimizer that learns these people optimizations over time, and then we organize these people optimizations as a table, index table. And then when you want to optimize something, then you basically query this people table and then kind of optimize it using Windows. And then we have an algorithm that kind of stitches them together using dynamic programming. So that's basically the overall mechanism. The second question is about completeness. As I said, I mean, we just need to be better than current compilers. Our current compilers are also not perfect. So
No, my question is, what is the effect of it? We don't get optimized.
we don't get best possible code. Yes.
Great talk, Saurabh. Thank you very much.
Thank you, sir.
So the question that I have is the equivalence checking that you're doing. Is it intra-procedural? Does it account for procedure calls in between? Can you take effect of compositions of procedures?
Yes. Okay. Great question. Can certainly deal with procedure calls and all that. Inlining is something that is only supported partially right now, but I don't think it's a major. I mean, it's not a conceptual issue. It's more like an implementation issue. We can easily support inlining.
One last question over there. Time. Hi, I'm Prakash from Remo. Thanks a lot for the talk. It's very interesting. So
Thank you.
my question is more like there's a lot of great work in like vectorizing compilers and scalar compilers. Have you ever thought of ML or AI sort of compilers where they're actually compiling for like the GPUs or ML accelerators? But a lot of things are about numerics, quantization, and other things where you may want to like
Sure.
localize things where like numerics changes. Yeah.
Absolutely, absolutely. Yeah, I mean, so AI compilers are very active today. Have we thought about it? Yes. Have we done something about it? Not yet. We are. I mean, so one of the big applications of our equivalence checker. I mean, it's basically like this, right? So we have a large vision that we want to kind of get to the super optimizer, but we need to have milestones in the middle and kind of find applications, the most important application for what we have right now, so that we have some user base and we have some resources to kind of take this forward and things like that. Our current most fit for the kind of thing that we have done so far is basically safety critical sectors. And I don't think that the AI compilers are terribly concerned about correctness at this point so much. But if you are, I'm very happy to talk to you, and yeah, we would love to support it.
Maybe one last question from Arvind there.
I had one false false negatives. So what classes of programs are actually harder to verify within the restrictions that you have?
Okay, very good question. If you look at my future work slide, uh, question is what categories of optimizations are harder to verify when I talk about false negatives. Uh, if you look at the last bullet here, support non-bisimilar transformations like loop fusion, polyhedral transformations. So the mechanism for equivalence proofs that I showed you was through a lockstep correlation, where I expect that one lockstep of one program is equivalent to some locksteps of the other program. And this mechanism is works only for transformations that are, the technical term is bisimilar or lockstep preserving. And most transformations that a compiler does, like all the loops with peeling, unrolling, vectorization, are, are bisimilar. But there are these transformations like polyhedral transformations and fusion and things like that, which are non-bisimilar and they are harder to do. And this is something that we have started on, but I think it's a long journey ahead to kind of do these kind of things. Thank you.
Let's thank Saurav once again. Thank you, Saurav.
Thank you for having me.
We'll move on to the next presentation in this session. Formal verification approach to safeguard. Controller based particularly safe. That was slightly bad.
Yeah.
This is the pointer,
Okay.
the button on top, next slide, and the previous slide.
Okay.
So, okay, I will not focus on the, only focus on the slides, not on the remote work. Yeah, it's working. Mm. Yeah,
Okay.
thank you.
Good morning. Myself, Ganesha. I'm from Samsung Research, Bangalore. Uh, this is my part of PhD work. Along with me, Professor Sujit is also here with me. The topic of our talk is a formal verification approach to safeguard controller variables from single event upset. So I will give you a brief introduction about what is a single event upset, how it is being handled at present, and I will explain with a motivating example what it is and few terms and concepts and what approach we are following it to solve this problem, and I'll conclude with some experimental results. Now, what is single event upset? The de facto way of deploying control system is through computing chips. And these algorithms which are running on the controllers, these are running on the controllers or system on chip. When sometimes these computing component need to function in harsh environmental conditions. During this time, when these are working in harsh environmental condition, a phenomenon called single event upset. It is rare and random. When this single event upset happens, a bit in the chip would flip its value. Sometimes it is fall off track, or sometimes it is resulting in catastrophic failures in safety critical systems. Now, what is hardening? Currently, common technique used in the industry prevent this single event upset is called hardening. You can imagine it as a kind of a silicon coating. So, what is the use of hardening? Hardening will withstand the causes of single event upset. But the problem is it is costlier. So, what is our approach? We will not harden entire thing. We will propose a technique which will do a selective hardening. Uh, our approach is explained in the figure. Like, for example, we have a program. The program analysis will happen, and we will identify the critical part of the program. And we will instruct the compiler what has to be reside in the hardened part and what has to be reside in the non-hardened part. So for this, we will define a term called conditional relevance of a variable. I will explain what is that conditional relevance of a program. Suppose we have a program, we will divide the program into two categories. One is which is relevant and one which is not relevant. The relevant part has to be kept in the hardened and non-relevant, as I already told. There are some techniques to identify this thing. For example, static analysis, especially a program slicing. If you give a program along with a program location of interest and a variable, it will give a part of the program that is called a program slice. There are different techniques in the program slicing, like it can be a forward, it can be backward, static, or dynamic. But we know identification of actual set of this conditional relevance variable is an undecidable problem. So static analysis gives, program slicing will gives a sound results, but there is a loose upper bound on the conditional relevance of a variable. So we use a combination of formal verification and static analysis. In case of formal verification, we will use software model checking. I will explain how we are going to use that. And the bounds, what is depicted here, this is like, say, the outermost square, it is a total number of variables. The innermost circle tells actually that is the actual set of variables. Right now, the green circle shows like has some false positives or something that is a identified CRVs, we are trying to just improvise it. What is our contribution? Our contribution is like we formally define what is conditional relevance of a variable, and we use the combination of program slicing and software model checking to identify conditional relevance of a variable. And this we have done some experimental result and prove that actually indeed there exists some conditional relevance of a variables. This is one of the example where we can uh, I will explain what is a conditional relevance of a variable. There are let us discuss about three types of variables. One is relevant variable, conditional relevant variable, and um, conditionally irrelevant variable. What is a relevant variable? A relevant variable means there is some dependency while computing some output operation. Conditionally relevance of a variable is like based on the condition whether this variable is relevant or not. And opposite of this, like non-conditional relevance is variable is relevant, but based on that condition it is not relevant. So in this particular example code, we have a outermost while loop which runs iterates for 7 times, and we have two nested if statements. Suppose there is a safety condition imposed on this controller structure kind of a code. For example, the safety condition is like output less than or equal to 10. Is there any way to violate this safety condition? Yes, you just think about the let's see, output is equal to 4 that we have initialized, and suppose x greater than 10 is false for all the iterations. Then outermost while loop runs for 7 times. We know the initial value of output is 4. Then always it comes to the else part where output is equal to output plus 1. It will always go there and it will compute the value. Now the value initial it is 4, 7 times it iterated, the value is 11. So it violated the safety condition output less than or equal to 10. So what is the interesting fact here is like when it violated the safety condition, variable y is irrelevant. You can see in the next second if statement y is equal to 1 that has not been used for computation of output. Actually, y is dependent on y, but whenever it is violating the safety condition, then the variable y is not relevant. Such variables we can identify, and we no need to put them in the hardened region of the silicon. The same thing has been explained. What about the safety condition when it is being violated, and what is the irrelevant variable here? We have defined some concepts here. What is safety condition and what is conditional relevance of a variable? Safety condition is like some condition imposed on the control system to satisfy. For example, I will explain it through some examples. This is a normal controller kind of feedback, which is consisting of a feedback loop. We have a controller, we have a plant, and from the plant some operation is being computed, and some values is being adjusted before it is sending to the controller, and controller in turn send to the plant. This is a typical closed loop control structure. When we see it as a program, it will look like a while loop structure. Some of the computation will be always happening. It is always a running application. Like for example, while one do some computation. This is also similar kind of a thing. You have a initialization point, then always a running condition. Some inputs, that inputs may be some sensor inputs or something. We will do some computation, and then output. That output will be written back to the plant or something. This is one of the example for safety condition. Right now, the safety condition has been written based on the domain knowledge of system. For example, one example is like, for example, output less than or equal to 10 for a period of 5 milliseconds. how to translate this? That is exactly this formula tells. For example, if one upset happens in between these 5 cycles, then that can be tolerated. It will be like a low pass filter. Else, if the safety condition will be violated only if all the control cycles it violates. Now, coming to the conditional relevance of a variable, what is our analogy? Let us assume we have a system. How we have a system with some knobs. You can think the system as a program and knob as a variables. So let us take K1 is my variable of interest. I want to identify it as a what conditional relevant or non-relevant. So the definition is like keep all other variables to a certain fixed state. For example, K2, K3, K4, 5, and tune the knob of K1 such a way that the system goes to safe ones and unsafe ones. Then only we will call it as a conditionally relevant variable. These I have already explained in my previous slides. What is a relevant variable is like there is a dependency between x is being used for the computation of y. So, conditionally irrelevant also I have discussed. This is a formal definition of conditionally relevant variable. This just tells, like, suppose I have a program P and I have a safety property phi. So how I can define it as like in the program P, uh, it should satisfy the safety property, and in the P dash it should violate. And the second clause is its reverse version. In both the cases, we will call it as a conditionally relevant variable. So in case of first case, the safety condition violate, but in second case, it may not happen always, but in case it happens, it is a program bug. Because of SEU, it will mask the bug also. And what is our approach is like, we have a program and we have a safety condition and we have a program of our interest. We will instrument a program in such a way that we will simulate the single event upset and simulated and the original code, both we will give it to the model checker and we will check whether this variable is conditionally relevant or not. This is the simulation of the single event upset. Before every use of a particular variable, we will simulate, and we will do it for only once because it is a single event upset. This is the algorithm. I'll just explain because of the time. This just tells like S and S dash are the two sequence. The above P program is a typical while loop kind of a structure. That O dot append O is like, for example, how to embed the safety condition. For example, output less than or equal to 10 for a period of this many milliseconds or something. Then we will have two versions of the program, and one which will satisfy and one which will violate. That how we will check is like, we have a phi and phi dash, that formula we will give it to the model checker and we will check whether such path exists or something. Do we have the values of the variables, whether it will satisfy and whether it will violate. If we have two such variable values, we will conclude it as a conditionally relevant. This is a code part of it. Just to, we have used a static thing to simulate, and we will use a XOR operation for the bit masking to simulate a single event upset. This is the overall approach. We have a C code. We will use a pharmacy. That is, initially we will do the slicing with the existing technique, and once we get the sliced code, we will instrument it to form two versions of the program. One which has a simulated version of single event upset. We will give it to the model checker, and we will check the property for satisfaction. And we have run some experiments. We have conducted our experiments in some. And this is the setup. The tools what we have used is a pharmacy and CBMC model checker we have used. And slicing is based on the safety property only. Then after slicing, we have instrumented it and then verified through CBMC. The evaluation criteria and this we have actually compared our approach with the slicing over our approach. How much percentage is the efficiency? This is the few simple programs what we have tried. This is the initial version. After this, we have tried some 39 controller programs, and we have found out the better results, means indeed there will be some extra conditional relevant variables which static slicing failed to identify. Yeah, to conclude, actually, we have introduced a concept of conditional relevance of a variable, and we have used static analysis and formal verification, and we have used that in our algorithm, and it showed like CRVs are the strict subset of the relevant variables, and this will in turn help us to harden only a part of the silicon. Thereby, we can achieve the chip manufacturing cost. Thank you.
Why didn't you use condition slicing approach?
Thank you for the question, sir. Actually, we have gone through the conditioned slicing. Almost that overlaps our approach. But what we can say is like that doesn't deal with the single event upset property violation and satisfaction. I can say it is an application of conditioned slicing.
Right, but your CDMC is also not complete, right? So the CDMC also it may not detect because it is incomplete. Have you used full unrolling in your case? Because loop unrolling
Yes.
may lead to incomplete results. Right? CDMC.
Yeah, we it is in the initial stage. We did not explore all the things. Maybe we will consider this point. Even the inter-procedural analysis we had to verify.
Okay.
Basic things we have.
Yeah. Hey, good talk. This Krishna Nadiyodu.
Hi, sir.
Is your technique both sound and compute? Can you give any connection?
It is sound of our experimental results or benchmarking with the this one. While
No, just the results. I'm saying your technique is it somewhere for these examples it may have been right, but is the technique sound and complete or sound or complete? Anyway,
because we are using it over and above the static slicing and existing formal verification, they are sound and complete. It is just an extension. No, sound and complete both will not happen. Static slicing is sound. There will be some false positives in case of static slicing. We just try to eliminate those false positives.
go ahead.
Yeah, Mr. Hussain. Interesting talk. We have the examples where you're saying you're checking fan speed like what design like that. So one of the things what's confusing me here is are you checking at a very high level which is like relevant to this or are you going to check at a slightly lower level? Fan speed seems to be something which is very close to the application time.
I maybe I did not understand the question.
Maybe I'll request you to take it offline because. Okay, let's try to see if you can squeeze two questions from here, and then I'll come to you.
So you mentioned that it would reduce the chip manufacturing cost. So does that just include the processor or also things like ECC memory?
The thing is like what is our we will instruct the compiler. For example, we for what compiler will uh, instruct where to load the variables. For example, we will be having the registers, we will be having the cache line or memory regions from, for example, certain M1 to M10 memory locations. Few of the things have been already hardened. We are not going into the hardware part of it. We will just instruct the compiler where this variable can be loaded.
Okay, one last and three questions.
Hi,
Nice.
nice talk. Very nice practical motivation as well. I'm
Thank you.
reminded a lot of some of the other literature on things like non-interference and security properties and so on. Wonder if you even thought of exploring that area apart from this kind of hardening that you're talking about.
No, no, sir. I am not aware of that. Maybe I will check those.
Okay, thank you. That's once again thank Ganesha for an interesting talk.
Thank you.
TV is present.
Wait. It's not on. You can turn it on with this. How? Yeah. So this is the pointer, and this is the next slide and the previous slide. Okay. What's with this? The mic is on. Yes. Okay. I hope you can hear me, everyone. A very good Sunday to talk about mathematics and formal verification, and this is coming from the deep learning side of things. So before I start, how many of you use PyTorch or have used PyTorch? That's great. I mean, pretty good. How many of you have used PyTorch and faced some issues like index out of bounds, assertion errors, sometimes out of memories, when you're fine tuning training or doing some inference? Quite common, right? Last night I checked, I saw over 1300 these kind of issues which are happening in the backend, okay, in PyTorch. So there's a huge technical debt, right? Where how are we formally verifying what optimizations go in for this, from the deep learning side of things? Deep learning for GPUs is a little bit complicated, and today I'm going to talk about specifically PyTorch related stuff, even going to lower level such as Triton, PTX, and down the line. So probably the motivation is raising your hands up, right? You already know what the motivation is going to be about. Now, the thing is, for PyTorch, actually, there are a couple of stuff, right? So we have something called as a Dynamo backend, which is the backend agnostic backend. And from Dynamo, you can actually use something called as an inductor, which does just in time for your specific hardwares, right? You are going to have something for C++ OpenMP backend, that is for x86 CPUs. You are going to have something for Triton, right? Which basically boils down to your GPUs and so on. So once you have written a particular piece of code for PyTorch, right? Your model, how are you verifying whether the model performance is good, whether the model is formally correct or not, right? So inductor is a customized IR which is either backed by the C++ backend or the Triton backend. And if we want to do formal verification for it, it is actually done with the help of this particular toolkit. So what it does is there are a couple of basic blocks inside it. One is the kernel extractor, which every PyTorch code that you write, whether it be a simple addition, right, define addition x plus y, or a particular softmax, right, basically boils down to a kind of like an extern C for C++ OpenMP packet, or a kind of like a Triton-based code, right, for your GPUs. So we are only interested in the kernel part because the kernels are exactly where your formal verification should take place, actually. So we want to ensure that our code follows the semantics of whatever our hardware requires it to be, whether it be SIMD processing, word processing, lane processing, whatever it is. Then we have something called as a customized alive, right? Where we boil down, for the GPU side, we get PTX. And from PTX, we do a boil down to something called as NVVM IR, which is NVIDIA's equivalent of LLVM IR. And we provide custom support for Alive2, which is a formal verification toolkit. And you will see that after a while, to provide both transformation and translation validation. And then the next part is about program synthesis, which I think Professor Saurabh Bansal has already given a quite good talk about. And we are going to see in the case of GPUs how it happens. So let's see about how the PyTorch compiler works. So you have something called as a conf2d, right? You lower it with ATON or primitive IR, and then you are going to have something called as a kind of like a segregation based upon your JIT packets, right? So all these backends are there from PyTorch. So if I go to the next slide, so essentially now we have this. So the first step is the kernel extraction. So once we do that, we can actually get something like the extern C that we're talking about, right? So once this is the C++ backend, that is the CPU backend that we have, okay? And we are only interested in this part, actually, this kernel part, right?
How do we ensure that the simple addition gets boiled down to this? And how do we ensure that this is formally correct? This is for the Triton part. So in Triton, we see a softmax kernel, and that is a Triton JIT code, right? We want to verify, we want to also extract the kernel from this, and we want to actually formally verify this as well. This is the ensuing PTX code, which is there, right, from that particular Triton kernel. And if we take a look at this, this PTX is happening at a very low level, right, which is the parallel thread execution library of NVIDIA. And inside that, if we can directly not include PTX because formal verification of these kind of things doesn't happen at that much of a low level. So we have a tool called as Alive that we are going to use, but we are going to use it for a more upper level stuff, which is LLVM IR, because that is what it understands. And so yeah, this is the kernel extraction, how we can get with the kernel extraction with Clang. This is the small part of it. This is the part which is very interesting and I want to talk about. A part of the thing is where PTX cannot be directly used, and you have to convert to an equivalent LLVM IR format which Live understands. So how do we do that? Because we are coming from a low-level dialect to a very high-level dialect. And I don't want to lose out on CFG, DFG. That means I don't want to lose out on context. I do not want to lose out on data, right? How it is flowing through the graph. How do we do that? So it is actually a kind of very novel neural fuzzing framework, a transformer framework, if you may. But that framework is actually based on a couple of things. So that transformer framework has categorization of PTX to be mapped to an equivalent NVVM IR. This is actually the demo which I'm going to show you after a while. But anyways, so it maps to your PTX to an NVVM IR, but PTX has so many modifications, right? It has so many modifiers, different kind of memory stuff and so on, right? How would you map to an equivalent lossless translation to an NVVM IR, which is actually at a level higher, without losing semantic equivalence? That's a very question which actually tricked me. And one of the ways you can do that is to actually have a policy gradient and allow an agent to choose a correct modifier through mutations, multiple mutations. And you rank those mutations in a way that most favorable mutations are chosen. So for example, if I'm having, let's say I'm a CUDA programmer, right? And I've written a PyTorch kernel with inline ASM volatile PTX, right? And let's say I do not know the intricacies of what a tensor memory is or what global or shared memory is. Okay. For me, when I write the kernel, it is just going to be a generic memory. Now, from the NVVM IR scope, I need to convert that to, if I'm doing an MMA operation, I need to convert that to an equivalent, generic to some tensor memory kind of stuff. Now, who is going to take care of that? Who is going to take care that I do not want to lose my data flow. I do not want to lose my context flow as well. So this fuzzer has kind of like a transformer architecture, which also actually maintains a kind of like a policy gradient, which rewards mutations which maintain the control flow, so that we get semantic equivalence. And I don't know if I will be able to present that, but anyways, yeah, this is the next part of the crux of the talk actually, formal verification. And you will see this giant, I would say, dragon with the knob everywhere, right? So formal verification for GPUs is a little bit complicated. You have to adhere for memory consistency. You have to adhere for warping. You have to adhere for different kind of tensor code semantics, right? You have to adhere for lots of different things. How will you formally validate a particular PyTorch instruction? Let's take a simple example. Everyone knows softmax, right? E to the power x by summation of e to the power x, right? Can that be ever 0 or less than 0? Even if you take any kind of Lagrangian or Taylor series expansion, can that be ever 0? No, right? So what if your PyTorch code is in your loop of your training loop, sometimes you get minus INF, where that is coming from? Let's say you have a transformer code, right? You are going to have attentions and you are going to have a final feed forward, and then after that you are going to have a softmax. So let's say in the softmax penultimate layer, you are getting inf, minus inf, and so on. I don't know, PyTorch will say, boss, I don't know your code. Okay. Fine. So who will validate that? So there is something called as a translation and a transformation validation. Okay. So translation validation means that when this code gets boiled down to my PTX for my GPUs, right? I want to ensure the same memory consistency model which is there inside PTX. Atomic operations should not be interrupted at any point of time. Operations which do concurrent read IOs from weak memory operations, which are like load, store, asynchronous stuff, which happens in the case of flash attention to your SRAM and all this kind of stuff. So these should not be overlapping with each other. Strong memory operations in the memory consistency model should always be guarded, right? They are generally called as fence operations in memory. We'll take a use case of transformer with flash attention after a while, actually. So once we do this, we can actually run a kind of like a proprietary as well as very customized set of passes, including NVGPU as well as whatever LLVM supports, right? All the standardization passes, and you have to ensure that your actual code that you generated using NVVM IR through your previous step, which is the further step, is actually semantically as well as CFG wise, it is equivalent and formally verifiable with that pass. That means that pass actually goes through and you get a correct equivalent representation. Very hard topic, actually. I'm explaining it in this way. But how will you formally validate MMAs, matrix multiplications? Matrix multiplication is the easiest as well as the toughest problem in the industry, which is driving the arms race for GPUs, right? When Strassen first developed the 2.8 complexity of dynamic programming based algorithm, there was an algorithm designed for MMV, matrix multiplication verification, which used something called as a very simple concept. So you take a dot b, right, and you have a value equal to c. Okay. Now you multiply both sides with r. Some people call that r as a coding sample, right? Error checking codes. But let's say I like to call it as a zero. R is actually a 0, 1 kind of like a vector array, which n is the dimension of your matrix. So if you do a dot b r minus c r, this should be equal to 0 to formally validate your MMV. Okay, and for different values of r, you will get a probabilistic distribution, which you can analyze using some Bayes theorem kind of stuff. This famous algorithm is known as the Frivar's algorithm, which came way back in 1979. And why it is important in today's context, because people like William, people like Hoshi, they always said that, boss, I can do better MMAs, right? Faster MMAs. Speed up your verification process. How you verify faster MMAs? One way is to reduce the amount of non-deterministic part of your MMAs to a more deterministic part. That means you split your matrix into subdivisions, maintaining the rank coherency and so on. Okay, so I don't want to go into the mathematical details of all of that, but MMAs formally verifying that is very, very complicated actually. So luckily for PyTorch and these deep learning kernels, they have something called as sparse tensors. So there are some axioms related to sparse tensors, which limits the exploration capabilities or the non-deterministic part of this particular verification strategy. And this is what it is. So you want to ensure memory consistency, you want to ensure proper MMAs, you want to ensure no permutation inside your lanes, you want to ensure there is no side effects, which is also guarded by NVPTX and NVVM dialects, right? Yeah, this is the demo for the other part. If you're interested, we can take a look. Next part is the super optimization. Since there has been a great session on super optimization, I will keep it short as to what we are doing. And this is the last part. So super optimization is a very interesting topic, right? And there has been a lot of use case on using deep learning and all of these stuffs. Our use case depends upon cutting your piece of code, right? Your alive to formally verified IR, right? Into blocks or chunks. These chunks are guarded by your memory model. So let's say you have a basic block which is guarded by your fencing, right? Your fence serves as your blocks. So you cut your code into smaller parts, and each of these basic blocks, wherever there is a NPC like intra-warp dependency or a kind of like a branch predicate divergence, You can apply small, minute optimizations in each of them to make your code even more optimal, smaller, reduce the number of cycles it takes on your GPU to run, right? So we take inspirations from papers like Super, which is a project from Google, right? And that's it actually. So just a small use case from transformers. This is the last slide actually. How many of you know flash attention? What flash attention does? Excellent. It is a very genuine and a good problem because it uses something called as online softmax or a saved softmax, where instead of doing e to the power x summation of x by e, a summation of e to the power x in the denominator, you do something in a recursive manner so that your IO cycles inside your SRAM gets reduced, and you do that in one step. How this happens is because, but how are you going to formally validate that? How are you going to formally validate a recursive loop of MMAs which is exponential, right? E to the power x. So to formally validate that, there are a couple of ways which we have been trying to maintain semantics with the GPU hardware, like taking hyperbolic expansions, restricting them to certain bounds, right? Performing some LU decomposition of the matrices, and all this kind of stuff. And you will ask me, why are we doing all this when if we get some errors at the PyTorch level, right? So this is the back loop, and this is the future work, right? But there is a back loop on this as well. So all of this is being done, it is at a lower level. I want PyTorch also to be ensured about that. So there is a preliminary pass at the top level of PyTorch, which ensures under your same group theory, same guards, your commutativity, associativity, rank ordering, preservation of your tensor spaces are actually made consistent, even before it goes down the line. Okay, so that at the PyTorch level, you will not get this kind of stuff. This tool actually produced a lot of bugs, quite a lot of bugs which we are taking up with maintainers and all, and we plan to enhance this further. So if you're working on Triton or especially this kind of deep learning kernels, please feel free to talk about. And I'm open to questions, and I hope I try to do justice to this difficult talk. Yeah, thank you.
Hi, this is Ravi. Actually, also one question. There was matrix multiplication. Whether, as far as matrix multiplication here is concerned, whether it will go row column-wise or row wise. What is the difference of these two methods? Can you explain, please?
So yeah, so without going into the mathematical details, there are two components which you rightly asked. One is the row measure format, one is the column measure format. So when we do MMAs, right? So what do we look for in MMAs? So I'm assuming your question is on verification of the MMAs, if I'm not wrong, right? Yeah. So in feed-forward neural networks, or any kind of neural networks, there is always going to be an MMA component. Basically, these are row measured. If you have basically, if you have a large sparse tensor or a sparse matrix, it will basically be a kind of like a row measure format. The reason why it is chosen as a row measure format is because let's assume you have a 3x3 matrix, square matrix, right? If it is sparse, then for let's say if there are n elements which are non-zero, then there are certain axioms which state that if your runtime complexity is n to the power x, then there must be at most x by 2 elements which are non-zero, and the rest all of them are zero. So this gives a very peculiar thing, is that you can split your matrix into lower diagonal and upper diagonal matrices. There's a bunch of mathematical theories on it, matrix optimizations. So we can use that, and deep learning algorithms actually use it to cache something inside your software RAM, cache something inside your L1 cache, so that you do not have to do MMAs fully for the entire matrix. That's it. I hope it answers your question.
So can you explain how would you handle it for torch level dialects or when you know some presentation? How would you rerun your verifications if it is already over to site?
Yeah, great question. Great question. This is one of the future part of the work that is written over here, which is ID and Torch MLIR, which are downstream projects for doing 4th gen from optimized torch back, like I meaning the inductor backend, if you may, back to MLIR, right? Particularly on the TOSA and the lineage, if I'm not wrong. So there are MLIR stuff which is there, like there is a experimental MLIR TV which does this, but they only do something on the path structure of it. If you want to formally validate a code gen which has produced MLIR from torch MLIR or some other part, then you actually have to ensure some kind of pass inside your formal verification, which ensures that the expanded MMA or in computation. That's basically it across any kind of kernels, right? So if you can do that, and if you validate those looping kernels at each and every block, cache it somewhere, you have a formal verifier which is there. So conceptually, we are extending that to Torch MLIR and IDE backends as well. But that's a great question to ask, and I hope I answered it. Yeah.
Thank you. If not, let's conclude this session. Let's once again thank all the speakers.
So, snacks are served to the right. We have to all assemble here at 11:30. Please be here a few minutes before 11:30. And to my left on the job board, we have a few new job postings from Waymo and IIT Hyderabad Research Group. So please take note of it. Thanks.
and then use the analysis result generated statically at the runtime to perform more optimizations. The optimization which we have been working on is regarding object allocation in Java. So by default, objects in Java are allocated on heap. There is an optimization called as stack allocation, which tries to optimize. So if objects are on heap, there will be indirections while accessing the object as well as its field. So to improve this situation, there is an optimization called as stack allocation, which allocates the object on the stack frame of its allocating method at the runtime. Obviously, we can't allocate all the objects. So to find which set of objects we can allocate on the stack frame, there is an analysis called as scape analysis. So using the idea of stage analysis, we perform the scape analysis statically, the precise analysis, which will be context, flow, and field sensitive. And then use the statically generated results at the runtime to optimistically allocate the objects on the stack frame at the runtime. Notice the word optimistic. Since there are dynamism offered by the language as well as the runtime, such as hot code replacement or dynamic class loading, which can affect your static analysis results. So to maintain functional correctness, we use the idea of heapifications. So heapification basically tells that when you are using your static analysis results, if at runtime the static analysis result doesn't correspond to your runtime environment, in that case, we do something called as heapification. We basically heapify those objects back on heap from stack if the runtime finds that object allocation was not correct. So let's say there was this O5 and O6, which using static analysis we allocated on the stack frame. And at runtime, we found that, okay, these are wrong stack allocation. We heapify the object back on the stack, back on the heap. And to make this heapification checks efficient, we use some idea of stack ordering, like how can we order objects on the stack frame such that these heapification checks are efficient. So overall, this was one of the first approach which soundly and efficiently used static analysis result or the offline result in the JIT compiler. So if you go over some of the recent work which has been done in this domain, you will find that most of the works are trying to use the static analysis result to perform optimizations in the JIT compiler. So they are somehow trying to offload or do everything statically and then depend on that static analysis result at the runtime. But we all know that there are things where a JIT compiler is also good at, such as doing profile-based optimization. So profile-based speculative optimizations. So there are profiling information that is maintained by the JIT compiler, such as like how much the invocation count or the loop iteration count. There are type profiles that is maintained for like typecast statements or polymorphic call sites. There are branching information available. So these are information maintained by the VM at the runtime. There are dynamic class hierarchy tables maintained by the runtime, which tells at any given point of the time what are the loaded subclasses that are present for a particular class. There is inlining table which is present at runtime, which tells at a particular call site which set of which set of methods got inlined at that particular call site. So using this profile information, JIT does perform some standard speculative optimizations. Why I say standard? Because even to perform speculative optimization, you need some kind of interprocedural information, which JIT doesn't have budget to perform. There is another reason why JIT doesn't perform more aggressive optimization is the fallback options. When you are using speculative optimization, you need to have a fallback, which means when your speculation goes wrong, what should you do? And in most of the scenarios and most of the optimization, the fallback is fallback to interpreter, which is just discard the binary generated by the JIT and fallback to interpreter, which is pretty conservative. So since we have an fallback option, which is the heapification mechanism, can we make the JIT compiler perform more speculative optimization backed by the static analysis? That's the overall idea of this work. The title is CosJIT, where we say we are combining static analysis and speculation for JIT compiler. The idea is we enrich the static analysis with the possibility of speculation at runtime. That's the first thing. And the second is we try to enable the JIT compiler to use those results to perform more optimization. So that's the idea. Huh. Yes. I think we need permissions and all. It's okay, I think. Yeah. Yes. So this is the idea where we try to have two things in our mechanism. Um, yes. So let's go over one by one few cases where we try to improve the existing static analysis the way it works. Let's consider this code example. At line 14, we have call to method bar, and now based on the receiver type at line 14, its corresponding bar method will get called. Now, if you notice in one of the bar methods in class C, we are making the parameter escape since it's being stored into some global or static field. In that, the existing analysis, while generating result for method foo, will take meet for both of the callees and then say that the object which was passed, which is x and which you see, which is O5, and its field is pointing to O7, which the existing static analysis will mark that as escaping. Now, at runtime, uh, there might be possibility that the class hierarchy table tells you that the class C is not loaded itself, which means that the reason why we were marking the objects as escaping is not even present. So we can actually mark those objects for stack allocation. Even if the class hierarchy table shows that the class was available, it might happen that most of the times at runtime, the profile data shows that the bar which was taken is from class V. So to encode this idea that this might happen at runtime, we try to add additional conditions to the static analysis results. We say that in this uh, we say that at this call site, if the type of the receiver is of type B, then this runtime can allocate O5 and O7 at runtime. That's what we encode. Uh, let's go to another condition. So first was method calls. Second is the way control flow is handled. Instead of marking it as escaping in a callee, let's say the object escapes in one of the branches. So similar to uh, earlier ways, the current static analysis will mark the object as escaping. But again, it might happen that at runtime, most number of the time the if branch is taken. So again, to encode this idea, we add extra conditions which tells that which set of branches makes the object doesn't escape. So this is the second condition. The third one is based on inlining based results. Let's consider this code example where we have a method bar, and let's say the object which is coming from the callers are not escaping. Now at line 13, we have a new object O13 which is being stored into parameters field, which makes the object escaping. Since it's being stored into parameters field, the scope of this object goes out of the bound. Now the existing analysis will again mark this object as escaping, but it might happen that this method gets inlined at a particular call site at runtime. So what is the state? The state is that we had a object which was being passed from the caller that is allocated on the stack, and then there is a method when then for method bar O13 is on heap pointed to by P3. Now at runtime, if this gets inline, which makes O13 local to the method foo, which means that O13 can now be allocated on the stack frame of method foo. So this way we can mark some of the callee objects also to be allocated on the caller's stack frame. So this is one more ways where we try to enrich the static analysis and to improve or to encode speculative optimization that might happen at runtime. Yeah, so we add extra conditions which says that uh, which says that uh, at line at BCI4, if this method gets inline, these are the set of objects that you can mark for stack allocation. Just to summarize, when we generate static analysis result, now we have some results for direct allocation, which doesn't depend on any values at the runtime. And then, apart from that, we have this set of conditional results, which depends on the runtime profile data. And now we give this statically generated result to the JIT compiler, which can make use of these results. On the JIT side, we have some algorithms which tries to make use of those profile informations as well as the static analysis cells. I will not go in detail of these algorithms. The idea is pretty straightforward. When we are trying to resolve polymorphic call side results, we need class hierarchy table, we need some of the profiling information. So what we check is, the first check is if the object is not marked for stack allocation by the existing ways. We check if the object is, yeah, so the first check is regarding class hierarchy, which you can find over here, which checks if the types specified in the static analysis result are superset of the types present in the class hierarchy table. If that is true, which means that we can go ahead and mark the object for stack allocation. If that is not true, we look into the profiling information available for those types, and we take a summation, and if we find that the type is greater than a particular speculation threshold, then we go ahead and mark it for stack allocation. Similarly, for branching information, we again try to get the profiling information, and we take the summation of the branches in which the object is not skipping. We take the summation for those branches, and if it is greater than certain speculation threshold, we mark it for stack allocation. So if you are wondering what is the speculation threshold, we try putting different speculation threshold values, and we found around 70% we are getting the maximum performance in terms of stack allocation and minimum vipifications. Similarly, for inlining based results, we try to get the inlining table which is available at the runtime, and then see if at a particular call site, if a particular method got inline, is there a static analysis result available for that method? If it is there, we try to mark all the objects that we marked statically for stack allocation as for stack allocation. Yes, so we did evaluate our work. Our static analysis implementation is done in the suit analysis framework. Our runtime is done in the Eclipse OpenGen VM. And we use all the newer decapos as well as the older decapo benchmarks, apart from SpecJVM benchmarks as well. The evaluation scheme has two schemes: the baseline scheme, which will use the existing JIT analysis, JIT-scape analysis, and CosJIT will use our analysis results. And we compute few of the things like how much is the enhancement in stack allocation, what is the impact on performance, what is the impact on garbage collection. Just to briefly give you some ideas, so we have two schemes present over here. We are measuring static count, which is basically the allocation, how many allocation sites we were able to mark it for stack allocation. We have dynamic counts, which means how many dynamic number of objects that were actually got stack allocated, and then how much memory on the stack we were able to get into. So these are some of the results for benchmarks. More results are there in our paper. If you see some of the benchmarks like GraphG, where you see static analysis, if you see our static count went from 12 to 109, and then similarly the dynamic count was pretty higher. And on an average, we were able to improve the stack allocation by 1.4 times, and even the stack bytes improved by 5.7 times. This means that this much of less heap allocation we did. Similarly, we tried to find out the contributions, how much is the contribution from all the different approaches. On x-axis, you will see different benchmarks. On y-axis, is the static count, basically, how many number of allocation sites that were marked for stack allocation. So yeah, so you can see that inlining had the best impact, but other ways also had some of the impacts. We did measure the performance improvement, and on an average, we were able to improve by 6.7 times for the performance. You can find more details about the performance and all in the paper. We did evaluate the garbage collection as well, as we are doing less allocation on heap. We expect garbage collection to cycles to reduce. You can see we did measure on different heap sizes. There is X, 2X, 3X, where X represents the minimum heap size required to run that particular benchmark. We see continuous less garbage collection cycles that were getting invoked. And on an average, the VC cycle reduced on the minimum heap size by 35%. We also measured overheads. What are the overheads which we are adding? So there are different information like how much is the static time, what was the size of the file which we are passing to the JIT compiler compared to the class file size, and then how much is the over improvement which we are getting compared to the overhead we are adding. So we found that most of the times the improvements were much higher compared to the overhead which we added, and some of the better improvement benchmarks are highlighted. So just to summarize, the takeaways from this work is that this work proposed an approach to combine the best part of statically performed AOT analysis and dynamically performed JIT analysis. We tried to enrich the static analysis with the possible runtime based speculative results. We added mechanism in the JIT compiler to incorporate conditional static analysis results. And this was again one of the first approach that strikes a balance between the static analysis and the JIT, harnessing best of the both worlds. You can find more details about this work in the paper which was published recently at UPSLA. Thank you.
Yeah, thanks for the print talk. I'm Feniji. I wanted to ask about the interaction with the GC. So, like Java has a generational garbage collector, and it depends on how many, like on the generation, how many cycles actually go through.
Yes.
So, when you do heapification, do you take that into account that which generation you want that thing to land in, like or that object to land in? Because that can cause, depending on the object's usage, can cause a performance issue.
So for now, we don't alter with the garbage collection, the way garbage collection is getting handled, since there are a lot of garbage collection that get invoked based on different heuristics. So we are not altering with the garbage collection the way garbage collection is getting invoked as of now. But yeah, there we have plans to like take advantage of how can we handle those scenarios.
Makes sense. Thank you.
Any other questions?
Yeah, so hey, thanks for the talk. So you said you noticed a 5 times increase in the stack usage, right? So can that do you see that causing an issue since stack size is limited, right? Like maybe even if it's 1 MB, if it's a recursive call or something, you have made it into a static. So is it more of a code problem that something which could have been static marked to be allocated on heap? Or since when we are all automatically doing this, automatically making heap allocations into those stack allocations, does that 5 times increase cause any situations for overthrow and so forth?
So to answer this question, so first I will tell you that on stack frame there are fixed location for each of the objects. So there are fixed slots for each of the objects for a particular method. So there is no overflow. So every time if it is possible, then object will be allocated. Second thing is since the object were earlier skipping, I didn't get your second part of your question. Like what do you mean by um,
I mean, if we are allocating something which was on key,
Mhm.
could have been a bigger chunk of memory that we would be requesting, right?
No, it's the object itself. It's the object size. So object will have some header, it will have some field. So that object itself we are allocating on stack now.
Just small objects.
Yeah.
Yes, yes.
Okay. In the interest of time,
So, thank you.
yeah. Thank you. So,
Slides on.
model an idea for take certain capital in mind. Nitish.
Is that funny?
Yes.
Let's go back. Let's flip it on. Really easy to. Up with this. Yeah, really easy.
We have 5 minutes left. You can just look up there. I will just point you 5 minutes.
Yes, yes. Thank you.
This stuff and you will control the slide with these 2 minutes.
Thank you. Is there a problem? Hello everyone. Am I audible? Hello. Yeah. Hello everyone. My name is Mitesh. I'm a PhD scholar at IIT Bombay. And I'll be talking about our work on static analysis of JavaScript programs. So this is our team. We have Anirudh, who is a BTech at IIT Bombay, Aniket, who is a BTech at IIT Delhi, and this is our small team which is working on this new framework that will enable static analysis of dynamic languages. That is our goal. So around over a year ago, we came up with this plan of creating an intermediate representation for JavaScript. And we had three key characteristics in mind when we were looking at this problem. We wanted something that was general purpose, something which you could extend to languages like Python and so on in the future. And it could support multiple backends, so it has to be an agnostic system. The next thing is it has to be an analyzable language. It needs to provide a sufficient level of abstraction for reasoning about dynamic languages in general, nothing too specific to JavaScript. And the third is it should be executable. We don't want to create yet another static analysis framework which integrates to IDE. I mean, it's not bad, but we wanted a executable runtime at the end. So this has been our goal, and we are at a stage where some parts of all these three goals have been met in around 1 year of development, and I'll be talking about our work here. So just to motivate the use case, where would someone, let's say, use such a framework? So Amazon published a project around 2 years ago. It's called LLRT. So it's a AWS Lambda project which came up. And the really interesting thing that we found in this project was the choice of the VM. It uses a VM called QuickJS. It consumes literally less than 1 megabyte of RAM, this VM, and it doesn't have a JIT. So this is really good. It has no cold startup time, and it is able to handle things like incoming store request, filter request reasonably well. But if you give it something more intensive, like real-time Monte Carlo simulation, it's not going to do well. So the reason, if we hypothesize the limitation, is each the time taken for each of these is sort of fixed. Each iteration takes a given amount of time, and if you run it in a VM like V8, Google's V8 or SpiderMonkey, you get the benefit of static analysis and optimized code which gets dynamically generated by the system.
So why is Amazon spending all this time and money? Like there must be a good reason, right? And there is. You can't use JIT everywhere. So it's known to have poor security. It's known to be unpredictable, and it's not really suitable for low latency workloads where throughput is the main requirement. So this was our plan. A year ago, we came up with, okay, let's start with the JavaScript 5 and see what we can reason about, what facts we can collect about the program, and how we can speed it up. So this is our pipeline in one year of development. So we have a front end, we have a middle end where the optimizations happen, and we have an instruction selection pass which integrates it with a real backend. And so let's start with the front end. So before we start, the first thing you look at is the source code. So this is a JavaScript for off loop, and what IR design really looks like is you start with a world where the user has written some code, and then there is your CPU or a virtual machine, and there's a bridge in between that these languages try to create. So the job of our framework is to come up with this middle block. And turns out it's really challenging. JavaScript is not a neat language to work with. So inside this 3 lines of JavaScript code, you end up with try-catch handlers, you end up with abstract operations, and you end up with different evaluation scopes. So it's not a simple language to work with. So that's what makes it a nice exercise. The idea is if you're able to manage all this, a lot of other languages will fit into place. And for our implementation, we decided to have a Lisp-like representation. So it's our expression format. You can look it up. It's been documented. It's being documented on GitHub. And so what this basically means is it doesn't distinguish between data and control. So it's a unified S expression based representation, and this allows us to make the task of serialization, deserialization, representation very, very simple. To just give a quick feel about what this framework does and how it makes things better. So let's have a small let's have a show of hands. How many people think this is going to print 12 as the output, and versus how many people think it's going to print 13? So is there anyone who thinks it's going to print 12? Okay. Is there anyone who thinks it's going to print 13? Okay, we have a few. So we have people. So the idea is an IR should make the task of what this is doing more explicit. So that's exactly what a compiler does. Take something that's sort of confusing and go through different stages, disambiguate things, and make it easy to reason about. Right. So this was our talk last year. So this has become my yearly progress report talk at ICT. So this was our first pass we developed last year. It's called JS3. So it's a three-address like representation at for JavaScript. And since then we have come a long way. So we have a binary format that we support now. So if we sort of extract this binary, it is this S expression mess. But so if we look at it from a high level, it's basically taking your JavaScript code and squishing it into this format. It's just a bunch of basic blocks. So at a high level, this is what it does. It creates a sort of a control flow, creates basic blocks, and then it introduces these special nodes. So these are something we call transitional nodes. So in this case, the yellow highlighted nodes are the nodes which the user didn't write. So we call these implicit bindings. So these are called implicit bindings. So these are the bindings that the VM put into the code, that these didn't exist by the user. And green ones are the ones that user created. So the environment gets bindings, and some bindings come from the user, some come from some places. So some level of disambiguation happens in this front end phase of our compilation. So it does these two parts, and the rest of the things happen in the next phase. That's the middle end or the fourth. So we have a front end and then the middle end, which actually does and make the code optimizable. So at a very high level, it takes this structure of this S expression format and create something we call compilation units. A compilation unit we define as a couple of logical stack frame and a bunch of code. So it's a code and logical stack frame collection. So just to give an example about how these compilation units get created, if you look at the code on the left, we have bar is equal to some closure and foo is equal to 12 and bar. So this gets extracted into its own compilation unit, and you have some sort of a stack frame that represents the binding. And then the closure itself gets its own little space of compilation unit, and which has this different stack frame. So this is the logical separation that we must do to make the compilation job easier when we go downstream. So there are a few algorithms here. I'll not get into the details of how these things work. There are a lot of interesting things that we can do. So when you go from representing a program in a system, you need to think about the stack frame, and there are really neat things you can do. You can move things around on the stack because some addresses in the stack are really optimized to be loaded up quickly. So you could prioritize things on the stack. So we have a few things that take care of moving these things around. But at the end of the day, you just need a contiguous memory of reference at the end. So you can think of us having a way to do this right now. And and once that's done, so this second pass of the compiler you can imagine is simplifying the program even more. So this was the program that we started with, and it's simplifying things even more, and now you're end up with this piece of logical iridium code. It's not the exact code, it's going to have a lot more to it, but this like a simplified representation. And now we just have two basic blocks, and inside the basic blocks you see there are no bindings anymore. These are replaced with these references. And one really neat thing about iridium that we have the luxury to build is inlining becomes very easy when you don't have bindings in your program. When you inline a function, you have to rename A1, A2, A3, T1, T2. It becomes a mess. But if you create singletons out and separate out the logical bindings, you can just copy paste code to do inlining. So that's what we want to do. And that's the design principle behind representing these things. But coming back to the problem, the code has become much simpler. You start from BB0, run downward. And the question that we really wanted to know was what's the output of console.log. So console.log call is happening here. And the value that really gets read is this NUBD, that's the local A that's coming from this location in the stack frame. And finally, the answer is NUBD. The acronym tells you the answer. It's no use before def. So, two weeks ago, this is the comment I heard about this program. If output is anything other than 12, JavaScript is broken. So turns out both the options 12 and 13 are in fact wrong. You get an error at the end, so it was a trick question. Anyway, so now so this gives you a feel of how this breaks down a sort of complicated language into a very functional, simple to work with core. And the final step is, in my opinion, the easiest. Instruction selection is something that I don't find much difficulty in, because VMs have a very rich instruction set, and it's really easy to sort of translate your code into them. So we have a backend, and I know some people here will think this is not a real compiler because it uses JSON as the binary format. So this is a remnant from debugging. We haven't gotten around to a real binary format yet. So our code sort of gets expanded. So you can imagine the current system takes a 1 MB code file as input and produces 100 MB file as output. But this is a work in progress. So it takes a JSON file. We use a JSON library to load this in the backend and do the instruction selection. And the instruction selection pass really has rooms for improvement. As I mentioned, there are a lot of specialized instructions that make access to certain stack locations faster. There are some instructions that bypass certain reference checks. There are a lot of read and write barriers. So one of the things that you really need to know about JavaScript is just because something looks like A is equal to B doesn't mean it's A is equal to B. It could sit behind a write barrier, and that write barrier may have conditions. And there are even read barriers for even simple looking things like console.log A, which we just saw. The A was sitting behind a read barrier, which prevented you from reading uninitialized value. So we have a few optimization passes that sort of reduce these barriers and so on. So there's that work happening here. So this is the generated bytecode after the instruction selection, and this is the output that we get. So in conclusion, this was our work from this year. So these are the different projects and some statistics. So it's all being developed in-house at IITB. We don't really use external code, so it's all homemade. And this was the result. So you can see this is the slowdown, and these are the benchmarks. So I know it's contrary to all the talks here that I'll be showing slowdowns instead of speed ups. But this was 1st of September. We finally managed to get all the benchmarks working, the instruction selection done just right. So this is our first draft. And this was 2 weeks ago. The worst peak became 100% faster, still 500% slower. And this is last week. So we are seeing some improvement. So when you have a system that's able to represent your language, the only difficulty is coming up with the predicates. So the predicates are like, okay, if these set of conditions meet, I can delete this code. If these set of conditions meet, I can move around this code, or I can inline. So this process I feel is a bit faster. We have a lot of low hanging fruit, so we should make quick progress. So this sets us in orbit. So this is where we are, and in the future we'll be implementing and looking at new sorts of optimizations, which sort of become popular now. So you can read about our research group. We are called Plato at IIT Bombay, and this is our link. Thank you.
Thank you. Question? Question? I have one question.
Yes.
You know this cast by Walla Group?
Yes, JS Wala, right?
Yes.
Yes.
How is it different from that?
So JS Wala was presented at PLDI in 2014. It targets a much older specification of the language. And in our study, what we found was the transpilation that you have to do if you want to analyze new code, that the transpiler is not semantics preserving. Turns out it's not even functionally possible to represent some of these new syntax features as a combination of these old syntax. So we believe that's a semantic problem. So the only solution is build our own framework for this.
Okay. Any other questions?
Fun project. Yeah, my name is Krishna Rajwala, One question I had is, what's your thought on the size of the IR that will be generated for large JavaScript applications? Is that a design thought you had in your mind at all so far? Or you still
So
I know
currently,
it's a work in progress, but
yes. So we have benchmark programs that are around 60, 70,000 lines of code, and our compiler is really slow, I admit. But the really answer that question, I don't want to speculate on what might be slow. So our solution here is measure everything, see exactly what is so slow. Is it some grouping pass which is slow, or is it some transformation pass which is slow? And really nail down the problem that way.
Okay, question is the slow part. Question was
Scalability. Okay.
size.
So I don't see size being much of a problem. So S expression has been a S expression format gets used in the RussiaJet compiler and a lot of R-based compilers, and they have been known to scale. So I'm counting on the fact that because this has been so widely used, and there's a book on it, the Blue Book, which literally represents an entire language in Lisp. So I believe it should scale.
Okay, it was time does people.
Walk for bidirectional analysis. So,
Go to the first line. This is the pointer. And with this you can control the crafting. Control 15. Yeah. Okay. New pointer.
Yeah, point. This one, the red one.
The red one. Okay, fine. Thank you. Hello everyone. Hello everyone. I'm Swati Jaiswal and I'll be talking about Vasco for bidirectional analysis. So, if we want to understand context sensitivity, what it does is it is trying to capture the effect of the callee in the caller procedure. And it does so by achieving the effect of inlining. And this effect can be achieved by performing call return matching, by using the call string space method, or computing the summary of the callee and using the summary at the call point, as in the functional method, or analyzing a procedure for a particular data flow value, as in the Vasco or the graph reachability based methods. So there are many context sensitive methods that have been proposed in the literature. And here is the list. But now if I try to talk about all flows, so we talk about unidirectional flows and bidirectional flows. So all the methods that I have listed, they are for unidirectional flows. When we talk about bidirectional flows, we can further subcategorize it. So bidirectional flows would be of the kind where we have two components and they are interacting with each other. Okay, an example of that kind would be liveness based pointer analysis that I would be taking up as an example. And that is the first category here where I'm talking about this category, only unidirectional interacting components. The others are only universal component where there is only one component and the information is being propagated in both the directions. And the third one is both unidirectional and crossover components. So when we talk about context sensitive methods for these different kinds of bidirectional flows, we see that there have been some attempts in this area, not in the others. Even for this first category where we are interested in right now, for only unidirectional interacting components, the context sensitive methods that are, so for example, the LFCPA work, the liveness based pointer analysis, they use value based termination of call strings. The floatroid approach also is context sensitive. But these methods, which are context sensitive, they either try to perform context matching or use some notion of context injection. And they do not explicate what would be the notion of context or how the context matching needs to be done and what is this notion. So we would try to address all these issues in this talk today. So context sensitive methods defined for unidirectional analysis cannot be used for bidirectional analysis as it is. So now, as I said, we will be talking about liveness based pointer analysis as our application. So this analysis comprises of two constituent analysis. The liveness is a strong liveness and the points to analysis. And these analyses are interdependent on each other. By interdependency, I mean points to information is being computed only for the pointers that are marked live, and the liveness information refers to this points to information to generate liveness of additional pointers. And we will be looking at this with the help of an example. So if this is an example and I have marked all the statements in different basic blocks so that we can understand the flow of points to information here. So a flow sensitive points to information that would be generated would be something like this. Now, if I were to explain this, if you look at this use of P here, I don't need all these information that is being computed here. Instead, what I'm interested in is only where P is pointing to. But if we look at the steps intermediately, the computation of where P points to happens when we know where Q points to or where further pointies of Q would point to. So in some sense, all the information that I have marked in red are not required here. They are redundant information. So LFCPA typically is designed to handle this problem. So the first round of liveness analysis, what it does is it would mark liveness of a pointer at the use point. and generate subsequent liveness at intermediate points. And once it has done this, once it has marked some pointers as live, then the next step is to generate points to information for the pointers that are marked live. So as Q is been marked live here, it would generate liveness of Q pointing to P and it would propagate it. We are still not able to find out where P is pointing to because we don't know where point of Q is pointing to. So we need one more round of liveness, which would say that apart from Q here, we should also be generating liveness of B. And that is what would happen in the subsequent round of liveness. Now that we have marked B as live, we know that the points to analysis would take care of it and would generate liveness of B. And the additional points to information would be generated. And now we are able to figure out where B points to. So now if we compare the points to information that has been generated in both P1 and P2 rounds, we see that it's exactly the information that we needed here, that we said is relevant, and it does not compute the information marked in red, which is redundant computation. So strong liveness analysis and points to analysis, they are interdependent of each other. Points to information, as we said, is generated for only the pointers that are marked live. And strong liveness uses points to information to generate more liveness of pointers. Right? And LFCPA is able to reduce the amount of information computed significantly. Now that when we understand our application LFCPA, let's look at how to make it context sensitive and the challenges there. So we use VASCO method, the value context based context sensitive method, to make our application context sensitive. So what does VASCO do? VASCO uses data flow values to define the context. So when I am analyzing a procedure, if there is a particular data flow value in which the procedure has not been analyzed, it will analyze the procedure. And if the procedure has already been analyzed in a particular context with a particular data flow value, we will not analyze it again. Instead, we will reuse the results. So we will first talk about this with the help of another example. So I am kind of enriching the previous example. Now in this example, if we look at it, we have this call point. We have two call points in main, and there are use of P at these points, and procedure T is doing nothing but it just has an indirect assignment statement P equal to start Q. So now we will start with the liveness round. So for the liveness round, what would happen is we would generate a context x0 for main with the empty value. So we're doing liveness. So we're saying that we consider the initial liveness information as empty set. Now when we encounter this call point here, we want to analyze procedure T. So when we want to analyze this procedure T, we check if my procedure T has been analyzed with this data flow value P. If it has not been analyzed, it will create another context X1 for procedure T and analyze procedure T. In the intermediate step, it would generate liveness of Q. And once it has analyzed this procedure completely, it would propagate the result back to the call point. Now, now we encounter this use point here and we generate liveness of P. Again, at this call point here, call site C1, when we encounter this call to T, we check, has my procedure T been analyzed with this data flow value P? And we know that procedure T has been analyzed and the analysis is complete for that procedure. So we can reuse the exit value that has been computed. So procedure T will not be analyzed again. Instead, the exit value, the already analyzed summary of the procedure would be used at that point. So we end up not analyzing procedure T again, but using the values at this point. And with this, we complete our first round of liveness, first round of context sensitive liveness, right? So LFCPA, now the next round of points to analysis would come into picture. So because LFCPA, we said it's comprising of interdependent components of these analysis, the points to analysis round need to refer to the information of the strong liveness information. So when I start analyzing this procedure for this context here, so I create another context y0 for points to analysis round. But I need to make sure that I'm talking to this x0 here because my analysis wants to know what pointer information should I generate liveness for. So I say there is a correspondence between y0 and x0, and I generate points to information q points to a because my x0 said that I am interested in knowing where q points to. When now we encounter call to t, we want to decide whether uh, procedure T has been analyzed with this data flow value q points to A, and it has not been. So we create another context y1 with the data flow value q points to A, and we analyze this procedure. This procedure will not do anything because p equal to star q cannot be dereferenced. We don't know where point of q is pointing to yet. At this call point here, we would have q pointing to C, and this information will also reach the call point in a different context because the incoming data flow value that we are using to analyze procedure T is different in both the contexts. So we create two different contexts in this case. Okay. So because different data flow values reaches, we have different context as opposed to what was done in the liveness round. In the liveness round, we had the same data flow value reaching from both the contexts, so we analyzed procedure T only once. In this case, we are analyzing procedure T twice. Now we will proceed to the next round of liveness analysis. So what would happen now is, in the liveness analysis round, when I say I'm generating liveness of P, and this liveness of P would reach here, I want to find out where Q points to. And my points to information associated with the corresponding context y2 gives me this information that q points to C. With that information, I would generate liveness of q and C here, and that information would be propagated back at the call point. But what would happen when the same information reaches from this call site? Based on the existing notion of Vasco, what we would do is we would say that since my procedure has already been analyzed, let me reuse the value, right? So even if I'm saying that my X0 needs to refer to a corresponding context of a different analysis, we also need to encode it in the algorithm. So I don't know what to compute because I would say that my QC has been computed as the exit value, let me reuse it, but that is not right. Right? So this problem is arising because we just don't need to create two interacting components which are interacting at the context level. We also need to understand that we need to split the contexts also. So just context matching is not enough. So in this case, if we look at this graph here, X1 is being created as a single context for procedure T in the liveness round, whereas points to round is creating two different contexts. Now, how do we map Y1 and Y2 with X1? So to address this issue, we would want to look at what is the notion of context and can we avoid this context matching and context splitting completely. Okay. So in this case, procedure T need to be analyzed in context X1, Y1 and X1, Y2 separately. And that was not happening because we need to work on the analysis. So now there is a need for context matching while performing the analysis as well as while creating the constituent analysis. So we propose a new notion of context that eliminates this need for context matching. So let's consider this case where I say that at this call point, procedure R is being invoked. So for a forward analysis in Vasco, what is the notion of context? The inflow value reaching in procedure R, and that is F in this case. For a backward analysis, it is the information reaching end of R, and that is B. For a bidirectional analysis, if we are able to find out what is the inflow value and define context appropriately, maybe our job is done. So for a bidirectional analysis, if we look at this information F and B, so we say that the inflow value is the forward component reaching from the start of the call site and the backward component reaching from the end of the call site. So considering this as a pair of the inflow value, which will help us define the context, not for individual strong liveness and points to analysis, but as a pair, it would help us address the issue of context matching and getting into further complications. So let me quickly run over this example. So now we are saying that we're computing a pair of values. So we have x0, p comma empty set, which is representing the forward component, and p, which is representing the liveness information being computed. At the call point, since procedure T has not been analyzed with this context, We create a new context x1. We analyze this context. Intermediately, we are generating liveness of Q, and that information is propagated back to the call side. Similarly, at the use point, at node N3, we generate liveness of P, but then procedure P has already been analyzed in the context, so we reuse the value. And this part is very similar to what had happened in the previous slide for the liveness round, except that now we are maintaining the context as a pair, and with every context, a pair of data flow values. When we perform points to analysis, now we compute that Q points to A. With this, the information that would reach the query procedure would be Q points to A and Q. The context that we should note is generated as Q points to A and P. So Q points to A, the forward component reaching the call, and P, the liveness of P being generated at the out of the call block. So we create a new context and nothing else would happen in this procedure. We are yet to find out where Q points to. Similarly, from the call point, we would have the information coming as Q points to C and Q, and that is the information that reaches at the call point. We create a separate context in this case. Now, in the further round of liveness analysis, what would happen is, so let me remove all the pink boxes. So this is the information that we generate at the end of points to round first points to round. And now when we want to find out where our liveness information would be propagated in the next round, what would happen is we start saying that we generate liveness of empty set and P. This information reaches the calling procedure, and now the calling procedure, now that it knows where Q points to in the respective context, would generate Q points to A and will generate liveness of QA in context X2 and QC in context X3. And that information would be reaching the start of the calling procedure. It would be updated as the exit values here and propagated back. Now it's very easy to see that one more round of points to analysis will very appropriately propagate the information that A points to B here and C points to D here, and propagate the information and correctly find out that P points to A in context X2 and P points to P points to D in context X3. So we define context as a pair of data flow values, forward component reaching the start of the call node and backward component reaching the end of the call node. This eliminates the need for context matching, and it naturally extends the existing Vasco defined for unidirectional analysis to bidirectional. So the current status of Vasco implementation, it has been implemented in LLVM. Our current implementation is the result of efforts of Professor Uday Khedkar and multiple MTech projects at IIT Bombay under his guidance. Kaushik and Sridevi, we have them in the audience. They are our past MTech students who have worked on NFCPA and Vasco, respectively. Anamitra is here, who has been actively involved in both NFCPA and Vasco. Skarma, again, is doing her MTech project from IIT Bombay, and she is looking at the worklist management issue in Vasco. The other projects that we are using on orbiting on top of Vasco framework is we have Aditi Raste, who is a PhD student from Pune University. She is using it for her proposed bypassing NFCPA work. She is also in the audience, and she will be presenting this work as a poster today. And another work by our group, which is stage pointer analysis, is also built on top of this framework. Thank you.
Any questions? I have a question. Hi, good ideas here. I had a question. Have you thought about extending this idea of liveness to non-C type programs? Say in Java, where I don't care too much about the liveness of individual variables, but I'm quite interested in the heap locations. Have you considered extending these thoughts?
Right now, not. But then liveness based analysis is a very generic concept. And it can be applied anywhere. So, for example, if you want to cut down on the information, it is a wise idea to do it liveness based, so that you naturally find out which elements or what information you want to compute and restrict it to that.
But we are talking about heap is live.
Yeah, so I think there was a work by Professor Khedkar and one of his past students where they were talking about liveness on heap abstractions as well.
If I recall my memory, I think this WASPO reduces the call stack, call string implementation from KD square to KD, right? But does it impact this WASPO analysis? Does the complexity increase because of this?
Oh, so I think you're comparing the classical constraints based approach and maybe the value based termination of constraints, which restricts, which does not impose any restriction on the length of the call strings, but it says that it provides a natural bound
Yeah, natural bound.
on the call string, on the length of the call strings that would be generated by using the data flow values.
Right.
The VASCO framework here is kind of a revisit or remodeling of the original value based termination of call strings, where it does not make data flow values as a second class citizen, but makes as a first class citizen. And it says that I will define context not by referring to the call strings, but by looking at the data flow values itself.
Okay. So in that sense,
Yeah,
bound,
so it has already reduced it. So it's along the
I mean,
lines
the
of value.
bound stays, whatever the VASCO bound previously.
The value based termination of constraints. Yeah, yeah, yeah.
Any other questions? Okay, let us thank the speaker once again. So our next talk is context sensitive interprocedural dominance for SSC. Society. Yeah.
Yeah, no. I was not present. Yes. Yes. That's okay. It's okay.
Yeah, I want to clear up. Before we use that string for clear up.
It's not changing.
Hi, I'm Supriya Bhide. I'm working in IIT Bombay with Professor Uday Khedkar and Dr. Preetam Gara. I'm in my fourth year of PhD. I know my talk is before lunch, so let's have some delicious food for thought now and before we proceed to the main course. So, my talk is on context sensitive interprocedural dominance for SSA. So, here are some obvious questions and let's answer them. So, dominance is a relation between two nodes in a control flow graph. SSA is an intermediate representation used widely by production compilers. What is SSA, you ask? Well, here's a control flow graph of a simple program, and here is its SSA form. We can observe that there are unique definitions for each statement that assignment statement we observe here. And at node 7, we observe a phi function inserted. Why we insert it here, how we insert it here, we'll look at the details later on. So to answer the third question, what is the relation between these two terms? Well, in order to construct SSA form from the source program, certain transformations are required and the transform program is required to satisfy certain properties. And to ensure that these properties are satisfied and the constructed SSA form is optimal, dominance relations are crucial. But dominance relations already exist at the intra-procedural level. So why interprocedural dominance, you ask? Well, SSA has the following properties. Every use has exactly one definition reaching it. At points where multiple definitions reach, we insert a phi function and merge them into a new single definition. And the third important point is that the number of phi functions we insert should be as small as possible because we are adding some code into the already existing code. And these relations of dominance and dominance factor ensure that these properties are satisfied. We at IIT Bombay are working on constructing an interprocedural SSA, and therefore we want to extend these relations of dominance and dominance factor to the interprocedural level. So we'll begin by revising the intraprocedural concepts first. So here's an example that we saw before. The question is, we know we inserted some new definitions, we made all definitions unique, but how do I how do we know that what definitions, what versions of variables should we put on the RHS in the use side? To answer this, we must understand the dominance relation. So here's a simple control flow graph, blank with no assignment statements. And dominance relation says that a node M dominates node N if and only if every path from start to node N passes through M. So let's consider the node 7. Here, from the start node to node 7, we have exactly two paths. And observe that the encircled nodes appear on all of these paths. Therefore, nodes 1, 2, and 7 would dominate node 7. Let's take the case for node 5. We have exactly one path. Therefore, nodes 1, 2, 3, and 5 would all dominate node 5. Similarly, for node 6, nodes 1, 2, 4, and 6 would dominate node 6. Dominance relation is a partial order relation. So with this information, let's come back to how we are using versions of definitions on the RHS. So as you can observe, the versions of the variables on the RHS are coming from the dominators. But one might wonder that these nodes 5, 6, and 7 have multiple dominators. Why just their immediate dominator? Well, to answer this question, the dominators of these nodes have dominance relation among themselves as well. Therefore, only the effect of the last dominator would reach these nodes. So we now know how version numbers are assigned. But what about phi functions? How do we decide where to put them? So to answer this, we must understand the dominance frontier relation. So let's consider the same control flow graph. Dominance frontier of a node n is the point at which the dominance of n ends. So here we have a mathematical equation, and SDOM here refers to strict dominance, which is a version of a variant of dominance which is not reflexive. So coming back, in order to define dominance frontier relation, it is useful to define the notion of dominators of an edge I to j, where the dominators of this edge are essentially the dominators of node I. So for instance, here nodes 1, 2, 3, and 5 dominate the edge 5 to 7. Nodes 1, 2, 4, and 6 dominate the edge 6 to 7. Observe that nodes 1 and 2 dominate both the in edges of 7. However, nodes 3, 4, 5, and 6 do not dominate both in edges of 7. Hence, node 7 is a dominance frontier of nodes 3, 4, 5, and 6, but it is not a dominance frontier of nodes 1 and 2. So with that, how does classical SSA place phi functions? It places them at the dominance frontiers of the relevant definition nodes. So now we saw it at the intra-procedural level. So let's try to extend this to the inter-procedural level. And let's consider all of the variables here are now global variables. So we have the same control flow graph. Let's introduce a procedure queue. Let's push the statement from node 6 into node 10, call queue from these nodes. Now let's try to answer. Does node 4 dominate node 10? Is node 7 a dominance frontier of node 10? Let's introduce yet another procedure and push the statement from node 5 into procedure R. And now let's try to answer the questions. Does node 3 dominate node 13? Is node 7 a dominance frontier of node 13? Does node 10 dominate node 13? Or does node 13 dominate node 10? Well, to answer these questions, we must define these relations at the interprocedural level. So before we get to those, before we define them at the interprocedural level, we must understand some terminologies. For simplicity of explanation, we will exclude indirect calls in our examples. So let's look at the first term. It's call string. So call string is a call chain reaching a procedure which is described in terms of call nodes. And these are essentially sequence of unfinished call nodes, unfinished calls. So we denote call strings using the symbol sigma. So for here, instance, the call strings in the green this thing represent the call strings reaching node R, which is 1 or 1, 2, 3 or 1, 2, 3, 2, 3 and so on. Similarly, the call strings in the orange or peach box 1, 2, 1, 2, 4, 1, 2, 4, 2, 3, 2, all of these are the call strings that reach the start of procedure S. Next, let's look at LCP of sigma 1, sigma 2. Again, sigma 1, sigma 2 are the call strings here. LCP is longest common prefix. So here the longest common prefix of these two call strings would be 1, 2, 3, 4, 5. Next, pivot is another term that we've introduced. Pivot is the first node in sigma 1 after removing the LCP of sigma 1, sigma 2 from sigma 1. For instance, pivot of sigma 1, sigma 2 here would be node 6. Pivot of sigma 2, sigma 1 would be node 8. The next is EOC of n. EOC of n is the end node of the procedure called from node n. So for example, EOC of node 2 would be node 6. And this is the last term. So prefix relation, we denote it with the prefix symbol. Let a call string sigma 1 reach q and sigma 2 reach p. Then we say that if sigma 1 is a proper prefix of sigma 2, it denotes that procedure q transitively calls procedure p. So for instance, 1, 2, 3, 4 is a call string reaching the start of procedure q, which calls procedure r from node 5, and the call string reaching start r is 1, 2, 3, 4, 5, which in turn calls procedure s, and the call string reaching this procedure is 1, 2, 3, 4, 5, 6. Observe that all of these call strings are prefixes of the previous one, proper prefixes. So note the following. Consider the call node 2, which calls procedure r here, occurring in some call string, say sigma. Then node 2 would dominate the start of procedure r in the context sigma, or in the call string sigma. Start r, however, would dominate all the nodes in r in every sigma. So we'll keep these things in mind. It will help us to understand the further equations. Here the use of sigma or call strings is helping us ensure context sensitivity. So now we want to know if node m in some procedure p dominates node n in some other procedure q. Now here p and q may be the same or they may be different. So let's look at the dominance relation. In dominance relation, we categorize the types of programs into two parts. One is in which the call strings reaching procedure P and procedure Q are the same, and the other in which they are different. So let's look at the first case. Here, the call string reaching procedure P and Q are the same. This is only possible only if P and Q are the same procedures. Here, M and N, the dominator and the node it dominates, are in the same procedure. Next, the second case is further divided into three subcases. So let's look at the first case. In the first case, we say that P calls Q transitively. Here, P and Q may or may not be the same procedures. Here, the dominator is in the caller procedure and the node it dominates is in the callee procedure. This second case is in which Q calls P transitively. Again, P and Q may or may not be the same procedures. Here, here the dominator is in the callee procedure. The node it dominates is in caller procedure. This brings us to the last case where P and Q are both callees of some other procedure S. Again, here P and Q may or may not be the same procedures. Here, both the dominator as well as the node it dominates are although in two different procedure contexts. They are in the callee procedures. So with this, let's look at these four cases in detail and establish the dominance relation at the interprocedural level. So here's the case 1. What we require here is for node M to dominate node N. For instance, here node 2 dominates node 4. This is same as the classical intraprocedural dominance relation, which we already know. The equation for this is as follows. Let's look at the second case. In this, the dominator is in a caller procedure and the node it dominates is in the callee procedure. What we require here is for node M to dominate node I. What already holds, as we saw before, is that node I dominates the start Q and start Q dominates node N. With this, we have the equation for the second case as well. The third case is the one in which the dominator is in the callee procedure and the node it dominates is in the caller procedure. Here, what we require is for node I to dominate node N and for node M to dominate the end of its procedure, which is end P. What already holds that node I dominates start P. Since all these conditions are satisfied, we can say that M dominates N or node 7 dominates node 4. The equation for the same is as given here. Let's come to the fourth case. Here, both the dominator and the node it dominates are in Collie procedures. What we require here is for node I to dominate node J, which it does. Node 6 dominates node 7. What we also require is for M to dominate end P. So node 11 dominates node 12. What holds is I dominates start P, that is node 6 already dominates node 10, and J dominates start Q, that is node 7 dominates node 30. So since all of these conditions are satisfied, we say that node M dominates node N, that is node 11 dominates node 14. This is the equation for the fourth case. This is the final reveal for all the equations of interprocedural dominance. With this, let's get to the dominance frontier relations. Recall that we saw all these four cases just now, but are all of these valid for dominance frontier? Let's take a look. So for the first case, we require for M to be a now we're looking at M as a dominance frontier. So we want to see whether M can be a dominance frontier of N in this case. It is possible if M had some other path reaching it. So this case is valid. Let's look at the second case in which M is in a Collie procedure. We require for M to be a dominance frontier of I. However, note that this is not possible because I would dominate all the nodes in procedure Q in the context of the call of procedure in call of R. So this case is not possible. Let's look at the third case in which M is in a caller procedure. What we require here is for N to dominate end P, which it can, and for M to be a dominance frontier of I, which is also possible. Therefore, this case is valid. In the fourth case, we require for I to dominate J, which is possible, but we also require for node M to be a dominance frontier of node J, which is again not possible because J will dominate all the nodes in start queue in the context of its call. So this is also an invalid case. So we're just left with two cases. It is important to note the observation here that dominance frontier of a node can never occur in the Collie in any of the Collie procedures. So a dominance frontier of a node will always occur in the same procedure or in a caller procedure. So let's take these two cases one by one. So here we have both the procedures are same, both the dominance frontier and the node are in the same procedure. What we require here is for node M to be a dominance frontier of N. So here we have two paths reaching M, and N, thus M is a dominance frontier of node M. We have seen this before in the classical intra-procedural dominance frontier relations. This is the equation for the same. Next, we have the second case in which P calls Q. The dominance frontier is in the caller procedure. Here what we require is for M to be a dominance frontier of I, and for node N to be a N to dominate end P. What already holds is that I dominates start P. Since all of these conditions are satisfied by this example, we say that node M is a dominance frontier of node N. This is the dominance frontier equation for the same. And this is the final reveal for the interprocedural dominance frontier relations. The next question, which is obvious, is has this not been done before? Well, it has. Here's a paper, you could look it up. But there's a limitation. This paper proposes context-sensitive interprocedural dominance. So, for example, let's take the figure here. What the paper would compute is that nodes 3 and 4 do not dominate node 12 in procedure Q. What our definition computes is that node 3 dominates 12 in the context of call to P at node 5, and node 4 dominates node 12 in the context of call at node 6. So why is that a problem? Well, node 12 contains use of variable y. The definition of y to be used here in SSA form would be determined by its dominators. However, the paper says that neither node 3 nor node 4 dominate node 12, although they contain the definitions of y that would reach here. So now node 12 has two definitions of y reaching it. It would thus insert a phi function for the definition used in node 12. This would make the resulting SSA imprecise. Now we have a way of avoiding this by making SSA more precise by cloning the statement in node 12 context sensitively. The other thing is the paper would consider the variable z at node 7 and 8 to be non-constant. However, our method would be able to perform constant propagation at nodes 7 and 8 and get us use 21 and use 101 instead of a non-constant this thing because we use a context sensitive method. This is because of context sensitivity that we maintain here. And these kinds of opportunities would be missed by context insensitive SSA or the context insensitive dominance relations proposed by the paper. So, coming to what we do, we are constructing interprocedural context sensitive SSA, which is COS SSA. We plan to use these definitions to show the optimality of pi function placement in COS SSA. What's COS SSA, you ask? Well, come see me at my poster on 30th October at Aplas SRC. Thank you.
Any questions?
About the application of this analysis, so did you implement it in some compiler or any plans to use
Yeah.
it in some optimizations?
Yeah, so we have not implemented it yet. We are in the process of implementation. So these relations that we have defined will be used for, so we are implementing context sensitive SSA. So these relations that I just defined will be used to ensure the optimality of our COS SSA, like whether it's placing pi functions optimally and all of those things. So we are in the process of implementation, right?
Actually, look, this process, this analysis more useful in the inlining heuristic, where we can improve it with this exact analysis. Yeah.
Um,
Hey, good talk, yeah. You talk well. Ah.
Thank you, sir.
I have two questions. Let's see. The first one, you mentioned about keeping the call string. I hope you also keep the line numbers where the call is happening.
Yeah, so the call string is essentially the line call node number. Yeah.
The second question is something that you said you don't want to talk. You mentioned that you don't want to talk about in the calls where you don't know, where you cannot resolve. Say function pointers are in the Java case,
Yeah.
Virtual calls or C++ case virtual calls. In such a case, what can you do?
So we are looking at that right now. We are exploring that option. We haven't yet included pointers into our this thing right now, but we are exploring that.
Yeah, I mean, my point is, if you if you precisely do not know the target, the target would be F1 or F2.
Right.
Because you see, the SSA is kind of a lost information.
Yes.
And this is a main information. It will be very interesting analysis.
Yeah, so we plan to use some points to information. We would rely on some external points to information and use that information in order to do our analysis later on. But we are yet to get there right now. Yeah. Thank you.
Yeah. There are no further questions. Let's end the speaker. Thank you.
We have management deal with affect individuals here at duration and sorry. All the different will be able to spend on each poster.
ಎಷ್ಟೊತ್ತಿಲ್ಲ ಇದು ಸ್ವಲ್ಪ ಆಗ್ಲಿ ಇರು.
ಆಯ್ತು. ಅಷ್ಟೇ ಇತ್ತು 90% ಆಗೈತೆ. ಚೀಲ್ ಇನ್ನೂ ಐತಾ? ಚೀಲ್
ಕಾಪಿ ಆಯ್ತಿದೆ.
ಎಷ್ಟು ಕಾಪಿ ಆಗೈತೆ ನೋಡು ಅಟ್ಲೀಸ್ಟ್ ಹೋಗ್ಬೇಕು.
ಎಲ್ಲಿ ಫುಲ್ ಕಟ್ಟ ಕಾಪಿ ಆಗಟ್ಟ ಅಲ್ಲೇ ಇರುತ್ತಪ್ಪ ಅದು.
ಹೌದಾ?
ಫುಲ್ ಹೋಗಾದ್ಮೇಲೆ ಬರೋದು ಅದು. ಇಲ್ಲಾಂದ್ರೆ ಒಂದ್ ಕಾಪಿ ಉಳ್ಕೊಳತ್ತೆ.
G2
ತೆಗೆದ್ರೆ ಒಂದ್ ಕಾಪಿ ಅಲ್ಲೇ ಇರುತ್ತೆ.
ಓಕೆ G2 ಇದಾ ಜೆ
ಮೈ ಬುಕ್
ಹಿಂಗೆ ಕಾಪಿ ಪೇಸ್ಟ್ ಮಾಡಲ್ಲ ಡೇ ಟು ಡೇ ಹಿಂಗೆ ಬರಲ್ಲ. ಹಳೆ ಟೈಮ್ 25 minutes.
ಬಟ್ ಅದು ನೋಡಿ 40 Mbps ಇದೆ 80 Mbps ಡಬಲ್ ಸ್ಪೀಡ್. ಕಾಪಿ ಕೊಟ್ಟ ಕಟ್ ಕೊಟ್ಟ
ಕಟ್ ಮಾಡಿ
ಇದ್ರಲ್ಲಿ ಫಿನಿಶ್ ಮಾಡ್ಬೇಕು. ಅದೆಲ್ಲ ಫಿನಿಶ್ ಮಾಡ್ತಾರೆ
ಆಗ್ಲಿ
ಫೋಟೋ ಎಲ್ಲ ವಿಡಿಯೋ
ಅಲ್ಲೇ ರಾಸಿರೋದು ಅಲ್ಲೇ ಕೂತಾರ ನೋಡಿ. ಇದೇ ಫಾಸ್ಟ್ ಇದು
ರೆಕಾರ್ಡಿಂಗ್ ಐತೆ ಯಾವ್ದು
ಇದೇ ಫಾಸ್ಟ್ ಐತೆ ಇದೇ ಫಾಸ್ಟ್ ಐತೆ.
₹1800
ಇದು ಕ್ವಾರ್ಟರ್ ನೆಕ್ಸ್ಟ್ ಇಸ್ಕೊಟ್ರೆ ಪೂರ SD ಕಾರ್ಡ್ ಐತೆ ಅದಕ್ಕೆ. ಅದಕ್ಕೆ SD ಕಾರ್ಡ್ ಹಾಕರ್ರಾ ಆ ಕ್ಯಾಮ್ರಾಗೆ? ಯಾವಾಗ ನನ್ಗೆ ತರ ಬಿಚ್ಕೊಟ್ರಿ? ಏನ್ ಕಾಪಿ ಮಾಡ್ತೀರಿ ನೋಡಿ ಸೈಲೆಂಟ್ ಆಗಿ ಬಂದು ಇಡ್ಬೇಕಾಯ್ತು ನೀವೆಲ್ಲ. ಅವ್ರಿಗೇನಿತ್ತು ಅವ್ರು ಫಾರ್ಮೆಟ್ ಆಗುತ್ತೆ ಏನಿಲ್ಲ.
ಅಲ್ಲಿ ಕಾರ್ಡ್ ಬಗ್ಗೆನೇ ಫೋಕಸ್ ಆಗಿಲ್ಲ.
ಇಲ್ಲ ಕಾರ್ಡ್ ಎರಡು ಕಾರ್ಡ್ ನನಗೆ ಕೊಟ್ಬಿಟ್ರು ಅವರು.
ಅಲ್ಲಿ ಯೂಶಲಿ ಇರುತ್ತಲ್ಲ ಅನ್ನೋ ಒಂದು ಪ್ರಮೇಲೆ ಇದೆ. ಅದು ಕ್ರೇಜಿ ಇತ್ತು.
ಆಮೇಲೆ ಫೋಟೋ ಹಿಡ್ದೇವ್ ಲಾಸ್ಟ್ ಫೋಟೋ ಕಿತ್ತು ನಾವೆಲ್ಲಿಂದ ಹೋಗ್ತಾರಂತೆ.
ಲೈಟ್ ಬೇರೆ ಇಲ್ಲ.
साकल वही तो कम नहीं रहे
ಎಡಿಟಿಂಗ್ ಅಲ್ಲ ಎಡಿಟಿಂಗ್ ನಮಗೇನು ಕೆಲಸ ಇಲ್ಲ ಅಷ್ಟೇ ಕೂತ್ಕೊಳ್ರೆ ಆರಾಮ್ ಸುಸ್ತಲ್ಲ ಕ್ಯಾ ಭಯ್ಯ ಎಸ್ ಡಿ ಕಾರ್ಡ್
ಇರ್ಲಿಲ್ಲ ಅಲ್ಲ ಕ್ಲಿಕ್ ಆಯ್ತಿತ್ತಾ ಹಂಗೆ
ಕ್ಲಿಕ್ ಆಗ್ತಿದೆ ಹಂಗ್ ಕ್ಲಿಕ್ ಆಗುತ್ತೆ ಹಾ
ತೋರ್ಸಲ್ವಾ
ತೋರ್ಸಲ್ಲ
ಯಾವ ಕಾಲದಲ್ಲಿ
ನಾನು ತೋರ್ಸಿತ್ತು
ಇಲ್ಲ
ಹೌದಾ
ಕಡೆ ನಾನು ಡಿಸ್ಪ್ಲೇ ಮೇಲೆ
ಡಿಸ್ಪ್ಲೇ ಮೇಲೆ ಬಂದಿರುತ್ತೆ ನೋಡ್ರಿ
ಹಾ ಬಟ್ ಅದು ಫೋಟೋ ತರನೇ ಮೂವ್ಮೆಂಟ್ ನೋಡಿ ತೋರಿಸ್ತೀನಿ ಹಿಂಗಾಗಿ ಇದು ಹಿಂಗ್ ನೋಡ್ತಾ ಇದೀನಿ ನೋ ಕಡೆ ಅಬ್ಸರ್ವ್ ಮಾಡಿಲ್ಲ ನಾನು ಹಿಂಗ್ ಹೋಗ್ತೇನೆ ನೋಡಿ ಕ್ಲಿಕ್ ಆಗ್ತದೆ ಮೂವ್ಮೆಂಟ್
ಇಲ್ಲೂ ನೋಡ್ತಾ ಕೆಲ್ಸ ತೋರಿಸ್ತಿತ್ತು
ಹಿಂಗಲ್ಲ ಇಲ್ಲಲ್ಲ ಈ ಮೂವ್ಮೆಂಟ್ ನೋಡ್ರಿ ನಾನು ತಕೊಂಡ್ರೆ ರೆಡಿ ಆಗ್ತದೆ ಬಟ್ ನೆಕ್ಸ್ಟ್ ಈ ಮೂವ್ಮೆಂಟ್ ಇದೆ
ಕರೆಕ್ಟ್
ಒಳ್ಳೆ ನಕಲ ಬಕ್ರ ಆಗ್ತಿದ್ವಿ
ಅವ್ರು ಆಯ್ತಿದ್ರು
ಒಳ್ಳೆ ಮೂವ್ಮೆಂಟ್ ಹೇಳ್ತಲ್ಲ ಎಲ್ಲ ಆದ್ಮೇಲೆ
ಎಲ್ಲ ಡಿಸ್ಪೋಸ್ ಆಮೇಲೆ ಅದು
सामने का भी पड़ा हुआ है क्या कोई फोटो स्कैन करो मत सारी फोटो शादी में सेलेक्ट है अरे भाई ಒಬ್ಬರನ್ನ
ಸುಮ್ಮನೆ ಇವರು ರೀಲ್ಸ್
अब क्या
रिपोर्ट बताइए किस बताइए हम कहेंगे ठीक है मैं तो जल्दी कर
देखा सोने वाली आने के बाद तो निकल गया वाह तो मैं कॉल करवाएगी आज तो जाके बताइए
Excuse me, do you not have charger? Type C. Yes, type C.
Sorry, sir. Port is not available.
Do you have type C charger?
I don't have changes. We have the wire.
पोर्ट अभी कौन सा अवेलेबल है
लोग क्या कर रहे हो तो ये इवेंट्स कवर करते हो वैसे इवेंट्स का काम करते हो तो इवेंट कवर करने का चल भाई
इवेंट्स का कितना भाई करता है ऐसे इवेंट्स ठीक नॉर्मली है ब्रो अभी No.
Everything is in you can put it here. सारे मतलब कट आउट कट ये और वो वाला हाँ वो बहुत हम पॉइंट तो देख लिया ये ट्रांजिशन करना है स्ट्रीम करना होगा क्या ट्रांजिशन पूछ लेता है क्या कर देते हैं पूरा और कोई है I will add on to the beginning yeah, I mean, yeah, I will okay. I will take one part to the anyone. Oh, exactly. What time? शोज नहीं होते हैं बड़े शोज परफॉर्मेंस शिफ्ट वो करते हैं कि वो भी ऐसे ही कॉलेज में ही काम कर रहे थे तो एक फेस्ट था डीएस में बहुत बड़ा तो उधर कोई तो आया था तो जो स्क्रीन्स लगती है दूसरी स्क्रीन्स की मैपिंग करनी पड़ती है वो तो वो
एक्चुअली मैं काम करता हूँ शाम के स्कूल में कुछ नहीं करता अपना ही नहीं मेरा जो काम आता है उसमें टाइम था
मैंने बनाया फिर मैंने अपडेट नहीं किया है क्योंकि बहुत सारे काम जैसे ये काम है तो पोर्टफोलियो बनाने में बहुत फाइल कर सकते हैं
और मेरा एक पोर्टफोलियो क्या पोर्टफोलियो है हाँ, एक से हम किसी को कुछ वीडियो भेजा था हाँ ले देख लो ये मैंने बनाया है
वही
Like
सेम
that.
सेम मोस्टली नेटवर्किंग से हो जाता है कि
हाँ मेरा
हो जाता
networking से देखो अभी ऐसे देख लिया काम करते हुए पता है कि काम देख लेता है वो वैसे में
अब जैसे ये हो गया तो फिर आप इसको कंपाइल करके एक अच्छा अच्छा अगला प्रोजेक्ट पे काम करो
लेकिन ये करके दे रही है उसमें पेट खोल
मैंने तो वेबसाइट बना दिया उसको पूरा सब पड़ा हुआ है फिर पुराने प्रोजेक्ट इनहेंस पे जो डाला है इसमें एक यूआई का बनाया था और एक कॉलेज का बनाया था सफाई में डाल दिया है ऐसा था वो वेबसाइट और फिर हुआ क्या दूसरी बार
सुनते नहीं पीडीएफ
हम सिग्मा आजकल वेबसाइट पे वो वीडियो प्ले होता है वहाँ पे सफाई हाँ वो सेक्टर में अपनी हम कौन अपडेट करता है I think it was
Bro,
ಪ್ರೈಸಿಂಗ್ ಗಿಫ್ಟ್ ಏನಾಯ್ತು?
ಒಂದೇ ಒಂದು ಬಂದೈತೆ ಇಲ್ಲಿ ಫೈಲು ಡೇಟು ಅಲ್ಲಿ. ಇವಾಗ ಕಾಪಿ ಮಾಡಿದ್ದೆ ಇಲ್ಲಿ.
ಒಂದೇ ಒಂದಿತ್ತು.
ಅವಾಗಲೇ ಕಾಪಿ ಮಾಡಿ ಇದೆಲ್ಲ ಕಾಪಿ ಮಾಡಿದೆ ನಾನು.
ಏನೇ ಹೇಳ್ತಿದ್ಯೋ?
ಇದು ಡೇಟ್ 27 ತೋರಿಸ್ತೈತೆ. 28 ಇಲ್ಲ ಡೇಟ್, ಇವತ್ತಿನ ಡೇಟ್. ಓಕೆನಾ? ಇದು ಬಂದು
27.
ಇದರಲ್ಲಿ 27 ಇದ್ರಲ್ಲಿ ಐತೆ.
ಏನಾಯ್ತು ಇವಾಗ?
ಎರಡು ಕೊಳಾಬ್ ಆಗ್ಬಿಡ್ತಾ ಇಲ್ಲಾಂದ್ರೆ?
ನೋಡು. ಓ ಕಾಪಿ ಆಗಿರೋದು ಫೈಲ್ ಬಂದಿಲ್ವಾ? ತೋರ್ಸು ನೋಡು. ಕಟ್ ಕಾಪಿ ಮಾಡೋದು.
ಕಟ್ ಕಾಪಿನೇ ಮಾಡಿದ್ದು. ಪ್ರೈವೇಟ್ ಇಂದ ಇದಿತ್ತು, ಎರಡು ಇದ್ದು ಹೆಸರು. ಲೈಕ್ ಅದೆಲ್ಲ ಪ್ರೈವೇಟ್
ಮೆಮೊರಿ ಕಾರ್ಡ್ ತೆಗಿ. ಮೆಮೊರಿ ಕಾರ್ಡ್ ಬಂತು. ಎಲ್ಲಿ? ಇಲ್ಲಿ ಒಂದು ಎಕ್ಸ್ಟ್ರಾ ಓಪನ್ ಮಾಡು. ಸ್ಪೀಸಿ ಹೋಗು. ಮೆಮೊರಿ ಕಾರ್ಡ್ ತೆಗಿ.
ಪ್ರೋಗ್ರೆಸ್ 0. ಪ್ರೋಗ್ರೆಸ್ ಎಲ್ಲ ಐತೆ ಫೈಲು.
ಫೈಲ್ ಇರುತ್ತೆ.
ಓಕೆ.
ವಿಡಿಯೋ ಮರ್ಜ್ ಆಗ್ಬಿಟ್ಟಿದೆ.
ಮರ್ಜ್ ಆಗ್ಬಿಟ್ಟೈತೆನಾ? ಅದಕ್ಕೆ ಸ್ಕಿಪ್ ಅಂತ ಅನ್ಕೊಂತೀನಿ. ಲೈಕ್ ಲಾಸ್ಟ್
ಸ್ಕಿಪ್ ಯಾಕೆ ಕೊಟ್ಟೆ?
ಅವ್ರ ಫೈಲ್ ಬಂದು ಸ್ಕಿಪ್ ರಿಪ್ಲೇಸ್ ಇಂದ
ಇವಾಗ ಪ್ರಾಬ್ಲಮ್ ಆಗುತ್ತೆ. ಅದಕ್ಕೆ ಸಪರೇಟ್ ಫೈಲ್ ಮಾಡ್ಬಿಟ್ಟಿದ್ರೆ ಈಸಿ ಆಗ್ತದೆ. ಇವಾಗಿಲ್ಲ ವಿಡಿಯೋಸ್ ಇಲ್ಲ. ಎಲ್ಲಿದೆ ವಿಡಿಯೋಸ್? ಎಲ್ಲಿದೆ?
ಇದೇ ವಿಡಿಯೋಸ್.
ಯಾವ ಫಾರ್ಮೆಟ್ ಆಯ್ತು?
ಏನೆಂದು ಯಾವ್ದು ಇದ್ರಲ್ಲಿ ಪ್ಲೇ ಆಯ್ತಲ್ಲ ನೇಮ್ ಇದು ಮಾಡಿದ್ರು.
ಬಟ್ ಇವಾಗ ವಿಡಿಯೋ ಬಂದಿಲ್ಲ ಅಂದ್ರೆ ನಾನು ಯೂಸ್ ಮಾಡಕ್ ಆಗಲ್ಲ. ಇದು ಇದಕ್ಕೆ ಚೆಕ್ ಮಾಡ್ಬೇಕು.
VLC ಪ್ಲೇ ಆಗುತ್ತೆ.
ಒಂದ್ ಸೆಕೆಂಡ್ ಕೆಲಸ ಮಾಡಿ. ನಿಮಿಷ ಹೇಳು. ಡಿಜಿಟಲ್ ಸಿಗ್ನೇಚರ್ ಹಾಕಿಲ್ಲ. ಅದಕ್ಕೆ
ಅದು ಇವತ್ತಿನ ಡೇಟ್ ಇದು.
ಇವತ್ತಿನ ಡೇಟ್ ಸರಿ ಎಲ್ಲ. ಇವತ್ತಿನ ಡೇಟ್ ಫೋಲ್ಡರ್ I getting from others from volunteers. I'm from Lab City. No, I get it. Hello? Yeah, I'm here. ಬೇಡ ಫೋಲ್ಡರ್ ಆಯ್ತಾ? ಅಲ್ಲಿ ಒಳಗೆ ಹೋಗು. ಕ್ಲಿಪ್ ಹೋಗು. ಅದು ಪ್ರಾಪರ್ಟೀಸ್ ತೆಗಿ. ಆಲ್ಟೆಂಟ್ ಮೇಲೆ ಡೀಟೇಲ್ಸ್ ಹೋಗು. ಡಿಜಿಟಲ್ ಸಿಗ್ನಲ್ ಹೋಗು. ಹೋಗ್ಬೇಡ ಅಂದ್ರೆ ಹೋಯ್ತು. ಇರು. ಇವತ್ತು ಆಲ್ಟೆಂಟ್ ರೋಡ್. ಡೀಟೇಲ್ಸ್ ಕೆಲವು no record. No laptop recording for hacker things. We can just point at the screen on. Okay, they're just gonna show that demos and all of this. It's going to be important. Okay, no, I can only send them a Google Meet link and record it. But the presentation, they don't have any presentation. They have both presentations and I can send them a Google Meet link and get recorded. How? I will send them a Google Meet link. Join the meeting. I didn't get the point. For a hackathon. Send a Google Meet. This laptop will not work. They have their own timing goals and calculations. So they will show that about that. So can't we make them join? That's what I'm going to. Yeah, that's fine. Yeah. Since you're going to speech, sorry, are you going to capture the whole video or what's the plan? Again, same movie. Just make sure that they join the same way. Sure, present it. Okay. And I would need your laptop to record the play. I'll enable the recording in the meet.
Yeah, that's what. That's it. Yeah, that time.
ಇದು ಯಾವ 30 GB ಫೈಲ್ ಐತೆ
ಟೋಟಲ್ ಬ್ಯಾಕ್ ಕೆಲಸ ಮಾಡಿದ್ರೆ ಎಲ್ಲ ಬಿಟ್ಬಿಡಿ ಆಗ್ತಾರೆ
ಇದಿಲ್ ನೋಡು
ಆಯ್ತು ಅವಾಗ ಕ್ಲೋಸ್ ಮಾಡಷ್ಟೆ
ಎಲ್ಲ
ಐತೆ ಬಿಡು ಯಾಕೆ ತಲೆ ಕೆಡಿಸ್ಕೊಳ್ತೀರಿ
ಎಷ್ಟೈತೆ
120
65
ಐತಪ್ಪ ಇದೊಂದು ತೆಗಿ ಇಲ್ಲದು ಇದಾ
ಇದೆ ಇದು ಇದಿಲ್ ನೋಡು
ಇರುತ್ತಲ್ವಾ 120 ಅಷ್ಟೇ ಜಸ್ಟ್ ಇನ್ ಕೇಸ್ ಬೇರೆ ಮೊಬೈಲ್ ಕಟ್ಕೊಡ್ಲ ಅವ್ರಿಗೆ
ಎರಡು ಮೆಮೊರಿ ಖಾಲಿನೇ ಫೈಲ್ ಇಲ್ಲ
ಅಲ್ಲ ಇದು ಬ್ಯಾಕಪ್ ತಗೊಳಂಗಿದ್ರೆ ಡೇಟಾ ರಿಕವರ್ ಮಾಡಂಗಿದ್ರೆ ಮಾಡ್ಬೋದು ಯೂಸ್ ಮಾಡಿದ್ರೆ ಡೇಟಾ ರಿಕವರ್ ಆಗಲ್ಲ
ಡೇಟಾ ರಿಕವರ್ ಬೇಕಾಗಿಲ್ಲ ಯಾಕಂದ್ರೆ ನೆನೆ ಇದ್ ಮಾಡಿದ್ದು ಇವಾಗ ಸಪ್ರೇಟ್ ಆಗಿ 2 ಫೋಲ್ಡರ್ ಮಾಡಿದ್ವಿ ಗೊತ್ತಾ ಮಾರ್ನಿಂಗು ಅದು ಬಂದು 2 ಫೋಲ್ಡರ್ ಕರೆಕ್ಟ್ ಆಗಿ ಐತೆ ಆಮೇಲೆ ಮುಗ್ದ ಆಮೇಲೆ ಸಾಯಂಕಾಲ ಇದ್ ಮಾಡಿದ್ವಿ ಗೊತ್ತಾ ಅದು ಮರ್ಜ್ ಆಗ್ಬಿಟ್ಟೈತೆ
ನೋಡು ಸೈಜ್ ಡಿಫ್ರೆನ್ಸ್ ಮಾಡಿ
ಬ್ರೋ ಅದು 2 ಬ್ರೋ ನೀನ್ ತಗೊಂಡಿದ್ ನಾವು ಇವತ್ತು ಒಂದೈತನ ಫಸ್ಟೇ ಬಂದಿದ್ದು ನಮ್ಗೆ ಇದು ಫಸ್ಟ್ ಆಫ್ ತಾನೆ
ಅಷ್ಟೇ
ಒನ್ 65 ಅಷ್ಟೇ ಇದು 61 58 ಒಂದಿತ್ತು
ಸರಿ
ಇದು ಜಾಸ್ತಿ ಬಂತು ನೆನ್ನೆ ಬಂದು
ಚೆಕ್
ಎರಡು 65
ಚೆಕ್ ಮಾಡು ರೊಕ್ಕ ಬಂದಿದೆ
We're not there even for 6 You're chit-chatting. You chit-chat for them. I saw.
No, we were talking about the
One word.
Sorry, bro.
Okay, one photo. One picture. Who will take? Yeah. I take. Come. Just like that.
He's not there even for a single moment.
That should that should record. That should be in the background. So that's yeah. Go back.
Yeah, I can.
Yeah, no problem.
Yeah, मैं भी आ रही हूँ अच्छा
ಆಯ್ತಾ objective memory card साफ दिख रहा है साफ दिख रहा है
क्या बोल
मतलब हम रहे
Camera is out recording.
yeah
Okay, it's okay.
ಅರೆ ಇದು ಕಟ್ ಮಾಡಿ ತಾನು ತೆಗ್ತಿರೋ ಅವರು
earphone
ಆ ಕ್ಯಾಮ್ರಲ್ಲಿ ಐತಿ ಈ ಕ್ಯಾಮ್ರಲ್ಲಿ ಇದೆ ಇಯರ್ಫೋನ್ಸ್
और मोहन ಅತ್ತೆ ಕೊಟ್ಟಿದ್ನಲ್ಲ
ಇಲ್ಲ ನನಗೆ
ಕೊಟ್ಟಿಲ್ಲ ಇಲ್ಲ ಮೈಕ್ ಜೊತೆ
ಕೊಟ್ಟಿಲ್ಲ.
ನನಗೆ ಇದೆಲ್ಲ ಚಾರ್ಜರ್
ಇಲ್ಲಿದೆ
ಶಿವಮ್
ಹಾಂ
ವಾಯ್ಸ್ ವಾಯ್ಸ್ ಸೆಲೆಕ್ಟ್ ಇರುತ್ತೆ ಏಕೋ ಸ್ಪೇಸ್ ಇದ್ದಾಗ ರೂಮ್ ಅಲ್ಲಿ ಇದ್ದಾಗ ಹೌದು ಇಲ್ಲ ವಾಲ್ಯೂಮ್ ಓವರಲ್ಲಿ ವಾಲ್ಯೂಮ್ ಇಲ್ಲ ಒಂದೊಂದ್ಸಲ ಸ್ಟ್ಯಾಂಡ್ ಹಾಕ್ಬಿಡೋಣ ಸ್ಟ್ಯಾಂಡ್ ಮೆಮೊರಿ ಚಾರ್ಟ್ ನೋಡಿ ಬ್ಯಾಟ್ರಿ ಬ್ಯಾಟ್ರಿ
ಬಂದೈತ್ ನೋಡ್ರಿ ಬ್ರೋ 1, 2, 3.
See, I don't say ये खराब आदत है बहुत खराब आदत है। I told you उसमें लोग को फुलाने के लिए भेजा था वो कुछ कर रहा था। मैं बोला ये ठीक है सब फोटो दर बंधु बोलते हैं what's kind of get on it and so on. It's not a man of his words. I mean, no, ये कुछ
They are all of it. Unlike other beaches, they are static with
Yes, I do. I don't have one. You want to come for? Yeah. Yes. Better can yeah. Same.
ಇದು ಇವರು ಪವರ್ ಬ್ಯಾಂಕ್ ಇದೆಲ್ಲ ತಂದ್ರ HDMI ಕೇಬಲ್ ಅದು
ಇಲ್ಲಿ
ಎಲ್ಲಿದೆ?
ಅಲ್ಲಿ ನೋಡ್ರಿ ಪವರ್ ಬ್ಯಾಂಕ್
HDMI ಕೇಬಲ್
HDMI ಕೇಬಲ್ ಇಲ್ಲೇ ಪವರ್ ಬ್ಯಾಂಕ್ ಚಾರ್ಜ್ ಹಾಕಿ ಬ್ಯಾಟ್ರಿ ಬ್ಯಾಟ್ರಿ ಅದೇ ಇದು ಫುಲ್ ಆಗಿತ್ತು ಇಲ್ಲ ಕೊಡಿ ಕೊಡಕ್ಕೆ
It is yeah. So they gave we all were supposed to wear it. But then what happened is I don't wear these shirts. So I told you that I'm very comfortable. So I got more from yes. Yes.
Yeah, bro. உன் பாடி சைஸ் எல்லாம் வச்சுக்கிட்ட உன் பாடி சைஸ் வச்சுக்கிட்ட 32, 33, 33 What are you doing? ಏನ್ ಬೇಕು ಕೊಡ್ಬೇಕಾ ಆರೆಂಜ್ ಸರಿ ಕೇಬಲ್ ಕೇಬಲ್ ಅಲ್ಲಿ
ಯಾವ್ದಕ್ಕೆ ಅದು
ಸಿಪಿ ಅಲ್ಲ 5 ನಿಮಿಷ ಮೊಬೈಲ್ ಚಾರ್ಜ್
ಮೊಬೈಲ್ ಅದಾಗುತ್ತೆ ಫಾಸ್ಟ್ ಆಗುತ್ತೆ
ಇದು ಫಾಸ್ಟ್ ಆಗುತ್ತೆ ಇದು ಸ್ಲೋ ಅಲ್ಲ ಸಿ ಬೇಗ ಆಗುತ್ತೆ ಹೌದಾ ಹಾ
ಇಲ್ಲ ವೈರ್ ಮೇಲೆ
ಇದು ಸ್ಯಾಮ್ಸಂಗ್ ಸೋಡಾ
ಫೋನ್ ಚಾರ್ಜರ್ ಕೊಟ್ಟಿರಂಗಿದ್ರೆ ಹಿಂಗೆ ಇಡಿ ನೀವು ಫಾಸ್ಟ್ ಚಾರ್ಜರ್ ಬೇರೆ
ಹಾ ಹಾ ಹಾ
ಡೈರೆಕ್ಟ್ ಆಗಿ ಅಲ್ಲಿಗೆ ಹಾಕಿ ಪವರ್ ಬ್ಯಾಂಕ್
ಶೂಟ್
ಚೆಕ್ ಚೆಕ್ ರೈಟ್ ಚೆಕ್ ನೆಕ್ಸ್ಟ್ ಏನೇನು ಇವಾಗಿರೋದು ಸೆಷನ್ ಚೆಕ್ ಮಾಡಿದ್ಯಾ ರೈಟ್ ಏನೇನು
ಸ್ಪಾನ್ಸರ್
ಕಾನ್ಸೆಪ್ಟ್ ಬೇಗ ಏನಿಗೆ ಲೈನಿಗೆ ಫಸ್ಟ್ ಇದು
ಇರೋ ನಿಮಿಷ ಲೈನ್ ಯಾಚೆ ಉಂಟು
ಅಲ್ಲಿ ಹಾಕಿಲ್ಲ ಹೆಂಗ್ ಬರ್ತು ಚಾನಲ್ ಆಟೋಮೆಟಿಕ್ ಆಗುತ್ತೆ
ಇಲ್ಲಿ ಬಾಸ್ ಇದಾಗುತ್ತೆ ರಿಸೀವರ್ ಅಲ್ಲಿ ಅಲ್ಲಕ್ಕೆ
ಇದೆಲ್ಲ ಹಾಕಿದ್ರೆ ಆ ಕಡೆ ಹಾಕ್ತಾ
ಟೈಪ್ ಸಿ ಹಾಕೊಳ್ರಿ ಬ್ರೋ
ಟೈಪ್ ಸಿ ಎಲ್ಲ Pradeep. Pradeep. ಈಗಪ್ಪ ಕೇಳಿಸ್ಕೊಂತಿಲ್ಲ ಅಲ್ಲಿ ನಾನು ಸ್ಟೇಜ್ ಮೇಲೆ ಆಡಿಯೋ ಚೆಕ್ ಮಾಡಿರ್ತೇನೆ ಇದು ವರ್ಕ್ ಆಯ್ತಿದ್ಯಾ ಡಿ ಜಿ ಐ ಹಲೋ ಯಾಕೆ ಡಿ ಜಿ ಐ ವರ್ಕ್ ಆಯ್ತಿಲ್ವಾ ಸರಿ
ನಾನೇ ಟ್ರಾನ್ಸಿಷನ್ ನೋಡ್ಬೇಕು ಹೊರಗೆ
ಹಲೋ ಹಲೋ ಹಲೋ
Pradeep, how's the what's the sponsor setup? No, only video or the
Just video,
PPT is
just video.
No,
No PPT. Yeah.
this one. So it's a button. So this one. This will be for you. How would I just wait? You can just yeah, hello, yeah.
Hello everyone. I now welcome you on to the sponsor presentations. We'll start with the first presentation by Pankaj from Qualcomm.
Yeah, hi everyone. Think very sparse audience, but that's fine. It's the conclusion of like the second day. But I think we have the hackathon, so I think more people would be interested in that. Uh, so this particular conference has been interesting for me, and I think for Qualcomm also it was slightly interesting, I would say, because we had around like 5 speakers, I would say, including one poster, and this is the best our team uh, would represent at any conference. So it's a big thing for us. I think, I don't know if everybody got a chance to see the presentations on this five. We had one on ELD, one on the plugins, and there was one on the vectorizer also, uh, poly work which we have done. So I think what I would say is we have covered almost most of the projects on which we work at Qualcomm. The two things which like we were not able to present is what I would cover here. So, and that is the most interesting one, I would say. So the interesting one is the hexagon and the NPU. So they used to call it DSP with when the same DSP gets used for different workloads, the name changes. So that's the NPU. So I'll talk slightly about that, and I'll try to also introduce what kind of MLIR work we are doing for this particular NPU. So far, I think we have had a lot of presentations on MLIR. I need not go into what it is. Everybody understands what MLIR is. So there is a challenge for us when it comes to running these models on NPU. So before I go to that, maybe I'll ask a question. If has anybody earlier heard about hexagon NPU? Anybody new? Okay, good. At least 3, 4 hands, so that's okay. Thank you. And do you know there is something called as Qualcomm GitHub where some models are hosted and you can run them on the, you can rent the devices and run on that. If any, does anybody know that? I was expecting zero, so that's that's expected. So because that is the work is still under progress. So I think what happened as Qualcomm over the 2 years, like I have been witness to that, is they have moved away from being a downstream only company to like giving access to people so that their hardwares can be programmed. So that's one different approach which has happened. And mostly we have been speaking about hexagon, how you can program or not. It's actually difficult to program it. So I was talking to one student from Triple IT Hyderabad, and he has been able to. He's now working in some other company. He has been able to program hexagon with just the online documentation. It's a big thing. So, and it's a big thing not for people outside. It was pleasantly surprising for us also that how somebody can do that. So, and don't want that kind of experience. So that's something we want to change, and it's a progressive step. We are going slowly. So, uh, to summarize, the compiler team for which I work on it caters to multiple architectures. For example, so we work for microcontrollers, we work for this DSP, we work on the ARM CPU also, and we have also one MLI team. So which I will talk about right now. So the challenges are interesting. I liked it, so that's why I'm there in that team. So and we get exposed. It's a close team, around like 30 engineers, so we get exposed to all the other compilers also. So when let's say I'm working on the RISC-V, it's not like I don't know about what's happening in this MLIR, or I don't know what's happening, what's happening in the ARM world. So I get exposure. Our folks also get exposure to that. So so that's a good part. So going to one use case, I would like to share a recent one. So did anybody watch Avengers Infinity War, the scene where Tony Stark says, calls Friday and tries to get some information? I hope everybody should have watched. It's an iconic movie. So Justin, you did watch. So what's interesting about that is in cinema, what ideas can come. So if I look at that as an engineer, for me the idea is about the glass, how we can do it with the glass. So that was very interesting thought, that will it come in real life? And recently, if you would have seen the news, there is the smart glasses by a popular company that has the Qualcomm chipset AR Gen 1. I was surprised, amused, and I saw multiple articles, and everyone was like, "What? This is a nice thing." So what was nice in that was you are not running the models on the cloud and getting the information. You are running it on the device, on the edge. So is it really possible? They made it possible, of course. So what kind of models are run on that? So then we have to understand what use case is also there on the glasses. So what you will say on the glasses is, okay, whoever is the speaker, just show me his profile. So then you will need that lens, maybe kind of a binocular lens, where you can see let's say Pankaj Good is there, what all he has done since how many years he has been working, all that you can see. So you need that lens. You need, maybe you need something to, uh, some kind of device or some interface which reads that for you also. So you'll say, okay, read that for me. So now I think you are understanding what is happening. You are giving it a command and it's translating it on the fly to give you the data. So that's an interesting use case. By the way, this particular work which I'm talking about is still under development. So it's not used in that particular project. So there is a Hexagon SDK which is used for doing inference on the glasses. So that's a different thing. But this is something which is under development. Generally, like we see companies talking and they will say, oh, this is under development and I don't want to reveal that. We are like, okay, this is under development. Get some ideas. If you have something, please let us know if you can solve it in some different way. So, so in this case, our problem statement is to develop this open source compiler for ML applications, of course, for NSP. The challenge here for NSP is, if you see all the models, everybody has talked in these 2 days focusing on GPU. What if you want to run the models not on the GPU, on this kind of device? So what is the challenge with this device? So the challenge with this device is power efficiency. You want it to be very power efficient, because on the glasses you don't want it to heat and your brain to fry up, right? You want it to be very power efficient. You can get your data. So again, I don't think you would have read, but on the glasses, the model which is run is the small language model. I wanted to know what kind of small language model it's running, and I was surprised it's running Llama 3.2 1 billion parameters. I will, what? Llama 3.2 with 1 billion parameters? Awesome. On NSP. It's a good thing. So means what I want to say is, like, the NSP has become efficient to run such models also, where you can do that image processing on the glasses. So the challenges which we have here are this block diagram. If you see, is this is not available much online. So this, but you can derive it. It's not a big thing. So interesting part here is, if you see, there is a scalar processor, there is a vector unit for vector operations, then there is a tensor unit, and you have memory processing also. Now these components all are dependent on the VTCM, how efficiently you use VTCM. So if you see, this is a shared memory between vector unit and tensor unit. So if you use it efficiently, then yes, you are doing a very good job. If you are not doing it, then there is a problem. Your power efficiency goes away. So this is one of the problem we are looking to solve when we are trying to develop this compiler for ML applications on NSP. So the engine, the overall Qualcomm engine, AI engine, which we call, so that has, I don't think this diagram is much visible, but I'll just spell it out. So you have the NPU, you have the GPU also, of course you need that. You have the CPU, and you have a sensing hub. So all these are required for doing any kind of inference on the edge. So here again, as I was saying, the challenge is NPU and how you program the HVX. This is slightly difficult right now. We are working towards making it easily programmable. So this is the target hardware for which this particular problem we want to solve. Now, MLIR is, I think, something we have. I was saying, like, we have been hearing about it from everybody. What we are interested here is the DMA generation, the memory management, the vectorization. That is of interest for the NPU world because of this shared memory architecture, right? Which I was sharing about. The VTCM is limited, it's fast, it's shared. So that's the challenge we are looking to solve. So how do we solve that? This again, I think this is, we all know, it's like about dynamic shape, sparsity, all that problems everybody knows. So this is the AI stack, which again we are all familiar with. So there are three areas where we want the AI workloads to, three areas we should address in order to support AI workload to run on NSP. So one is doing the core MLIR development. So what we want to do in this is we want to develop some kind of dialect. Dialect, I think, is now very native to India because every 100 kilometers we have a different dialect. So not surprising that we end up creating so many dialects. So in this case, now we are creating a hexagon dialect. Then we would also be creating a Triton MLI development workflow. And finally, the overall torch MLIR development, where you have a torch model and it goes through the full flow. So this is the high level flow we would be looking at. So when we want to support Triton workflow, so you have a Triton custom kernel. It can be optimized, it may not be optimized. It gets converted to a Triton dialect, and we are not directly converting from Triton dialect to a hexagon dialect or a custom backend dialect. We want to leverage on the lineage dialect. The reason is it offers your tiling, fusion. Those are very important for the hexagon dialect. So that's why we had to introduce this in the workflow so that the hexagon dialect gets benefited. So this is a typical four-step flow. You have Triton dialect, lineage dialect, then the hexagon dialect, then the LLVM dialect, which then runs on the LLVM hexagon compiler, goes on to run on the NP. The binaries goes on to run on the NP. So this is the flow we are targeting for Triton. Now, currently what we are trying to do is we are trying to develop this hexagon dialect where again the challenges are similar, like addressing the multi-core, multi-threaded parallelism, vectorization, how you can map your workload to tensor unit. That's also one area we are looking to solve with this hexagon dialect. It's a challenging area because I was saying, right, there is a VTCM which is shared between both tensor unit and the vector unit. So we have to map the workload such that you get the most efficiency. So when this slide was made, so we were looking at hexagon dialect, but now we also have introduced something called as a hexagon memory dialect, which takes care of DMA operations, transferring data from VTCM to DDR. So those operations are included in the hexagon dialect. This is still under development. As I was saying, this whole project is under development. So anything you want, you think might be interesting, you can talk to us, maybe contribute some way. I think soon this work will be upstream. So then the final part is running the overall PyTorch model, supporting the PyTorch workflow, wherein you have your PyTorch model going through the full flow of getting a Triton kernels in Triton, which you can go through the flow which I had explained earlier about, like going through the Triton dialect, the lineage dialect, and the hexagon dialect, and making it run on the hexagon NPU. So this is the work which it's under development. So if you have any questions or doubts about it, please reach out. It would be nice interacting and getting to see if we are missing out on some obvious things. But here, as I was saying, the challenge is managing the memory between the tensor unit and the vector unit. So that's all I had. Thank you very much.
Thank you. We now have Samira with us. Samira from Audrey.
एयरपोर्ट अच्छा You can tell it. Yeah. Okay. I'm in Hong Kong only, like Oval, Bangalore, Oval, like they won't take. How is this explain hands? It's short.
Just use the button mic here.
Okay. Okay.
Use this to switch between slide.
Oh yeah, I'll have to play. Okay, perfect. Thank you so much. I can do it from here as well, right?
Oh, okay.
Okay, perfect. Yeah, thank you.
Hi, good afternoon. I'm Samira Deshpande, Principal Software Engineer at Quadric INC. We are pleased to be sponsor at ISCT this year and hope you all enjoyed last 2 days of the conference. Quadric is uh, a developer and licenser of unique domain-specific processor. So we do not really build the chip, but we license our IP, and we are pure play semiconductor IP licensing aimed at AI inferencing. So this is we are based in Silicon Valley. Offices in Burlingame, California, um, and this is the first chip that we built as a prototype, but we no longer build a chip. So we like to just show this chip because this is the first time we had a POC that this concept actually works. Um, so we license our Chimera GPNPU, which is General Purpose Neural Processing Unit, to wide range of silicon design teams around the world. And because our customers are in diverse range of applications, we have different chipsets to cater to their needs. So, for example, Nano is for 1 to 7 AI tops, then P, which is Perform for 4 to 28 AI tops, Ultra is for 16 to 108, and then we have Multi, which can go up to 800 um, teraflops. So this is NPU for us. Um, so yeah, because we have what has happened? Oh, okay. So because of these wide ranging applications, we have different variations in the architecture. But overall, the architecture layout is pretty same for us. So let's start with the most important part for any NPU, which is the MAC unit and then some local memory, right? So that is MAX and LRM for us. Then to add to that, we also have a register file where local computations can happen, and then some 32-bit ALU operations, which we can perform in parallel to MAX. Then in addition to that, our processing element, so this is called as a processing element. Each processing element is connected with its neighbors. And so there is a neighbor access, and then there is a DMA control provided to this. And then there is a, if you look at the instruction, it is combination of compute instruction and data movement instruction. So we can, single instruction can initiate a compute operation as well as data movement operation. So now this is our PE, and it sits in, yeah. So this PE sits in array of processors that we have, and depending upon how many, what is the size of this array of processors, so depending upon size of or dimensions of this array of processors, we have the configuration of N, P, U, and all, right? So now this is our whole architecture. We call it Chimera because you can use the architecture for, so different parts of the architecture is capable of doing different things. And so it is Chimera GPNPU. So if you see here, we have a single instruction. Okay. Okay, yeah. So we have a single instruction port, then there is a data movement. You can notice that there is a local memory, which we call LRM, which is sitting in each PE. In addition to that, there is a on-chip L2 memory, and then there is a external connection to the external memory. So there is a hierarchy of memories that we have, and that poses another level of problems for the compiler. So yeah, we are scalable from 1 TOPS to 860 TOPS, depending upon how many Ps we have and how many such cores we have in the multi-core processor. So to exploit power of our architecture, um, we need the best compiler to support our architecture, and this is how we have implemented our compiler stack. So the Chimera graph compiler is at heart of our the compiler stack. So the CGC takes input from either the PyTorch in form of Onyx, or from the ChIPy compiler, which can again generate a relay input for us. Then the Chimera graph compiler generates C++ code. Then the users can also write custom operators or DSP application code, and some function libraries are there. So all can be compiled using Chimera LLVM compiler. And then we have a Chimera ISS, where our code can be seen running, or we can have a target silicon with Chimera GPNPU, sorry. Because Chimera graph compiler is at heart of our software stack, I'd like to talk more about the graph compiler. So yeah, so we take Onyx as input, then we have we do some graph analysis on the input, some graph simplification and canonicalization, and then some local optimizations like graph propagation on it. Then there comes the actual graph optimizations, which are very target specific for us, right? So there is some requantization and rescheduling happening. Parallel graph serialization happens, and then we can fuse some of the operators and select the implementations to minimize the data movement cost. In such architectures and such applications, data movement cost is far more than the compute cost, and so these optimizations play a crucial role in generating the optimal code. Then because we have multiple layers, 3 layers of memories, the memory optimization becomes quite important for us. So we have to pay attention to the tensor format layout analysis, and then intelligent weight prefetching, for example. We have to do that to optimize on the time taken by the data transfer. So this is CGC's high level architecture. We use TBM project as a base for our CGC. And then we have architecture aware quadric specific middle end, and then there is a direct mapping from the EPU relay, that is our architecture's relay code, into the TIR generation, which finally generates the C++ code for us. So to see what we were able to achieve. This is what we have already supported in our CGC. So you can see there are 74 ops from Onyx that we have already supported. We have added few algorithms in SDK so that that support is there. So you can see that even though our hardware does not need to change, if new algorithm comes in or if new feature is added or new neural network comes, we just have to add a support in the software in any layers of this to actually get the implementation and things running for us. So if you have any questions, if you want to know more about what we do at Quadric, please reach out to me. So these are the planned optimizations, but because short of time, I cannot go over that. Please reach out to us if you want to know more about us. Visit our website. Thank you. Thank you, Samita. And thank all our sponsors. And with that, I hand over to Amisha for another interesting session on hackathon presentation.
The hackathon presentations. All the teams who are all the teams who are presenting today, please come and be seated in the front row. And I also request the judges, Uday sir, Dixie sir, and to please come forward and
कॉलर में
हमारे पास नहीं कैमरा वाला
arrange get A4 sheets and pens. So 6 A4 sheets and pens. Yes. Which team is first? So up first is team We Don't Know LLVM. Please come on to the stage and get ready to present. Plug it in here.
Yeah. And under the scenes, every place is once there are plans. Just
from the teacher. I don't know LLV.
Use this along with the mic
Right.
for the camera. And you can
Flip it here.
yeah, this is a magnet.
Something when you can. Yeah, I want to.
So just explaining the format, each team has 6 minutes sharp to present. At 6 minutes, you will stop presenting, and the rest 4 minutes are reserved for Q&A.
What?
Well, I don't know. I never texted.
What do you know? So what?
It's kind of what?
Mirror the screen here.
Oh, there's a screen to the other side. Okay. Oh, wait, do you have Linux?
Yep.
Okay, then this the exit to the
Just skip the report. We'll skip the comparisons with BPF race. We'll shave off 30 seconds.
Slides here. Just one second, 1 second. I just wanted to your name is Viron LLVM, right?
Yep.
On chat room, maybe we could take this. Just tell me, don't share it on. OP. I think.
There's things going on.
Oh, yes. Yes.
We look express data path, then Chrome.
So you have verified that they started 1 month ago. Okay.
तो बोल रहे हैं we verified 1 month वाला.
We don't need like
Perhaps, okay, it's on. So we'll go through it. Uh, okay, we can. I will be speaking, so we'll go through it. So yeah, I guess it works. We can turn this off. It's fine. So
Okay, we start. So,
okay, we can.
hi, we are
I will be
Pragyansh and
speaking.
Varun from team We
So
Don't Know
we'll go through
LLVM,
it.
and we present Python
So
BPF, a
yeah, I
Pythonic
guess it
front end to
works.
write BPF
We can
programs.
turn this off.
A quick primer on what is BPF, a kernel subsystem which allows custom programs to run in the kernel space, provided they Okay, we conform start. by the rules of the
So
BPF verifier.
hi, we are
This is
Pragyansh
helpful
and
in
Varun from
networking,
team We Don't
monitoring,
Know
kernel
LLVM, and we
bypasses,
present
and
Python BPF,
observability,
a
a
Pythonic
Pythonic
front
front end
end
to write BPF
to
programs.
turn this off.
So we'll
A
focus on
quick
BCC,
primer on what
which
is
allows you to
BPF,
write
a
BPF
kernel
programs in
subsystem which
Python.
allows.
And there is a big problem with BCC. It's inline C in Python. And if we take a closer look at the syntax, we see more than half of the file is C of this basic example, which can't take advantage of a Python LSP and the linters. Also, this is objectively ugly. And this leads us to our problem statement. Make a truly Pythonic front end for BPF programs. It will be easier to learn and can take advantage of the Python ecosystem. Next. Next. And this is a side-by-side view of the same function. Left is Python BPF and right is BCC. You can see the difference is night and day. We get an easy to learn, truly Pythonic way of writing eBPF, which can utilize the Python ecosystem to enhance developer experience and data processing and visualization. And why did we choose Python over designing a new DSL? Because everyone already knows how to write Python. All BPF logic is written in functions decorated by a BPF decorator. We support pointer, integer, and string types and try to convert them to desired types when passing them as an argument to BPF helper functions. Next. And under the hood, we translate pure Python to an AST using Python CST module, so we don't need to write a parser. We check for the decorator function, lower those chunks to LLVM IR using Numba's LLVM Lite project, and then use LLVM backend to lower it to eBPF bytecode. And how did we design our syntax? We took the BCC examples, then we converted those programs to reduced C and tried to write them semantically in Python and created a Pythonic syntax for that. So a reduced Python used to write BPF programs. In the same file, we can write pure Python as well. And next, we'll skip over this. These are fine-grained. No, here. Right now, these were some to-dos we decided to do during our first eval on 14 September, and we are happy to tell that we achieved them. And we are still a long way off because we need to use the vmlinux.c generated from target machine to access kernel structs and kprobes. So, okay, next. You can try it out yourself. It's open on PyPy, and we are open to feedback and bug reports. And we'll talk about some of the traction this project got. We reached 130 GitHub stars within the first 3 weeks of the opening commit. And one of us blogged about this on our personal website, and that attracted some attention on Hacker News, Python Weekly. Isovalent gave us a shout out. We were reached out by many engineers working on BPF to give their review and discuss future direction of the project. We plan to refactor it, remove the ugly bits, and make it production ready. And now we'll move to the demos because we planned for 7. Yeah. So the first one is an express data path, not the hello world, express data path. Express data path example. It's an example with 3 sub-examples. Where we first send packets to a network network interface. It will read it, increment a counter, and then send an ACK back to the source. And in the next example, it will accept
network packet, increase the counter, but not send an ACK back using HTTP drop. And in the third example, it will only send ACKs back for the first 10 packets, and then it will start dropping packets. So we'll run these examples one by one. So for the pass-through first example, and then we ping another computer at our home, connected on the Tailscale network, ping a home node. So you can see the ping packets are going back and forth. On our computer, we can see the BPF count, BPF program increasing the counter, and the ACKs are also going back. We have a good amount of packets sent. Now, the packet drop example, if we ping our home node again, and we wait for some time, yep. So now we can see that the packets are being registered here, but we are not sending ACKs back to the home node. So on the home node side, those packets are being seen as dropped. So if we stop it now, we see 100% packet loss because the packets will be being dropped. And in the third example, you'll see packets go till the 10th count, 11th count, and then start getting dropped. So yeah. Please. Yep. So you can see the counts increasing on our side, but we have stopped sending ACKs back. This was all in Python. Next, we have an example of matplotlib being used with Python BPF, where we are tracking all the number of clone syscalls made within a session of 10 seconds by different processes, and create a frequency graph where we show the number of processes which issue X number of clone syscalls. So right now we'll open some terminals to simulate stimulate those syscalls, and you can see the number of processes, and there are a lot of processes, more than 500, doing one or two clone calls. But at the end of the right end of the graph, you can see some processes doing an unusually high number of clones, and we believe that it would be the number of the new terminals we opened, because that was the only significant thing we did in the last 10 seconds. And we opened 5 terminals, so it's kind of the what yeah 5 anomalous PIDs found with more than 40 clones. If we redo it with a different number of terminals, so like if we restart the whole thing, yep, stop. Yeah, we'll just do it again. So, and we do it a different number of times now. And then last cell, this time it was 7 windows. So yeah, we have found the culprit of that. The culprit was the terminal process issuing an enormous number of PIDs. There are more demos where you can visualize PIDs issuing a number of open access calls and things, but we'll just do it. We are open to questions now.
Okay, so that concludes that questions. So one of the important considerations for anything to do with kernel is the efficiency. So how does the time of how does the code that you generate with this compare with the code that used to be generated with the earlier uh, EPBF notation?
Yeah. Right. So here are two things. First is that eBPF code, the eBPF bytecode generated, does not account for a lot of performance hits by itself, because those programs are very small and don't take a lot of CPU time. Also, the most of the performance bottleneck in all of these things is reading things from kernel maps, IO, and sending data from kernel space to user space. That's the biggest bottleneck. For that, we are using Python bindings for libbpf, and libbpf is the way of doing this using C as well. So that bottleneck stays the same as in C. And for our BPF generated code, what we are doing is generate LLVM IR and let LLVM backend do the heavy lifting of optimizing things to BPF bytecode. And then kernel has a JIT compiler for different backend architectures like ARM, x86. So BPF to the final thing that runs on the kernel VM is done by kernel developers themselves. We asked about this from some kernel maintainers that should we actually think about efficiency in our case? They were like, no, that's the job of the LLVM project and the Linux kernel project. You should first focus on getting clarity with the VCC project. Uh, make it accessible for developers first so that it attracts a wide audience, and then think about things like performance.
So with the LLVM IR that we generate is close to O2. It's a we modeled it on O2. So
Fine. Thanks for the nice presentation. So one question I had is what fragment of Python you support in this translation? Do you support lambdas and
No, so this was in one of the slides which we conveniently skipped because in the interest of time, this was the reduced grammar that we support for now. There are some changes to it that we have added support for structs as well. So if we declare a data class in Python, that can be translated to a struct. The only restrictions there are that the struct fields can only be string type or one of the integers, unsigned, signed, 32 or 64-bit. So you can make those structs. Those are converted to an LLVM IR struct type. For strings, we use pointers, and for ints or pointers, we use their respective types in LLVM IR. And apart from that, this is the grammar that we are using.
and we do plan on continuing to write more of this.
essentially you wouldn't be able to do anything that allocates on the heap, right? So because Python runtime is not there, you can't do garbage collection and all of that. So essentially there is a small subset of Python here which can be converted to the underlying BPF
Yes.
thing.
And anything which is not decorated by a BPF decorator runs via a normal Python interpreter. So if it is not BPF specific, we offload it to a well-known Python interpreter.
So up next, we have team Blank Point with Edgeflow, which is a DSL for Edge AI pipeline. I also request team Captain IRS and Team Q to come forward. Mr. Yes. Thanks. That's more.
Okay. Good afternoon, everyone. We are Team Blankpoint, and we are here to introduce EdgeFlow, which is a DSL that transforms the way AI models are deployed on Edge. Our goal is simple: to make the deployment as easy as writing a config file. Today, today, deploying AI on edge devices is a messy, fragmented, and error-prone process. Developers face too many problems like hardware diversity, complex model optimization, no feedback loops, and this results in misconfigurations, failures, wasted weeks, and hours of debugging. Edgeflow, this is where Edgeflow comes in. So Edgeflow provides a simple declarative DSL with a human-readable script that deploys to any device with a single config. No or minimal ML knowledge required. No PhD level knowledge required for quantization device. You just have to write a simple config file. Avoids vendor lock-ins and manual errors, and it always also leverages built-in optimizations, making the deployment universal, efficient, and reliable. So this is our declarative DSL. You can basically configure model path, framework, and target device. If you want, you could also configure the optimization settings, resource constraints, deployment configurations. So how does it actually work? So the architecture is pretty straightforward. We ingest a model and we have a multi-format model support that supports like TensorFlow, PyTorch, and other frameworks. Parsing and validation is done. A canonical IR is generated, and then we have optimization passes. Our optimization engine runs various optimization passes like quantization, pruning, and operator fusion to generate device-specific code, which is then deployed to the edge devices. Our benchmarking and explainability module generates reports for clear and transparent reports, and then the developers could iterate through this process, making it a lot faster. The what does our actually compiler do, and what are all the abstractions that our DSL provides? So our DSL provides universal multi-framework support through canonical IR. It 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 takes inputs from various model frameworks like TensorFlow, PyTorch, ONNX, and transforms it into a single canonical intermediate representation, enabling a seamless optimization. Next, it does is like semantic validation and optimization. It catches the errors very early. For example, the mismatches in shapes or illegal configurations, and reduces the time taken for debugging errors. It is adaptive, so with minimal inputs, you could target your optimizations to the target devices without providing like specific details. What are the other core features that we have other than this? So we have automated optimization pipeline. Like I told you, just need to configure the target device and some other basic details. Other things would be automatically optimized by RDSL. Integrated benchmarking framework, which generates the reports and provides a clear detail of how throughput and latency were measured. We have hardware independent validation, so you don't need to have a particular edge device with you to test the models and run them and check its compatibility. So let's see the results now. We improve in terms of shorter deployment time. A lot of time is improved in checking the manual errors also, because we check the errors much earlier than deploying and actually running the model on edge devices. And again, the iteration cycle is done much faster because the optimization process is reduced from weeks to minutes. So what is the change and comparison with current tools? So time and complexity reduction, like I told, the tools currently take a lot of time and are fragmented. Edgeflow provides a seamless process, converting this expert tuning into 5 minutes. Then we have various vendors, but they are specific. For example, TensorRT for NVIDIA GPUs, but Edgeflow is universal. It would work from Raspberry Pi to to microcontrollers. And again, it is an intelligent and manual work, uh, intelligent versus manual work. So the traditional way of writing, fine tuning everything like specific details is much reduced to a simple config file. Now we'll be presenting the demo video.
So yeah, the story of H2 starts with a really frustrated ML engineer called Madhur. Madhur is sitting in his home and he's breaking his head over trying to optimize and deploy and fine tune his ML models So this is where edge flow comes in. We start off with a really simple config, very simple to write, and we also have a front end for, for demonstration purposes, we made a front end. The front end, in one single click, after writing a config file, it generates codes in all languages. It performs hardware-specific optimization. It also generates and displays the benchmark results, as you can see. Yeah, the difference in time is really visible. H2 also handles. Okay, it's there. Sorry. So H2, while running H2, it does perform, it does check your model for compatibility, and it also performs semantic validation. Mhm. So this is the demonstration of when you use H2 to deploy a large ResNet model on a Raspberry Pi 4.
Let me fast forward this.
1 second. For the closing statement, thank you all. This is team 1 point. Please feel to check out the platform, the front end for this. We have it on our PPT, which is right. Where is it? Yes,
We can begin with the Q&A.
yeah, we're open to questions.
So I have two questions for you.
Yes.
The first question is, you have designed a configuration file which is very nice. What guarantees do you have that you have covered all parameters that would be required? Everything that can be configured is covered. That's one question. Second question is, you talked about an IR which can cover many frameworks. So what are the main abstractions in your IR? These are the two questions that I have.
So the configuration, first of all, we we researched and saw that there are some standardized configs that are needed, like for the agile deployment. So all those configs are particularly mentioned in our DSL, and like the basic configs you need to specify, like whatever your target device is, and um, like if you need like for some optimizations and fusion pruning. But the other things, like what the things that are device specific, we have a device profile library where we fetch all the details from. So like for most of the devices we have that, so we could fetch the details from there.
And the second one is canonical IR, which supports multiple framework. So what we did was we selected the things which suppose for TensorFlow or ONNX or the PyTorch, we made separate IRs for each of them, and whichever it goes by that path.
Separate IR for each one.
Yes. Yes.
ಅಲ್ಲೇ ಪಕ್ಕದಲ್ಲಿ ಕೂತಾವ ಆಸರೆ ಕೂತಾವ
Yeah, for the DSL we are using ANTLR to
Like
yes,
the
yes.
RLF of us.
Thank you. Next up, we have Captain IRS with ESP line, which is a vector processing language for high bit vectors. In Captain IRS, please come to the stage.
Automatic. Yes, we want it to be convertible. This is considered. Ah, you're right. Yeah, it's just what I have that. What? Date no, 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 date. Okay, okay, fine. Sorry, yeah, well, then what? Yeah, that's good. Literally, sorry, was kind of the brain is function. You have to get right. What? Go to display, display. Settings display. Yeah, just mirror the screen to that. Just keep it. Should we connect the yeah yeah directly connect the HDMI yeah into port. Okay, yeah, display it again. How it is. That's interactions. Can you go to display settings? No, this is Ubuntu. No, no, this is search. This is display settings. Display settings. You know, wait. Wait. We remove the next presentation and then yeah, we'll go to next one. We'll go to next one and come back. It doesn't go there. What I managed some technical difficulties and that's the team will present. Yes. Yes, you can see them from the right, right, so oh, I thought so usually project is the debug direct for employer. Okay. 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 That's okay. I think we need this. Well, doesn't need to get up. Yeah, yeah. Then yeah, you didn't share this. So, yeah, yeah, sure, but I need to show the demo also. Yeah, this. Right? And next to the mirror. Can you mirror? Yeah, that's one. Connected. Wait. I think it's extended. Can you mirror? That's how it's came this mirror. How to do that? Maybe I can extend it to the. You can extend yeah. Just copy it to. Mm. Yeah. And so now so. So people. Sure, sure, sure. Hi all. Yeah, hi all. So I'll be presenting a debug dialect for MLIR. So before going into why we need an MLIR debugging dialect. So why we need a debugging dialect for an MLIR? So whatever you see over here,
Yeah.
So this can be considered as MLI or valid MLI code. So what it does is like it's basically a gem. It's doing a general matrix multiplication. It is using affine dialect and added dialect. Some of the standard dialect that's MLI supports. So the major issue with this MLI IR, this intermediate level is like you won't be able to know what's inside this IR. So at the end of the day, whatever you're doing, it will be lowered down to some LLVM at the end of the day or some other hardware specific IR. But you won't be able to see. So why this is important is like you will be writing the code to generate this code. So uh, if you don't, so basically this is a black box. So if you don't know what's happening with this, essentially you don't need this particular capability for MLIR. But if somehow we were able to know what's happening with this percentage zero, what is this percentage one at runtime, it would be great. So if you want to know what's the value of arg zero, that is all that has it as a runtime, it would be great. Or you want to know whether your loop is running at all. So if you're accidentally accessing any out of bound memory, so all those things you won't be able to, as of now you won't be able to query all those things from this particular IR that your code generated. So so why it is hard is like uh, for MLIR. So in MLIR we have something like an operation and the regions. So whatever we have is like operation, and whenever you create an operation in MLIR, you need to pass location information. That's the only debug information that the MLIR right now support. Then that's much more than needed. That's the thing that we need right now. But with just the location, the only debug information that you will have is like whenever your pass fails, your conversion pass fails, you will get a message saying that your pass got failed due to this particular operation that was in this line number in the source code. So that's the MLIS debugging works these days. And you can say that you can lower it entire thing down to LLVM, and then once the LLVM IR is there, you can basically debug the code. So there is also a case like you won't be able to debug the LLVM IR generator. Maybe you can debug the source level code, that's C or C++, or you can debug the machine level code. But in order to step through the IR, that's still not there. So that comes to the solution that we propose. So so what we propose is like if you want to know what's the value of arg0, you can simply write array.print. So array is the dialect that we developed. So you just need to say that array.print, and if you want to know what's the value of array arg0, you just do this. Just like what we do with the C++ code. Whenever you have a segfault in your C program, what you first thing that you do is like you will just do a small print. Or if you want to know whether your loop is running, you just want to do just like what we do with C++. You just need to print whether the thing is working or not. So for that, if you want to do some out of bound memory access, you just need to add an assert. So uh, this is what we propose. So why this is helpful? This is damn helpful for people who write passes and conversion. So almost all the MLIR project deals with some kind of passes or conversion. So essentially, if the array dialect or this debug dialect is not there, essentially this MLIR layer itself is a black box. What our dialect does is like it makes this black box a glass box. And obviously, so when I started working with MLIR, so my major concern was why I can't have something like a hello world program similar to what we have in C, C++. So that thought, and even writing some advanced transformation or passes, what I found was like if we have something that can show what's our operation that we have generated can do at the runtime, then that's going to be extremely helpful. That's how we came to this project, and we have already started using this dialect in our academy, in our projects. So maybe I'll go through a demo that will give you better understanding. Yeah, so right now we have a normal uh, gem file that we have shown the thing. So you just need, so you want to know what is the value of maybe argument 0. So you just need to pass the save it. And so this is a very small script that will run the passes on this particular this is the input. gem.mlir will be the input, and you can basically run the pass. As of now, it is not mainstream. When it is mainstream, you just need to add mlir opt slash array convert LLVM, array to LLVM or something like that. So what that pass will do is like it will generate one MLIR. So this will contain something like this. So basically do is like it will call the LLVM, the standard printf library over there. Maybe I can. So once this is done, maybe we can lower everything to the so the LLVM IR. So once this is the MLIR, so we'll convert everything to LLVM IR. That's the normal pipeline, MLIR pipeline we have these days. So this will generate the stop. Yeah, okay. So it will generate the LLVM. So I've written a small driver function to call the gem file. So this is the driver, and if you compile it with the generated LLVM file, so now we just need to run. So as you can see, the arc, what was that? So we printed argument 0. That was the third argument. And in the third argument, k is 1000. So this is what we have done. And there are printfs, there are asserts, and everything is there. Yeah, so that's it.
Questions? Do you have options which you have added?
Yeah. So we have added. So these were the things I could come up with, and the start time and stop time, that will basically calculate the what amount of time the operation has taken to execute, and we are still working on that. And this print shape is something I found very useful, like dynamically printing the. So memory won't have memory will usually memory will have a question mark and then followed by 128 or something. So at the runtime, what is the shape of the that tensor? That is a useful operation. And array dot count is there, so it will count the number of frequency of number the operation as work. Yeah, and those are the things we are working on, and these were the things I could come up with. So there are so many other operations that we can come up with. Anyway, it's extensible and it's open source. Everyone can contribute to this. Yeah.
Just a follow-up question on that. So, other thought of conditional one, adding condition like equivalence.
Yeah, assert is conditional.
For on a value. Oh, okay.
Yeah.
From that perspective.
Yeah. Yeah, maybe we can think about that.
Adding a condition to an existing print only when necessary.
Yeah, we can do that.
That's all.
Thank you.
So, next we have Nishant Sachdeva from Team Future Forge, who's presenting IR to Web++.
Sorry.
ದಿನೇಶ್ ಚೆಕ್ ಮಾಡು ಚೆಕ್ ಮಾಡು ಮೀಟು ಮೀಟು ಮೀಟ್ ಮೀಟ್
Okay, cool. Hi, good afternoon, everyone. In this presentation, I will talk about the improvements that I've been trying to make to IR2VEC and how they've come about. So what is IR2VEC? Now, as a background, compilers have a lot of optimizations, and in many of them, they use heuristics. These heuristics are often planned and made by experts in their fields, which they design very meticulously, but there is a limitation to these kind of activities. And when we use ML models to get to these heuristics, the results are often better. Now, to train ML models, you need embeddings. And how do you get embeddings? You need tools like IR2Vec, which will take LLVM IR and convert them into embeddings, which can then be used into downstream tasks. IR2Vec specifically does this by two methods. One is the symbolic embeddings and one is the flowware embeddings. Specifically for our case today, I will focus on flowware embeddings. Flowware embeddings, the MVP here is that they take an instruction and they take surrounding context, encode them all together into one final embedding, which is supposed to be better than the usual conversions. Here, if you focus the first two portions, the collect write definitions map and computing the reaching definitions, this is going to be the focus of my work here. Sorry, yeah, thank you. Okay, so there are a few limitations with IR2VEC as it exists right now, especially in the first two stages. Now, the collect write defs map and the reaching definitions, they use top-down DFS-like approaches to calculate the reaching definitions, which is one, it's inefficient, has some limitations. Secondly, a lot of this is essentially re-implementing passes which exist in LLVM already. So if we can use that code, of course, model it around, make some manipulations, and then use it in actual IRTOVIC, we save a lot of developer time, we make maintainability easier, and we, of course, cover some edge cases which we could have missed in our actual core code. So the MVP of my project here is that we use the LLVM API for the get underlying object, and we use the LLVM's memory SSA passes to essentially recreate the reaching definitions code that has been written from scratch for IR2VEC. Also, once this is made, once this actually goes upstream, we have also made this Python bindings package to make sure that the ML community actually can benefit from the improvements that we make. Now, write defs map. So, like I said, it's a top-down DFS-like approach which is in the native source code, and replacing it with underlying object API causes a massive amount of speed up, where we took a source code, we took the SQLite source code. With the original code, it took about 20 seconds to get to the write defs map, but with the new approach, it takes about 0.2 seconds. So that improvement is a huge plus that can go and help the community, the ML community, a lot downstream. And to test this out and to check the actual accuracy of the approach, I took a benchmark set of about 40,000 files, ran the same approach on it, and we got an accuracy where about 99.7% test files gave back the same maps. So the good thing here we can to report here is that the LLVM underlying object API and the actual source code that IR2VEC has, they both reach the same results, but one is far faster than the other. Now, what if I told you that the write defs map is not required at all? This is where the reaching definitions and approach comes in. The reaching definitions take the write defs map, where basically for every location you have the list of instructions which write to that location. Then for a target instruction, it removes all the instructions which don't actually reach the place, hence giving us our final reaching definitions. Here, we can replace this entire process with a memory SSA API, where if we use the get clobbering memory access functions, it returns two outputs. One, if it's a memory def, that's it, answer. If it's a memory file, you take the incoming nodes and run the same process in a while loop, and then you get your answers. This is a huge simplification over what we have right now, and it gives us better results than what we have with the current IR2X. For example, in this case, if you see the store instruction which takes the contents of 8 and store them to 9, the reaching definition which IR2Vec gives us is the definition of 9 as a load pointer. But with memory SSA, we reach the initial store instruction which actually wrote to that memory location. So in that way, semantically, this is a much more correct way of getting the reaching definitions. In another example, if you see here, look at the result instruction. Result is trying to load the contents of the pointer to variable. With the native IR2VEC, we get the get element pointer definition, which defines the pointer to. But with the memory SSA, we get the actual instruction, which is the store, which actually wrote to pointer to. So we have seen here that, okay, One is that one thing to notice here is that in this entire approach with the memory SSA, there was no need to collect write defs map anymore. That's gone. So the speed up we got initially, even that the whole process is simplified now. So the impact here is two parts. One is that okay, there is a performance improvement. Second, we have gotten better definitions here. This can help the community a lot, and of course, needless to say, the code becomes a lot more maintainable now. It's just one call to the memory SSA API, which itself is a battle-hardened upstream. Okay. Now, coming to upstream. So let's say we merge this all, but then how does the community get to this? IR2VEC initially came with its own Python bindings, but that is coupled tightly with the initial native source code. So anything we put into the LLVM IR2VEC doesn't get to the Python binding. So to mitigate that, I designed is a big word, but yeah, I made a Python bindings package using this PyBind module, which is something even MLR uses. So I took inspiration from that. We get a PyBind package, and I made the wheels files for it and put them in a collab notebook and on test pypy where we can actually just one command install and run it. In fact, this is something that even the community has been asking for. So this is a issue that's been made for the LLVM project. There's a GitHub issue which asks for Python bindings for IRTOVEC. So this project will also address that. But yeah, so the essential part here is that instead of using sub-process calls into LLVM to make sure that okay, we get some bindings, we can just install and have our answer in 3 lines. So yeah, to summarize here, we have the memory SSA improvements and we have a Python bindings package to actually support and bring that to the community. Future work we can discuss, but yeah, I would like to open it to questions.
So you talked about reaching definitions analysis. So saying you're essentially using the underlying reaching definitions analysis existing in LLVM, or have you encoded it? I got confused when you were mixing the two things. So
Mhm. So one thing, reaching definitions analysis is a wrapper that we write on top of the alias analysis, which already exists in LLVM, which is the native source code. Here in the improvement in the code that I have done, it's completely calling and offloading everything to memory SSA.
no. So reaching definitions and alias analysis, what's the connection between the two?
Okay. So alias analysis, of course, will give me an API to check if any instruction clobbers the address of my instruction or not. That's one. That is the API that the native IRTOVEC uses when it's actually checking if any instruction wrote to my instruction or not. If it does, then it is my reaching definition.
Oh,
All of that is already done with memory SSA.
okay.
So my project replaces the native code that we wrote with memory SSA, where one, the maintainability of my code improves, and secondly, memory SSA covers some edge cases which I had not covered. When I say I, it is the native IRTOVEC source code, which
Yeah. And you also talked about data. So other than reaching definitions analysis, is there any data flow analysis that you did? And this data flow analysis that you did was intra-procedural within a procedure.
memory SSA is specifically intra-procedural, I cannot go past into other functions. But the IRTOVEC embeddings itself, they do capture that. So let's say I have some embedding with an instruction which made a call to a different function. Now, in its own call, this function would have stored its own definitions somewhere, and then this actually brings it in to inculcate into the main procedure. But in the same piece of code, no, it doesn't happen.
Even if you did that, that will be context insensitive. If you know the distinction between context sensitivity and insensitivity.
But essentially, we cache the results for each function, and then when we realize that okay, a function call was made from function A, then we call the contents of function B and append them into our result.
Quick question. So this is improving IR2X,
Yes.
right? So have you considered upstreaming some of this?
Yes.
Okay.
Yeah, so like I just mentioned, the LLVM project has a GitHub issue for the Python binding, so that itself we can target. But of course, we'll have to calibrate our CMake files and with the standards of the LLVM. But in general as well, one is that I want to make sure that the approach is correct. There are some cases in memory SSA as well, where let's say if it reaches a memory 5. Now, with a memory 5, it tries to get all the incoming nodes and tries to run some optimizations on it. There are some cases where it will return only one dominating instruction. Now, I don't always want that. I want all the live definitions which reach my instruction. So There are some cases where I would want to have some control. So those things, trade-offs, we'll have to decide on. And then yes, target is to reach upstream.
Okay, so you don't have to replace it, right? You can add it as an additional sort of
course,
analysis
yes.
where this would be useful.
Yes, yeah, that would be an engineering work we can see, because I had to work, like I said, it collects right def's map and some initial information before it begins its work. So if I am going to allow for memory SSA, then none of that is required. But that's an engineering work. But yes, we can have a flag where users can decide which one they want to use.
So you have not considered upstreaming yet, right?
No, this is, I would still say this is something in progress. I want to have a more sturdy results before I go ahead.
We stop now in the interest of time. Up next, we have Team Ubiquitous with their LLVM part deobfuscator.
Yes, thank you everyone.
Thank you. The second last
काम कर रहा है? Okay. Okay, so good evening, everybody. I'm Ketan, and I'm here to present Ubiquitous, which is an LLVM-powered program analysis tool for breaking binary obfuscation. Quickly, let's discuss what is obfuscation. Obfuscation is writing bad code, but intentionally, as opposed to the common folly of unintentionally. Why would somebody want to write bad code intentionally so that it becomes hard to analyze? What is the common use cases in malware? Malware authors don't usually want their code to be reverse engineered and analyzed, because that would obviously hinder the malicious activities. Other people who want to do this are people who want to implement and protect their IP. So there's a lot of DRM systems who obfuscate their code, and you don't want other people to poke into your code and find out your algorithms and reverse engineer them. So people tend to obfuscate code. What have we built? We've built Ubiquitous. So we're showing that obfuscation is barely secure, and we do this by breaking obfuscation. And we do this by breaking obfuscation by commercial tools. It's not our own tool. These are commercial tools that are used by many people. So let's discuss code components. We've written our own LLVM interpreter for this purpose. We've not used LLI because I didn't like the code base, and I found it hard to hook into it. So I've written my own LLVM interpreter in I support about 30 or so opcodes. We support about 30 or more opcodes, and we're in the process of extending this. We've written a taint tracking engine, a control flow recovery algorithm, and opaque predicates optimization. More on this later. This is our CLI. Quick look. Let's talk about targeted deobfuscation first. This is a weaker algorithm of deobfuscation wherein you target it to particular obfuscation algorithms. So this is control flow flattening. This is not how a regular program should ever look like. There is no hierarchy between if and else. Everything is flattened. But typically, you would have an if-else construct, and the program follows a nice, clean flow. But if you flatten it using an obfuscation tool, this is done by Tigris. It's a very popular obfuscation tool, written by University of Arizona, I think. I'm not sure. So, but this has been flattened by Tigris, and a lot of other obfuscators produce similar code. Uh, this is how we unflatten it. So we do a dominance analysis, first detect loops. After performing a dominance analysis to detect loop, we implement heuristics to detect this dispatch block. So you can see the main block that dispatches to every other block, the one with the fewer instructions, and it leads to every other block. So that's the dispatch block. Once we have identified dispatch block using our heuristics post dominance analysis, we can walk through the flow and reconstruct this. So this obfuscation can easily be broken. Let's talk about some metrics. We can see that we've reduced branches by a significant amount. Let's talk about opaque predicates. What are opaque predicates? Opaque predicates are conditions which seem to be conditions, but when you actually look into them, they're either always true or always false. So it's either like if one, or while zero. But when you do static analysis, it seems to be a complicated condition. So a simple example would be if x squared greater than zero. We know if x is an integer, it's always going to be greater than zero. It's always going to be positive, I mean. So that seems like a condition. So you get two branches, but one of them is always unreachable. So in static analysis, the control flow graph looks really, really long and weird. But upon symbolic execution, we can just resolve and prove that most of those conditions are either one or zero. I'd be happy to discuss the exact algorithm for symbolic execution in the Q&A session. But there are certain limitations of targeted deobfuscation. What are limitations? It is not a general solution. It depends highly on heuristics and the implementation of the obfuscation. So if the obfuscation designer makes a few changes, our obfuscation is suddenly no longer valid because we relied on certain heuristics to deobfuscate. Also, opaque predicates, we also have a certain kind of obfuscation called virtualization of code. Now, this is one of the most powerful obfuscations and it's heavily resistant to static analysis. How does that work? Okay, so this is how virtualized functions look like. Now, this might look similar to a control flow flattening algorithm, but it is not. The dispatcher there is an interpreter on its own. What I mean by that is the program itself has been transformed into an interpreter. So the interpreter is going to have custom bytecode. Let's say bytecode 1 represents the AND operation, bytecode 2 represents the OR operation, and all these operations are implemented in bytecode. So the bytecode is stored somewhere in the global memory. There'll be a program counter, there'll be a stack, there might be a heap. There is this unlimited type kinds of VM design that you can go through. The problem with this is now obfuscation designers have a lot of freedom in what kind of VM they want to design. So there is no fixed heuristic that we can go with. It can be a heap VM, it can be a stack-based VM. The bytecode can be in global memory, can be locally. So it's basically the point is static analysis cannot do this. How do we fix this? Taint engine. So what is taint analysis? Taint analysis quite simply is when you taint a value and then you track how the value flows through the program. So what we do is we taint the input of the program, and as operations are performed on the input, we track what are the exact operations that the input is going through. So this is called dynamic taint analysis, and this is what I wrote my interpreter for, so that I could execute the LLVM IR and track exactly what is happening to my input. Now there's two kinds of things that happens here. We need to record all tainted instructions because this will give us something called data dependency. So if I have my input, which I taint by default, and then I have something called result is equal to input into 2. So now the result is a data that is dependent on input. Computation on input gives me result. So this is called a data dependency. So result will also become tainted. Now, if the input is stored to a memory location, that memory location is also going to be tainted. So we have certain taint propagation rules. I'll be happy to discuss what the rules are for taint propagation. We also need to untaint memory to prevent over tainting. If you have over tainting, then you virtually have a big trace, and that is as bad as obfuscated code. So I'll be happy to discuss the exact algorithm. We also log all the VM instructions. By VM, I mean the interpreter, virtual machine. We also log that. Why do we do that? Because, like I mentioned, there's a data dependency and there is something called a control flow dependency. So if you have something like if input equal to 0, y equal to 10. Now y does not directly depend on a computation on the input, right? It does not say y equal to input into 2. What is happening here is it's a control flow dependency. If input equal to 0, y equal to 10. To do this, we need something, we will have to combine post dominance analysis along with our tainted instructions to finally retrieve this code. So you can see that again, we went from this virtualized function after taint analysis plus post dominance analysis plus running the O2 pass of LLVM, we came to a simple hash-like function. This is the sort of function that you would like to hide in a VM because it's very easy to analyze, but it's also crucial because a lot of license checks, a lot of malware stuff use this kind of function. But I'd be happy to discuss the algorithm more in detail. Yeah, thank you. I'd like to invite my teammates also on for the Q&A round. Some metrics and some limitations. Okay.
So I have two questions. So basically, first is you have a closed world assumption about the obfuscation. So you're assuming that obfuscation is only of these 1, 2, 3, 4, 10, whatever n number of ways in which it can be done. Is that right? Or
for the first three obfuscations, yes, which was control for flattening, and for the first two opaque predicates, yes. But the taint engine does not assume anything. It is, I was only showing virtualization because it is the most powerful kind of obfuscation there is. So if the taint engine can work towards that, it will also work towards control flow flattening, for example. Suppose you don't want to rely on heuristics to do control flow unflattening. You can use our taint engine because it's also going to track the taint and it will produce a neater CFG. So we are not making assumptions, but yes, there are definitely some types that we cannot handle.
what you're calling as taint engine, to me it looks more like slicing.
Definitely, yeah. I am not exactly 100% up to date with the definition of slicing, but yes, taint engine I read in a paper somewhere is similar to slicing.
Yeah. So that second thing, you're doing it dynamically, you're not doing it statically, which means that you're not sure that you have covered everything.
Oh, exactly. So if we look at further work here, we want to implement a symbolic state tracking. We have already started doing that. This will help us incrementally track paths. So what we're doing is once we come to a condition which is tainted, so that condition depends on the input. There's obviously going to be a few paths and we can only take one. But we will track the symbolic, the operations performed on this input up to this point so that we can feed it to a SMT solver, Z3 for example, and generate a new input. And we will run the program with a new input to explore the other paths. Now the user will give user freedom to to see how many paths they want to explore, because there might be path explosion if you set all the paths. There might be path
Why
explosion.
not static analysis?
A static analysis for VM we found to be very, very inefficient, because the kinds of the VM might be loading bytecode from. The problem is you'll have to do all sorts of analysis. You'll have to do pointer analysis, alias analysis, and this is going to be a big, hard problem, and it might not even be very accurate. So yeah, but we are relying on static analysis, which is post dominance analysis, to complement it with our taint engine.
So thank you. For our last team for today, we have Captain IRS with DSP Lance.
Yeah, sure. Yeah, sure. Yeah. Seems a bit off. Yeah, you just need to stand here and speak. Yeah. Huh? It's a bit to the right, right? Okay, let's like it's offset to the right. So this because it's flying. Okay. That's all. It's next. It's the next one. And then we find. That's a bit. Yeah. Okay. Use offset. Is a VMH. Okay. Good evening, everyone. I'll be talking about the DSP line project. Uh, so let's start with the motivation. Like when you're writing code targeting like vector process, like you either like have this trade-off of like control over performance versus the ease of programming. So I wanted to create a language that sits right in the middle, like between the intrinsics and writing using some vendor-specific SDKs. So it's essentially a language that gives you constructs to build something like a manual. So the goal is to like develop a vector processing DSL for architecture, specifically like NPUs with high bandwidth vectors. And ideally, I should be using MLIR to progressively lower the DSL. And I specifically focus on the Qualcomm Hexagon NPU for this. So MPU usage is on the rise, like with ML image processing, vector processing workloads. So the problem is like LLVM doesn't like utilize these like max bit width effectively. So you should be writing like code in like backend specific intrinsics, which is very painful to write. So we need something better than that. So that's the motivation behind this project. And specifically with respect to the hexagon NPU, if you see on the left, like this, uh, the code here, like it uses the scalar processor. It doesn't use the vector processor in the NPU SoC. So we need to change this. And this was like just 3 days before I submitted this, and like even Qualcomm seems to be thinking in this direction, and they have this new RFC to LLVM related to this specific problem. So the hardware target is the Qualcomm Hexagon NPU, and this NPU has this HVX unit, the hexagon vector extensions, which I'll be leveraging in this project. And unfortunately, I couldn't show a live demo. I could have shown it in this phone, which I have, but unfortunately, I couldn't get the laptop working with this. So sorry for that. So I'll skip the aspects of the hardware since it was covered by a Qualcomm talk before this as well. So the high-level architecture here is that like the DSP lang and the DSP lang dialect are derived from the MLIR toy example, which is given by the NVIDIA project itself, and it leverages a lot of the existing infrastructure like the arith dialect, affine dialect, and the vector dialect. And the main contributions of this project are these two new dialects, the HLHPH dialect and the LLHPH dialect, which eventually help you to lower any dialect to this LLVM IR. So the more about the dialects, the LLHX dialect is a direct interface between MLIR and LLVM Currently, the hexagon intrinsics are not exposed to MLIR. So this is the first open source project to do this. And the problem with the low-level dialect is that the type information is not there. There's no specific type information. So I have built a high-level dialect which has the correct type information, and we progressively lower it from the high-level dialect. And this is how the DSP line dialect looks like, and it operates on like tensor and number of types. And this is the key contribution of this project, like the selective vectorization pass, where it analyzes the loop body for the data types which are being used in the loop and determines the step for the loop to do the vectorization. So the front end is basically like modified from the MLR example. So Jonathan, let's walk through the passes quickly. And the DSP line dialect, like the traditional LLVM passes are applied to it, and this selective vectorized pass basically like determines the step size as 32 and does the vectorization, and then it's converted to HLHPX, and this is converted to LLHPX, and then to the LLVM dialect and to LLVM IR. And when the optimizer is done, uh, like we'll be able to generate the vector processing code, the most efficient vector processing code for this particular use case. And since you don't have the demo, I just have some screenshots, and we have this DSP-Lang implementation and the C implementation. The DSP-Lang implementation effectively uses the HPX vectors, so it's able to get some performance improvement at the cost of a loss of precision. So these are the like HLHPX and LLHPX ops written using TableGen, and the translation test suite is also like auto-generated. And for converting from HLHX to LLHX, I've experimentally used the PDLL instead of using TableGem. And arith to HLHX is also lowered using PDLL. So this is one of the first dialects in existence to basically like expose these HX intrinsics to the broader ML layer ecosystem. And it's open source as well. It's like end-to-end fully open source and reproducible. And the future work is currently like only binary operations are supported. In future, like reduction based workflows like and sliding window based workflow will also be supported. So thank you. These are like used from LLVM directly.
These are
Yeah.
LLVM dialect, right? So the step that you are getting, can you go to the part where you were seeing the step equal to 32? Yeah. So this is generated by LLVM. Sorry,
This
MLIR, right?
this
Or
step
the
is
affine
determined
pass.
by me. Like,
This is generated by you?
yeah.
Okay, so how
This
do you
pass.
determine this?
So I basically look at the like loop body and see the data types it's operating on. In this case, like all the operations are happening on F32. So the target bit width is 1024. So I just divide 1024 by 32 and determine the step size for this particular instance.
Okay.
Okay, thank you.
So that brings this session to a close. Nothing we have a talk. Just can see that. About the final see that where is classified. Meanwhile, I equip the just there is in the right on left.
Come on. Yeah. This works. Yeah. Okay. Good afternoon, everyone. For those of you who are still awake and still present, so I'm Prachi Pandey, and I'll be speaking about the compiler research and development initiatives at CDAC Bangalore. But before I begin the talk, I would like to thank the IICT organizers for bringing this platform, bringing all the compiler enthusiasts under one roof. And that's a tremendous work done by them. And also, congratulations to the hackathon finalists. All of them have done a very commendable job. Wish them all the best. I know you must be nervous about the results. So, wish you all the best. So I'll be discussing about these things, just an overview about CDAC and its journey, then about one of our products, CAPSI, which is an automatic parallelizing compiler, and our open source SYCL compiler initiative from CDAC, which is called as PARAS. Then I'll be telling about the CDAC indigenous processor roadmap, and finally about our indigenous compilers, which are targeted for these CDAC processors. And I would also, in the end, like to discuss the career opportunities in CDAC for compiler developers. So CDAC, which is the Center for Development of Advanced Computing, is the premier R&D organization of the Ministry of Electronics and Information Technology. It was started with a bold mission to develop supercomputing capability in India. In fact, it's a very interesting story. I encourage all of you to look. It is there in the internet how CDAC was founded. So you can go back and look it up. And we are the pioneers of Param supercomputers, the first one to bring supercomputing in India. I think I have a next slide which talks about that. But now we are into all other verticals as well, other than HPC. We are into quantum computing, we are into artificial intelligence, the DER5 program, then we are into eGov projects, IoT, VLSI, and so on. So this is the CDAC Param series of supercomputers that I was talking about. The first one, Param 8000, was in 1991. And this was a result of technological sanctions imposed on us, which is the story I was talking about. And something makes me feel that we are heading that way again. But yeah, that was a result of the impositions on India for import of supercomputers. Then from Param 8000 to 10,000 to Param Padma, which was the first supercomputer to feature in the top 500 list of supercomputers in the world. And then we have Param Yuva, which was also there in the list. The Param Shivai is in IIT BHU. There's Param Shakti in IIT Kharagpur. There's Param Porul in NIT Trichy, and all the major institutes in India. We have our installation. Even here in IAC, we have Param Pravega, which is a 3.3 petaflop system. And now we are also releasing in a few months the biggest supercomputer of India in CDAC Bangalore, which will be of the capacity of 30 to 50 petaflops. It will be soon getting released. So, like I was saying, we have an automatic parallelizing compiler. You would have seen the poster in the poster session. So I'll just tell an overview about this. This takes a sequential program as input, the typical HPC codes, sequential codes, C, C++, Fortran codes, and it converts automatically to parallel codes in OpenMP, OpenAC, and OpenCL. And behind the scenes, it has typical compiler technologies which we are employing here, which is liveness analysis and dependency analysis, your control flow analysis, and so on. Then we manipulate the AST to finally get the parallel code. And this is also deployed on all the Param supercomputers that I was mentioning about in the previous slide. So the next one is the open source compiler initiative from CDAC, which is Paras compiler. The theme is code once, execute for all, which means that you write a code once and the same code will execute in your CPU, in any variant of GPU, be it AMD, be it NVIDIA or anything. So this basically gives the user the flexibility to just write a single source code and it can execute on any target. Again, this is available in GitHub actually. You can see the link over here and also the QR code. So I encourage you all to use it, to explore it, and also to contribute to it. There's a huge growing community of SiCL, so you can explore that as well. Currently, it is tested on the all the popular CPUs like Intel, AMD, NVIDIA, and the GPUs like AMD and NVIDIA as well. And it is available on Indian supercomputers and multiple international installations. So you could contribute to the community. Now coming to India's indigenous processor roadmap. So this is with the ambition of achieving self-reliance in technology. So with that goal, we are coming up with the line of processors, both for embedded class as well as HPC class. The first one, Vega processors, Vega series of processors is already available. It is for the embedded class and it is available in 32 and 64-bit form. It is there in single and multi core version as well. Then coming to the HPC class of processors, the immediate one that we have coming up is OHM processor, which is based on ARM Neoverse V2 architecture. So we are developing a processor based on the ARM architecture. And also we have started the development of HPC class CPU based on RISC-V architecture. The OHM processor is slated to be released in 2027 and the RISC-V based HPC core CPU architecture is slated to be released in somewhere around 2029. Along with the CPUs, HPC CPUs, we are also having a plan for release of our own indigenous GP GPUs as well as AI accelerator. So the GP GPU is based on RISC-V architecture with our custom instructions, and it supports both matrix cores and HPC cores. And our AI accelerator is based on systolic array architecture. It is having a proprietary ISA, and it supports both AI inferencing and training. So this is basically about our roadmap for achieving total sovereignty for processor technology in India. So next, this is about, so your processors alone cannot give you self-reliance, right? The hardware alone cannot do that. There's a need of software which will drive that innovation. So we have our own indigenous compiler developed in CDAC, which is for powering these indigenous processors, which are again developed in-house in CDAC. And that is called as Chakra. So in fact, I'm introducing Chakra in this forum, which is an indigenous compiler from CDAC. So it targets all the indigenous processes that I was talking about, including including the compiler for OHM processor, Chakra for RISC-V based CPU processor, then your Chakra for GP GPU, as well as Chakra for AI accelerator. So we'll see each of this one by one. The Chakra for OHM processor is based on the LLVM framework. Like I was telling, the processor itself is based on ARM Neoverse V2 architecture. So we have taken the LLVM toolchain for ARC64 and we are optimizing that toolchain. We are currently targeted some platform independent optimizations in the mid end, which is for HPC class of applications. So like vectorization, we have changed the default vectorizer of LLVM with the vPlan. and it is giving us some promising results. We have also done some loop optimizations like loop interchange, loop unroll, and all, which also have been posted to the open source LLVM community. This we are doing along with, we are syncing up with the ARM compiler team for coming up with these. And we are also targeting hardware specific optimization for our own processor. So both of this will be benchmarked with the HPC workload because this is targeted to be a HPC class processor. Then we have the RISC-V class of HPC processor, Vishwa AP, which we are going to call. So the Chakra compiler for that is again based on LLVM framework. But right now, what we are planning to do is make the ecosystem of LLVM strong for RISC-V, especially for the HPC scenario, because the LLVM toolchain for RISC-V right now is in a very nascent stage when it comes to HPC. The x86 and the ARM ecosystem is still evolved, but we are interacting with we are collaborating or contributing to the open source community where we want to make it more robust, more stable for the HPC class as well. So the same kind of optimizations that I was talking about, mainly targeting vectorization, loop-based optimizations, is what we have started with. Then coming to Chakra compiler for Vishwa GPGPU. Now this is again India's first GPGPU that we are planning to, that we had already developed. The prototype has been done on FPGA. And for the same, we are developing the Chakra compiler. This is based on, again, on the LLVM framework, and it will support both matrix cores as well as HPC cores. And we also have toolchain support for POSIT number system, which is an alternate number system to traditional floating point number system, which gives better accuracy in certain AI workload cases. So we are also targeting that. And the main thing why we are so confident that this program will be a success, because everything is done in-house, from the hardware team, which is doing the GPGPU development, to the compiler team, to the device driver team, runtime team, the software stack, everything is in-house. And so this will lead to seamless integration with all the components and better optimization. So coming to the compiler specific backend development that we are doing currently for GPGPU, there were talks from yesterday, like what are the key things that differentiates between a CPU and GPU, the memory access being one significant thing, right? So we are also doing that. For memory access, we are doing the optimizations. And then also, since we have taken the base RISC-V ISA, which is essentially scalar instructions, so we have to add our own custom instruction support for SIMT operations. So for threading and for generating the sequence of instruction, which would work in a SIMT fashion, we are changing the LLVM backend for that. And also for matrix core support, we have added our instruction. For memory operations, we have added new instructions. So basically, it's a combination of RISC-V ISA plus our own custom instructions. And it has to be compatible with the popular AI frameworks as well as your HPC programming models for GPU, like OpenCL CUDA. Next, we have the compiler for AI accelerator. Like I said, it would support both inference and training, and also, again, it would support POSIT number system, and it will be both AOT and JIT compilation as the need is. It is MLIR based design, and we have developed some dialects, some custom dialects for CDAC for targeting our accelerator. It has, which includes quantization, sparsity, etc. And then many graph level optimizations have been done. For example, graph fusion, layer fusion, operator fusion, and so on. We'll also, same for GPU and AI accelerator, we are planning to have a system built for that. So we have multi-accelerator support, which supports distributed training. In the same way for GPU, we are having multi-GPU support. And then implementing of optimized memory strategies. So all of this together makes our MLIR based compiler, Chakra compiler for Vishwa AI accelerator. So that's about our compiler initiatives that we are working on in CDAC. Now, this is something I would like to stress for you people. If you're interested to contribute in any of those areas, there are many ways you could join CDAC. For students, we have internship opportunities, both for BTech final year, which is 6 months internship, and the MTech students, you have 1 year internship opportunity in CDAC. So if you are within the top 50 NIRF, there's immediate internship options available. And upon successful completion of internship, you'll be mapped to the CDAC roles. Then for graduates also, we have currently openings going on. We are planning to start, in fact, our campus recruitment in all the leading colleges in India. And parallelly, we also have an open ad. Also, we posted in the job portal itself. We have a QR code where you could register. You don't need to register. You just need to send a couple of details, fill in a couple of details, and we'll be reaching out to you with whatever you want to work with us. So with that, I would end my talk. Thank you. Any questions? Thank you. Yeah.
So we have a quick conclusion ceremony. This plug it on. So, you switch off the front lights. It's hard to see. Switch off these lights. हाँ off कर दो अभी. We'll hand over. No, they will. Sorry. Fine. I'll just change from the laptop. I have to change with this.
Yeah. You can. No, wait, just
Yeah, that's fine. That's fine. Okay. Reload. So now we begin. Yeah. Now we begin the conclusion and award ceremony for the Innovations in Compiler Technology Conference 2025. So first, a few short notes. In numbers, this year's conference saw 379 attendees with 312 male participants, 67 female participants, 248 professionals, and 131 students. So this is up from the 210 participants that we had last year in total. In addition to this, the SegFault hackathon, in its initial preliminary rounds, had 48 teams with 101 participants. So, all in all, this conference workshop reached about 500 people. Some other numbers, the youngest attendee is about 19 years old. Actually, there's a bunch of 19-year-olds. The oldest attendees are over 60 years old. The average age of all the volunteers is 20 years old. All of them are second year and third year BTech students that ran this entire conference. We had 21 talks, including 3 invited keynotes, 6 hackathon presentations, 10 poster presentations across 2 days. No wonder all of us look really tired. It's been a pretty intense 2-day program. We had wide representation across a lot of companies. Here are some of the companies that were represented at the hackathon. This is a very small sample. We had NVIDIA engineers from NVIDIA, Intel, AMD, Cerebras, Broadcom, Blackfig, Google, TCS Research, MIPS, Amazon, CDAC, Sony, Multicoreware. And on the academic side, we had good representation from a number of colleges. We had students and faculty from IIT Bombay, IIT Madras, IIC Bangalore, IIT Hyderabad, IIT Delhi, PICT, Danan Sagar, PES, KTU, VIT, KLE Tech. Also, we this is not a one-time thing that compiler engineers don't need to gather once a year or twice a year. LLVM Social Bangalore runs monthly meetups. We have over 3,000 members. That makes us the largest compiler gathering in the world. So we have a YouTube channel where all the talks from this conference will be posted. You can find it on YouTube at LLVM Social Bangalore. You can also subscribe to our meetup page. So if we're ever meeting up either here in IASC or in one of the tech offices, you can meet us there. And this is the committee. We had a wide variety of support from almost all of the leading compiler practitioners and the organizing committee. And the volunteers were from Point Blank. If you saw them in their hoodies and jackets. So it's a student team based out of Danan Sagar that competes in competitions, does open source, does hackathons, organizes competitions, and everything else. If you're looking to hire bright engineers, look up at careers.pointblank.club. This is a photo of the volunteers. And a big thank you to our sponsors from NVIDIA, Google, Qualcomm, Quadric. Also thanking our knowledge partner CDAC for sponsoring this hackathon. A big thank you to Point Blank and ACM and iSoft for supporting this conference and workshop throughout. So first off, I'd like to call all the judges on the stage for a small token of appreciation. Please. Come there. उनको देते I'll give it to you. Yes, sir, please. You come here. Yes, sir.
Photographer is missing.
It's fine. Yeah. The trophy is an acrylic dragon made by our very own designer, Shivansh.
Oh.
So yeah, he's designed it himself. Excellent. Thank you, sir. And yeah, thank you, sir.
Thank you.
Ma'am, please. Thank you. That's it. So yes, sir. Winners, would you like to announce, sir? 3-1.
Okay.
Yeah.
Uh,
Yeah. Yeah. Please call. Yeah, ma'am. Hari Babu, sir. Sir, can you call Hari Babu, sir, to the stage? Yeah. Yeah. They have it ready. 3-2-1. Wala. Huh? Huh?
I have been given the responsibility of announcing the I have been given the responsibility of announcing the names of the hackathon winners, and it's a pleasure for me to announce them. They will be given prize by Mr. Hari Babu from CDAC. So the third prize goes to Team Future Forge. Team Future Forge, please come here. Please come quick. Be quick. You're getting a prize. The second prize goes to me because I don't know LLVM.
And the first prize, any guesses? The first prize goes to Team Ubiquitous.
Yeah, yeah, excellent.
Oh, you provide mementos.
Yeah, but just all of them.
I would like to call the remaining teams on the stage for their being given some mementos for participation. Please come. I don't have the names here on paper, but please, all the remaining three teams, please come on the stage.
That is called one of the winners, all the four high qualities. There are some certificates from CDEC.
And now there are certificates for all the six teams. Please come on the stage. Certificates from CDAC.
Someone is going to announce the names of all?
No,
Yeah, yeah. So you take care of
yeah.
it now.
So everyone know LLVM, Ubiquitous, Captain IR, Team Q,
Yes.
Black Point.
Thank you, sir. I will share the list. No.
There are hundreds that